Okay, good afternoon. Good afternoon, can you hear me? Okay, so yesterday we started sinusoidal oscillators. Oscillators we have broadly classified into two types. One is non-sinusoidal or relaxation oscillators. The other category is sinusoidal or harmonic oscillators. Non-sinusoidal, we have already seen square wave generator, which is the astable multivibrator, and triangular wave oscillator. So all these are non-sinusoidal oscillators. Yesterday we have seen sinusoidal oscillators. So how do we build a sine wave? To build a sine wave, we should have a provision to simulate a second order differential equation, or from the pole zero plot we can say that we need complex conjugate pair of poles, right? This is possible by two RC networks or at least one LC network. So if you have two RC, at least two RC or one LC, that will simulate a second order differential equation. And then by connecting an amplifier to that beta network, you have to make the amplifier gain A exactly equal to 1 by beta. A should be exactly 1 by beta, is it not? Or A beta equal to 1, the loop gain equal to 1. This is also called the Markowson's criteria for oscillations, right? But to solve any oscillator problem, the technique is only one. The strategy is you have to make the loop gain equal to 1. What about a Wien-Bridge oscillator? Wien-Bridge. So this is a Wien-Bridge oscillator. How do we calculate the frequency? The frequency of oscillation. Try to make the loop gain equal to 1. But where is a bridge network here? A bridge network, a bridge will have 4 arms, is it not? Four arms of a bridge. Suppose this is node 1, node 2. Node 2 is ground. Node 3 and node 4. So node 1, 2. Between 1 and 2, you have a RC in parallel. Between 1 and 3, you have RC in series. Between 3 and 4, you have RF. Between 4 and 2, you have R. So that is why this oscillator is called a Wien-Bridge oscillator, Wien-Bridge. And between 4 and 1, non-inverting is at 1, inverting at 4. The output is given to 3. So this oscillator can also be drawn in this fashion, right? So let this node be V0, this node be Vf. So let us calculate the loop gain, right? So step 1, find gain A, V0 by Vf. So what is gain A? 1 plus Rf by R. This is gain A. Step 2, find beta. Beta is Vf by V0. To the beta network, input is V0, but output is Vf. Input is V0 and output is Vf. Replace capacitor by 1 by Sc. Or you can treat this network as Z1 and the shunt arm as Z2. The series arm impedance as Z1 and shunt arm impedance as Z2. Then what is Z1? Z1 is the series combination of R and Sc. And what is Z2? It is the parallel combination, R parallel with 1 by Sc. It is R into 1 by Sc by R plus 1 by Sc. It is R by 1 plus SCR. So what is Pf by V0? Voltage division rule. Beta is Vf by V0. It is equal to Z2 by Z1 plus Z2. Z2 by Z1 plus Z2. So substitute the value of Z1 and Z2. Therefore, beta equal to Vf by V0. If you substitute the value of Z1 and Z2, it will be SCR by S square C square R square plus 3 SCR plus 1. Or you can divide numerator and denominator by SCR. 1 by 3 plus SCR plus 1 by SCR. Now you can put SC equal to J omega. So what is beta? It is 1 by 3 plus J omega RC minus 1 by omega RC. 1 by J is minus J. This is beta. Am I right? So what is the last step? Step 3. A beta should be equal to 1. Or A is equal to 1 by beta. A beta is 1 or A equal to 1 by beta. 1 plus Rf by R. is A. 1 by beta is 3 plus J omega RC minus 1 by omega RC. Am I right? Now, equate real and imaginary parts. If you equate imaginary terms on both sides, 0 equal to omega RC minus 1 by omega RC, or omega square is 1 by R square C square, omega is 1 by RC, or F is 1 by 2 pi RC. This is the frequency of oscillations. What happens if we equate real parts on both sides? If we equate real parts, 1 plus RF by R is 3. Then RF equal to 2R. So if RF is any other value other than 2R, you will not get oscillations, right? So the condition for sustained oscillations is RF should be 2R. What is the frequency of oscillation? F equal to 1 by 2 pi RC. Okay. Is my voice clear? It seems there is some background sound is coming. Is that so? Is my voice clear? Okay. Now, yesterday I told you at a particular frequency, what is an oscillator? Basically, an oscillator is a frequency selective circuit. An oscillator is a frequency selective circuit, right? It is going to select only one frequency from noise. But how do we know it is going to select only 1 by omega equal to 1 by RC? What about all other frequencies from noise? Those frequencies, all other frequencies from noise, are going to be added as harmonics to this fundamental. So this is the only signal that is going to burst out, and all other frequencies from noise are going to be added to this as harmonics, and the spectral purity is 80 dB below. What do you mean by 80 dB below? If your fundamental is 1, all the other harmonics added up will be 1 by 10 power 4. So it will be like 0.00001 will be all other frequencies from noise which are going to get added up. But if you take a triangular wave and if you connect a diode and try to clip it, what will happen? Suppose I try a triangular wave. How are we going to generate sine wave? To generate sine wave, what is the other name for sinusoidal oscillator? it is a DC to AC converter. It is a DC to AC converter. So we need sine waves in our day-to-day life. I told you. Suppose you want to build an inverter circuit. So how will you build an inverter circuit? Like Amir Khan in 3 Idiots, is it not? So we connect. He connects a 12-volt car battery. He gives it to an amplifier which has got some RC network here, RC network, and the frequency of oscillation. If it is an what you call a Wien-Bridge oscillator, or if it is RC phase shift oscillator, then the frequency of oscillation will be 1 by 2 pi RC root 6. This we will adjust it to 50 hertz, because what is the power line frequency in our house? 50 hertz. So when you switch on the car battery, you are going to get 50 hertz sine wave here. It is a DC to AC converter. This we will give it to step-up transformer. Now this we are going to step it up to 230 volts, 50 hertz. So suddenly when power goes off, what will you do? You will switch on the power supply here. You're going to get 230 volts, 50 hertz, and this is used for fans and tube lights. Is it not? Your television sets and all that stuff, right? So if power goes off, we need sine wave in our day-to-day life. So this is intentionally. Are you getting? Sine waves are very, very good in this topic, because we are going to have them intentionally, right? We want sine waves. We want sine waves, right? Without sine wave, we cannot have fans and tube lights working in our house, right? Okay. So oscillator is a frequency selective circuit, and oscillator is a DC to AC converter. So if you do this with an RC phase shift oscillator or a Wien-Bridge oscillator, you will get very, very pure signal. But what is the other way of getting sine wave? The other way of getting sine wave is you can take a triangular wave. Some manufacturers, they will cheat you, is it not? If you see in certain colleges, they have a single circuit board, and if you open there, you will find that the first stage will be a square one, the next stage is a triangular, but the triangular wave is given to a clipper circuit, and the diode will clip this portion, and if you see in time domain, it will almost resemble as sine. But these poor college people, they don't know, is it not? They'll think, a nice sine wave has come in time domain. But if you give this to a spectrum analyzer, you will realize that the spectral purity is not even 20 dB below. Lot of harmonics will be there on this. So never ever take a triangular wave and convert it into sine, right? You should never do it. Sinusoidal are separate topic. For building a sinusoidal oscillation, you need at least 2 RC networks and 1 LC network. You have to connect it to an amplifier, make the loop gain 1, right? Wien-Bridge oscillators, RC phase shift oscillators, all these sinusoidal oscillators, they will give you very, very pure signal. But you should never design a sinusoidal oscillator from a triangular circuit, because you will have a lot of harmonic distortion in it, right? Okay. Yeah. Now, to start oscillations, I told you to start oscillations, your loop gain A beta should be initially greater than 1. That is when the noise is going to develop with more gain. But after some time, you have to make A beta equal to 1 to sustain oscillations, because A will exactly be equal to 1 by beta. If the RC network attenuates a signal by 1 by 5, you have to connect an amplifier equal to 5. If your RC network attenuates a signal by 1 by 29, you have to connect an amplifier equal to 29. Is it not? So this is fine. This is the Bar-Cousins criteria. No problem. But how are you going to achieve this? To achieve this, I told you, in lab, we have to do it manually. Is it not? You have to do it manually. But can we do it automatically? Can we do it automatically? And who is the person who did this automatically is, there's a guy called Hewlett, right? You know, Hewlett and Packard, they They started a company, right? With the toss of a coin, they have decided whose name should come first. Hewlett won the toss, and that is why the company is called Hewlett Packard, or in short, we call it HP, is it not? So HP is a world leader today in a lot of things, laptops and a lot of stuff. But how did HP started? HP started with a simple Wien-Bridge oscillator, right? Until that point, all the oscillators in the market had harmonic distortion. But Hewlett was a man who did this automatically. The loop gain greater than 1 and then loop gain equal to 1. And he got an order of around 1,000 pieces from Walt Disney Movies. So, that's how the company HP started. So, what was the idea? Hewlett played a very simple trick. The trick is, of course, he did it with vacuum tubes, but I'm drawing the op-amp version of it. Suppose you have an op-amp circuit, and here there is an RC network, right, for the Wien-Bridge oscillator. Now, Hewlett put an incandescent bulb here, an incandescent bulb. Now, what is the property of an incandescent bulb? The property of a bulb is, if the bulb is in cold state, the resistance is going to be less. Suppose this is RF, RF is 2R, RF is going to be 2R. Suppose this is 0.9R and this is 0.1R. Okay, so I'm having RF equal to 2R here, and this should be R, is it not, in the Wien-Bridge oscillator. Now, the bulb, if it is in cold state, it is going to be less than 0.1R. It is going to be less than 0.1R. The resistance will be less. Or overall, you can take it R, right? Overall, this is going to be R, for example. If the bulb is in cold state, its resistance is less. If the resistance is less, then what is the gain of the amplifier? The gain is going to be 1 plus RF by R. RF by R. So if RF is less or R is less, the gain is 1 plus RF by R. The gain will be more. So when you switch on, the gain is more, and the oscillation, there is a less attenuation here in this path. There is more gain in this path. So naturally the oscillations will grow. But once the bulb gets heated up, what will happen if the bulb gets heated up? The resistance will increase. That is a property of a bulb. So when the resistance increases, naturally the gain is going to be less. When the gain is less, you will adjust the gain, loop gain equal to 1 in heated state. See, it's something like this. To do one thing, first connect the bulb, don't do anything. Connect the bulb, don't do anything. Wait for some time. When you wait for some time, naturally the bulb will get heated up, right? When the bulb gets heated up, you adjust this resistor in such a fashion that the oscillations will get sustained. The oscillations will get sustained first time in the heated state. And then switch it off, have a cup of coffee and come and then switch on. When you switch on, this time the bulb will be in cold state after some time. In cold state, the gain is what? More, because the resistance is less. Automatically, the waveform is going to start like this. Once it starts, after some time the bulb will get heated up. No? Once it gets heated up, the oscillations will get sustained because you adjusted for A beta equal to 1. So your job is to adjust for A beta equal to 1. Automatically here, A beta will be greater than 1. Why it will be greater than 1? Because that is a property of the bulb. Any bulb, any incandescent bulb in cold state, its resistance is going to be less. So naturally the gain will be more. So your job is to adjust loop gain equal to 1 in what state? Heated state. So the moment they design a circuit, they used to connect a bulb, wait for some time, let it get heated up, adjust it for loop gain 1, and put the potentiometer, put glue, araldite, whatever you want, fix the resistance and sell it. In the market, what that person will do, who will buy, the bulb initially will be in cold state, you'll switch on. Once you switch on, because of the cold state, loop gain will be greater. Slowly, oscillation will start. After that, loop gain will be equal to 1. Otherwise, who used to do this in lab? Students will do in college, yes or no? They will decrease, increase, decrease, increase, they will do. Instead, automatically the bulb is going to do that. This is what is the first product released by HP. And I don't remember if you see their website, this is a celebrated circuit, some HP 200A or something. No, I don't exactly remember the number. It's called HP 200A something, right? See, Hewlett was very clever. Oh my God, what happened? How can I remove this? Okay. So Hewlett is very clever. His first product, he released HP 200A something. That means as if he doesn't want to know, he don't want people to know that this is a startup company. So he didn't had even an office. So he and his girlfriend has to paint all the Wien-Bridge oscillator in their garage. So anyways, that's how HP started. But see, look at the name of the product, HP 200A, as if 200 products are already released, and A is an upgradation of that product. Now, he didn't even have an office, but the number which he kept for a Wien-Bridge oscillator is HP 200A, isn't it? Very clever man. It seems he also had an MBA from Stanford, right? So very clever. He didn't want people to know it's a startup. Fine. Whatever it is, if somebody asks you how to solve the Barkhausen problem of loop gain greater than 1 first and then equal to 1, don't tell all this story, right? You just tell him that put an incandescent bulb. That will solve the problem, because an incandescent bulb resistance will be less. So the gain is more. So automatically the Barkhausen problem will be solved, because Barkhausen will tell you how to sustain oscillations. It will not tell you how to start oscillations, right? To start oscillations, loop gain should be greater than 1. So if you want to maintain loop gain greater than 1, then some arrangement like this has to be there. Okay. Whatever it is, fine. So let me make a note of this note. RC phase shift oscillator is a fixed audio frequency oscillator. Whereas Wien-Bridge oscillator is a variable audio frequency oscillator. For high frequency of oscillations, we go for wideband amplifiers with LC network. So when in the Wien-Bridge oscillator, see here, in the Wien-Bridge oscillator, the frequency of oscillation is 1 by 2 pi RC. But you can as well make this as F equal to 1 by 2 pi root R1, R2, C1, C2 also, right? You can instead of RC, RC, I have taken RC, RC for simplicity. You can take R1, C1, R2, C2 also. Then the frequency of oscillation will be F equal to 1 by 2 pi root R1, R2, C1, C2. So what do you mean by that? By adjusting R1 or by adjusting R2 or by adjusting C, you can adjust the frequency. In fact, the capacitance they used to change in old radios. If you see the old radios, the capacitors are ganged. By adjusting the capacitance value, you can tune it to a new station. Are you getting? So you can, a Wien-Bridge oscillator frequency can be varied by adjusting R values or C values. But in RC phase shift oscillator, that arrangement is not there. All R should be same. All C should be same. Then only the loop gain will be equal to 1 at some frequency. That is why RC phase shift oscillator is called a fixed audio frequency oscillator, whereas Wien-Bridge oscillator is a variable audio frequency oscillator. Okay, RC phase shift oscillator. So how do you build an RC phase shift oscillator? So how many RC sections are needed? Now this is a buffer just to isolate the beta network with the amplifier. So we'll take V0 here, VF. So what is V0 by VF? This is an inverting amplifier. What is the gain? Minus RF by R or minus RF by R1. Minus RF by R1 is the gain. Minus indicates 180 degrees phase shift. 180 degrees. If that is so, then the beta network should give an additional 180 degrees. The beta network should give an additional 180. But how will the beta network gives an additional 180? You should not say each section will give 60, 60, 60. That is wrong. Each section, there is no word called each. When the network is already one network, it is a single network. A single network will have a single magnitude plot and a single phase plot. You cannot remove, you cannot isolate them. The whole network is a single network. So you should only say that it is going to give 180 degrees. That's it. But if you want 60, 60, 60, what you have to do is, after every section here, you have to connect a buffer. If you connect a buffer after every stage and isolate it, and at some frequency if it oscillates, definitely 60, 60, 60 will be there, right? If you want, I will make it 60, 60, 60 by changing the circuit. But this circuit is going to give you overall 180. Each section 60 is wrong. It is like when it is already one, how you can say each, is it not? So there is no word called each, right? When it is already one, right? If a single person comes to your house, how will you invite him? There's only one person, friend, he came to your house. How will you invite him? Will you say, each of you come inside? He's already one, is it not? So similarly, this whole section is one. When it is a single section, a single magnitude plot and a single phase plot will be there. You cannot use the word each section because you cannot isolate them. If you want to isolate them, then each network should experience high input resistance and low output resistance. You have to connect a buffer in between. Then you can use the word each. Then definitely each section will give 60, 60, 60, which I will prove if you want, right? Okay. So what is step one? A equal to V naught by Vf. This is going to be minus Rf by R1 or Rf by R1 at an angle 180 degrees. At an angle 180. What is beta? Beta equal to Vf by V naught. So V naught is input. Vf is output. So you can apply Kirchhoff's law here, right? Don't take one loop and make it whole cube, right? You have to take Kirchhoff's law. You cannot apply voltage division because same current will not flow here. So you have to take I1, I2, I3 and solve. When you find Vf by V naught, the transfer function will be of the form S cube C cube R cube by S cube C cube R cube plus 6 S square C square R square plus 5 SCR plus 1. So this will be the transfer function, right? You can put S equal to J omega. Step 3. A beta equal to 1. Right? What is A? Minus Rf by R1. What is beta? S cube C cube R cube. Put S equal to J omega. What do you get? S cube C cube R cube minus J omega cube C cube R cube by minus J omega cube C cube R cube minus 6 omega square C square R square plus J 5 omega RC plus 1. So it is Rf by R1 into J omega cube C cube R cube. This is the denominator. Now tell me, what happens if you equate real and imaginary parts? What are real parts in the left hand side? What are real parts in the right hand side? What are imaginary parts? Equate real. No real parts in the left hand side. Right hand side 1 minus 6 omega square C square R square. 1 by 6 is omega square C square R square. Omega is 1 by RC root 6 or F equal to 1 by 2 pi RC root 6. See, that is why these type of questions you don't find in the GATE exam. You'll find only in IES exam, right? Step 1, step 2, step 3. In GATE exam, last class, we have solved problems. Directly, beta is given. They ask you to find a relationship between R1 and R2 or RF and R. So what is that? You will simply do A beta equal to 1, right? So if you equate real parts, you'll get this. What happens if you equate imaginary parts? It is Rf by R1 into omega cube C cube R cube is 5 omega RC minus omega cube C cube R cube. So this is the imaginary terms. Divide the whole equation by omega RC. You'll get omega square C square R square 5 minus omega square C square R square. What is omega square C square R square here? What is omega square C square R square here? 1 by 6. So RF by R1 into 1 by 6 is 5 minus 1 by 6. 30 minus 1, 29. That is why RF should be 29 times R1. So if RF is any other value other than 29 R1, you will not get sustained oscillations, right? So finally, you have an amplifier and a beta network. The three sections are going to give you 1 by 29 at an angle 180. At an angle 180. But if RF is 29R, you will have an amplifier A equal to 29 at an angle 180. So what happens to the overall gain here, loop gain? 29 into 1 by 29 is 1. 180 plus 180 is 360. So A beta equal to 1 at an angle 360 degrees. This is what criteria? Bar-Cousins criteria. What is Bar-Cousins criteria? The product of A and beta should be equal to 1 at an angle 0 or 360 degrees. Is it not? This is the Bar-Cousins criteria. If RF is 29 R1, then naturally the gain is 29. Is it not? This is for RC phase shift. This is for RC phase shift. What about Wien bridge? We have already solved Wien bridge. In Wien bridge oscillator, the RC network is going to give you 1 by 3 at an angle 0. In Wien bridge oscillator, your RF is 2 times of R. So your amplifier A is going to be 3 at an angle 0. So what is A beta now? A beta is going to be 1 at an angle 0 or 360 degrees. Are you getting? This is called what criteria? Bar-Cousins criteria. Any oscillator is going to follow Bar-Cousins criteria. If the amplifier experiences a phase lag of say 180 degrees, the compensation should come from the beta network to give a phase lead of additional 180 degrees, such that the total angle will be 360 degrees. If the amplifier gives a phase lag or lead of 90 degrees, the beta network should give a phase lead. If that gives a phase lag, the beta should give a phase lead of again minus 90 or 90, such that the overall angle is going to be 0 or 360 degrees. So what is an oscillator? The third definition of oscillator, which I am going to give you, is an oscillator is a phase compensation circuit also. Phase compensation circuit. What that means? Any phase lag or lead experienced by the amplifier is compensated by the beta network such that the overall value is going to be 0 or 360 degrees. The overall value is going to be 0 or 360 degrees. So can you see RF by R1 is 1 by 6, 30 minus 1 is 29 by 6. 6 at left side, 6 right side are going to get cancelled. So there is no 6 now. RF should be equal to 29 times R1, right? Now, I mentioned that, yeah. In this, I mentioned initially the loop gain should be greater than 1, and after that, the loop gain will be equal to 1. Am I right? So initially, it should be greater, and after that, it should be equal. That is fine. Now, what is a guarantee that it will stay here only? What if some non-linearity creeps in the circuit, and if your V0 increases more than that value? If your V0 increases more than that value, then if V0 increases, your VF will increase, no? If VF increases, again your V0 will increase, and slowly it might go and hit plus VSAT and minus VSAT also. Then the output might become square wave, is it not? So what is the guarantee that the loop gain equal to 1 will be there? Some non-linearity creeps in the circuit. So already so many transistors, junction capacitors, yes or no? So a lot of linear stuff is there inside. By some action, right, non-linearity or something, we don't know, if the output increases more than that value, then in the next iteration, if it keeps on increasing, then it might become a square wave. It might hit plus VSAT, is it not, or minus VSAT. So we have to limit the amplitude. There is something called amplitude stabilization of oscillator. There is something called amplitude stabilization of oscillator. So now you can say, what is this, sir? The stabilization means it is only with negative feedback. Yes or no? With positive feedback, what stabilization can we expect, right? Negative feedback means if it increases beyond a certain value, then the next iteration it will decrease, and the decrease will further increase. So it will come back to the point where it has started. So the word stabilization doesn't fit for positive feedback. The stabilization is a word which will fit only for what feedback? Negative feedback. But even in oscillator, you need amplitude stabilization. You need amplitude stabilization. So how are you going to ensure amplitude stabilization in oscillators? Amplitude stabilization in oscillators. Amplitude stabilization in oscillators. So how are we going to stabilize the amplitude? For example, if I have a network like this, suppose this is 10K, 1K, and the beta is say 1 by 10. So what is V0 by VF? What is V0 by VF here? V0 by VF is going to be minus R2 by R1. So it is going to be 10 at an angle 180. 10 at an angle minus 10. What is minus 10? 10 at an angle 180. If the amplifier is 10 at an angle 180, the beta network is 1 by 10 at an angle 180. So it satisfies Bar-Khausen criteria. That is okay. Now, what happens if the waveform will try to increase beyond this value? beyond this value. If some non-linearity creeps increases, the increase will further increase. So then you're not going to have any stabilization. Then how are you going to ensure stabilization is? It seems that I told you negative feedback was introduced by a person called Stephen Black. So Stephen Black, after he presented the classic paper on negative feedback, he became so famous. He was invited in so many universities. They used to invite Stephen Black for a talk. It so happened that the Mr. Hewlett also attended, one of the conference or whatever talk, and he observed very carefully what is this negative feedback doing. Negative feedback means wherever you want stabilization, there has to be some sort of negative feedback. Without negative feedback, you cannot get. What is negative feedback? Increase should decrease and the decrease should increase. But here what is happening? Why is this positive feedback? If V0 increases, Vf will increase. If Vf increases, V0 will increase. So this is what feedback? Positive feedback. So with this positive feedback, you cannot get amplitude stabilization. So how I have to cleverly implement negative feedback in a positive feedback system, right? I repeat, in order to get amplitude stabilization, we have to implement what feedback? Negative feedback in this positive feedback system, right? How are we going to do that, right? That is a challenge, design challenge. So that you can do with some non-linear device like this, with some Zener like this. Now what happens if I connect? This is of course a gate problem. Gate problem in the sense of 4 options were given. The examiner said, what is the purpose of Zener there, right? The purpose of Zener, 4 options were given: amplitude stabilization, frequency stabilization, like that. The right answer is amplitude stabilization, right? But how a Zener is going to stabilize the amplitude in an oscillator, right? With the help of this nonlinear device, how we are going to do amplitude stabilization. Now please see here, take Vz some value. Suppose Vz is 6.3. Your Vd on is 0.7. So what is the total drop? 7 volts, right? This is ground for AC analysis. This is 0. This is 0 here. Your complete V0 is here. Your complete V0 is here. So now tell me, what happens when the Zener is off? When the Zener is off, what is the slope M1? We have already drawn the characteristics now. If the Zener is off, the slope M1 is going to be minus 10k by 1k. It is minus 10. What happens when the Zener is on? When the Zener is on, M2 is going to be minus 90k parallel with 10k. It is 900, it's almost minus 9, right? So when the Zener is on, the slope is minus 9. If the Zener is off, the slope is minus 10. Are you getting? So we have already drawn the characteristic. Let me explain this now. Suppose if V0 increases due to some nonlinearity, suppose V0 has increased and it has crossed 7 volts, what will happen? If Zener is not there, if V0 has crossed 7 volt, next iteration it will further increase, V0 will further increase, it might reach saturation. But now what happens if Zener is there? If V0 increases, then the Zener will get on. If Zener gets on, the gain will reduce. What is the gain now? The new gain? The gain is going to be minus 9. Gain will reduce. If gain reduces, what will happen? The next iteration, V0 will decrease. So if V0 increases, suppose here, look at my hand. Suppose V0 increases more than 7. When it increases more than 7, the Zener gets on. This signal V0 has to be passed again to Vf. And again through Vf, you have to V0. So what will happen to the next iteration? The next iteration, the gain will not be 10. The gain is going to be only 9. So what will happen to the next iteration? The moment the Zener is on, V0 increases, Vf, and then from Vf by V0, the gain is only minus 9, not minus 10. So the gain is going to decrease and your V0 falls down. So can you see the V0 was increasing, the next iteration V0 decreased. Okay. If V0 decreases, what will happen? If V0 decreases, then naturally the Zener is off. If Zener is off, the gain will increase. If the gain increases, naturally V0 will increase. So what do you understand by this feedback? V0 increase, V0 decrease here. This is a negative feedback system. Negative feedback is going to stabilize the amplitude. Negative feedback stabilizes amplitude. So we can confidently say that see, all this happens in a microsecond time, and after that the Zener will sleep. Zener is always sleeping, right? It is always off. But when Zener will get on, if as long as the output voltage is less than 7, Zener has no job, right? Zener will always stop. The moment it touches 7, the Zener will get on. Next iteration, Zener will decrease again, and again Zener will stop. So Zener is always off. Zener will get on only for that small instant where the output crosses how many volts? 7 volts. Are you getting? So this is a clever way of implementing. And the gate examiner said, what is the purpose of a Zener diode? What is the purpose of Zener diode? The Zener diode is used for amplitude stabilization. So with the help of Zener diode and the resistor with the op-amp connected in the feedback, definitely you're going to stabilize the amplitude. So this is a very clever way of implementing it, right? So what is the gain when Zener is off? The gain when Zener is off is 10. But the gain when Zener is on is 9. Do you remember we have drawn the transfer characteristics for this? Yes or no? What is the transfer characteristic between Vf and V0? Vf here, V0 here, right? So you are going to get a gain, a slope of minus 10 until your output V0 touches 7 volts or minus 7. After this point, the slope is going to decrease, not to 10, but to minus 9, right? So this is the transfer characteristics of the amplifier. Yeah, if you want each section 60, I told you we can change the RC phase shift oscillator. In the RC phase shift oscillator, each section, there is no word called each. The whole network together will give 180, I told you. But if you want 60 degrees, then what we can do, we can slightly change the RC phase shift oscillator. RC phase shift. Where each section, each RC section gives 60 degrees. Each RC section gives 60. If you want that, it's not only a buffer. You can put a common collector amplifier or a common drain amplifier also to isolate. But it should have high input resistance and low output resistance. Now the whole section is going to give you 180. This is 180, and 180 is distributed by 3 networks. Each network gives 60, 60, 60. So what is 60 degrees? 60 degrees is 180 by 3, 2 pi by 3, is it not? Pi by 3. How much is pi? 2 pi is 360. Yeah. So let me prove 60 now. Let me prove 60. This is V0, this is VF. VF. This is also VF. We can have Vx here, Vx, Vy like that. So what is loop gain here? What is loop gain? You have to go around the loop. The amplifier gain A is nothing but minus RF by R1. A is minus RF by R1. What about beta network? What about beta network? Beta equal to Vf by V0. You can write this as Vf by Vy into Vy by Vx into Vx by V0. But all are same only. All are same. It is equal to your Vx by V0 whole cube. Because this section, this section, this section all are same, right? So what is voltage division here? V0 by Vx or Vx by V0? It is R by R plus 1 by SC. R by R plus 1 by SC whole cube. So this is SCR by 1 plus SCR whole cube. So what is loop gain? Loop gain is minus RF by R1 into SCR by 1 plus SCR whole cube. Whole cube is 1, right? So you can do A plus B whole cube formula. If you do, then you will realize that your RF is 8R1 you will get, and the frequency of oscillation is 1 by RC root 3 you will get, not root 6, right? So at this frequency you are going to get 60 degrees. If you want, you can cross check what is the phase shift of each section. Phase shift of each section. Tell me, what is the phase shift of SCR by 1 plus SCR? SCR, what is the phi for this? SCR means 90 minus tan inverse omega CR. So 90 minus tan inverse omega is 1 by RC root 3 into RC. RC gets cancelled. So what is tan inverse 1 by root 3? 90 minus tan inverse 1 by root 3. What is 90 minus tan inverse 1 by root 3? (90 minus tan inverse 1 by root 3 is going to be 60, is it not? Right? So you have to do Vx by V0. What is Vx by V0? Voltage division. This is R capacitor. Because same current is flowing, there is no need of Kirchhoff's law. In the previous case, you have to write Kirchhoff's law, right? So Vx by V naught is going to be R by R plus 1 by S. But please don't apply voltage division rule in this. In this, what you have to do? How will you find the transfer function in this? Yeah. In this, how will you find the transfer function? You have to take nodes here. There is a node Vx, there is a node Vy, and here there is a node Vf. And you have to apply Kirchhoff's law. Entering current equal to leaving. And here entering equal to leaving. Are you getting? So then you have to eliminate Vx and Vy. But can you apply voltage division rule here? You should not apply because same current will not flow. But there, I have isolated with a buffer. Then I can easily apply voltage division rule. There you have to apply what law? Kirchhoff's law. Here simply voltage division you can apply. If you apply, you will get this R by R plus 1 by SC, and then SCR by 1 plus SCR. 3 sections are there. This into this into this is going to be all the 3 sections you are going to multiply. So naturally SCR by 1 plus SCR whole cube. Don't apply voltage division if they are together because that is a single network. It is all loaded. You have to apply Kirchhoff's law by taking the nodes, right? Okay. So each section is going to give you 60 degrees, right? Do you remember A plus B whole cube formula? If you remember A plus B whole cube, it is okay. Or you can do one thing. You can take one section and make it 60. Is it not? Like that also you can do. Because to all the overall, it is going to be 0 or 360 degrees. SCR by 1 plus SCR. So your wish, how you want to do it. You can do, if you remember A plus B whole cube formula, A cube plus B cube plus 3A square B plus 3AB square. You can solve it, right? Do you remember A plus B whole cube formula or you want me to solve? If you want me to solve also, I will solve. Minus RF by R1 into S cube C cube R cube equal to A cube plus B cube plus 3A square B plus 3AB square. Right. So now you can solve it. It's not a big thing, right? Put S equal to J omega and solve, right? Do you remember A plus B whole cube formula or not? Yes or no, right? Okay. General configuration of LC oscillator. general configuration of LC oscillator. So to build an LC oscillator, you need an amplifier and a tank circuit like this. Tank circuit. A tank circuit like this. So this is a general configuration of any LC oscillator. So you have V0 here, VF. So if there is some current I, the same current I here. So what is I? I is equal to V0 minus 0 by Z2. The same I is 0 minus VF by Z1. So what is beta? VF by V0. It is going to be minus Z1 by Z2 or Z1 by Z2 at an angle 180. This is beta. What is amplifier A? Gain is minus K. Gain is minus K. And the last step is A beta should be equal to 1. A beta should be 1, right? So this is what we have to do. But how do you find the frequency of oscillation? For finding the frequency of oscillation, assume the beta network is isolated with amplifier. Assume the beta network is isolated with an amplifier. Then this is the beta network. Now just tell me, if you have a single loop, which is easy, KCL is easy or KVL is easy? If you want, we can apply KCL also. But whenever the network looks stretched, single loop, it is always better you apply KVL. So what is KVL? The current flowing in the loop into Z3 plus the current flowing in the loop to Z2 plus Z1 is 0. So the current into Z3 plus current into Z2 plus current into Z1. So Z1 plus Z2 plus Z3 equal to 0. This is very, very important. For any LC oscillator, Z1 plus Z2 plus Z3 equal to 0. If you do, you can find the frequency of oscillations. If you want to find the frequency of oscillation, then please use the condition Z1 plus Z2 plus Z3 equal to 0. Now, if Z1 and Z2 are inductors, Z1 and Z2 are inductors and Z3 is a capacitor. If Z1 and Z2 are inductors and Z3 is a capacitor, then it is called a Hartley oscillator. If Z1 and Z2 are capacitors and Z3 is an inductor, then it is a Colpitts oscillator. Am I right? Hartley oscillator, you need an inverting amplifier. And this inverting amplifier should be connected to, if you want, you can put a buffer here. to isolate the beta network. Here you have Z3, which is a capacitor. Okay, so this is Z1, Z2, Z3. So tell me what is A. First step is A. V0 by Vf, which is minus Rf by R1. Second step, beta, Vf by V0. What is Vf by V0? We have already done here. Minus Z1 by Z2. Who is Z1 inductor? SL1 by SL2, which is minus L1 by L2. And the last step is A beta should be 1. A beta should be 1. That means minus Rf by R1 into minus L1 by L2 should be 1. So what is Rf by R1? Equal to L2 by L1. This is the condition for oscillations. Rf by R1 is L2 by L1. Alright? But how do you get frequency of oscillations? How do you get frequency of oscillations? Z1 plus Z2 plus Z3 equal to 0. You have to apply this formula. Z1, SL1 plus SL2 plus 1 by SC is 0. You can take S out. L1 plus L2 plus 1 by S square C is 0. Put SC equal to J omega. J square is minus omega C square, right? Put SC equal to J omega. So what is omega? It is 1 by root LC or L equivalent into C, where L equivalent is L1 plus L2. Where L equivalent is L1 plus L2, right? Similarly, draw a Colpitts oscillator. In the place of inductor, please connect a capacitor. 2 capacitors and 1 inductor. You will have a Colpitts oscillator. So please draw a Colpitts oscillator also. Draw a Colpitts oscillator. So similarly, A is V naught by Vf, which is minus Rf by R1. Beta Vf by V naught, which is minus Z1 by Z2. This is Z1 here, Z2. It is minus 1 by SC1 by 1 by SC2, minus C2 by C1. The last step is A beta should be 1. A is minus Rf by R1. Beta is minus C2 by C1 is 1. So Rf by R1 is going to be C1 by C2. And how do you get frequency of oscillations? For frequency of oscillation, you can do Z1 plus Z2 plus Z3 equal to 0. See, these standard oscillators will never come in exam, right? What is the oscillator that he will give you? He will give you an oscillator which you have not seen till now. A simple network will be there, like how we have done last class problems. You have to make the loop gain 1 for that circuit, and that is going to give you the frequency of oscillation or the condition for oscillations, right? Standard oscillators are seldom asked in GATE exam, right? So it is 1 by Z1, 1 by Z2 plus Z3. Put S equal to J omega. Omega is 1 by root LC. In the previous case also omega is 1 by root LC. But what is L? L is L1 plus L2. In this case, C is C1 C2 by C1 plus C2. In this case, C is C1 C2 by C1 plus C2. Okay. So like that, any oscillator, same, the method is similar, right? There is no change in the model. Every oscillator, same method. Start at one point, come back to the same point. V naught be Vf into Vf by V naught. If there are more nodes, Vx, Vy, Vz, Vy by Vx into Vz by Vy into Vx by Vz. So complete loop you have to cover and make the loop gain equal to 1. Like that, any oscillator problem can be solved, right? Any oscillator problem, there is only tomorrow if you are given a new oscillator which you have not seen in the exam, same thing you have to do, right? So like that, there are hundreds of oscillators, right? Standard oscillators are this RC phase shift Wien bridge, but it doesn't mean that these are the only oscillators available. So many, you can also design an oscillator, right? But the rule is it should follow the loop gain equal to 1 at a particular frequency where it has to simulate an S square term. So at least two RC networks, at least one LC should be there, right? Now, there is one more oscillator. If I remember, it's called three-phase oscillator. This oscillator is popular to build a control system which will run in step with the three-phase power system. The three-phase power system, what is the angle between any two phases in a three-phase power system? 120 degrees. So this oscillator will also give 120 plus 120 plus 120. It will give 360 degrees phase shift. Total angle is 360 degrees. So a three-phase oscillator is built with a simple low-pass filter. We have seen this low-pass filter so many times. With this help of a low-pass filter, we can build an oscillator. Do you remember this low-pass filter we have done? RF, R1 and C. Am I right? So this is a standard low-pass filter we have already done. So such filters you can connect 3. Then it becomes an oscillator. Each section should give 120, 120, 120. Therefore, it is going to become 360. Now, how do I know that it will give 120, 120, 120? I don't know it will give 120, 120. But I definitely know that it will give some theta. It will give some, because capacitor is there, it is going to give you some theta. See, the first section gives A at an angle theta. Second also will give A at an angle theta. Third also will give A at an angle theta for a particular frequency. And why same angle? Because same network is there. If this has to be an oscillator, your A into A into A cube at an angle 3 theta should be 1 at an angle 360. A cube at an angle 3 theta should be 1 at an angle 360. So, if 3 theta is 360, theta should be 120. Yes or no? It cannot be anything. X plus X plus X is 360. That means X has to be 120. 120 plus 120 plus 120 only will make 360 degrees phase shift. Right? So what is the frequency of such oscillations? What is the frequency of oscillations? Suppose this is V0. V0. If this is V0, this is also V0, right? V0 or Vx you can take. This is Vx. This is also Vx. This is Vy. This is Vz. So what is loop gain? What is loop gain here? Tell me. Loop gain equal to what? That means Vy by Vx into Vz by Vy into Vx by Vz equal to 1. But all are similar, is it not? All are similar. We can say Vy by Vx whole cube equal to 1. Vy by Vx whole cube equal to 1. But what is the transfer function of a low pass filter? We have already seen. It is minus Rf parallel with 1 by Sc by R or R1 whole cube. It is going to be minus Rf by R1 by 1 plus Sc Rf whole cube. So there are two ways of doing it. One simple way is take this section and equate it to 1 at an angle 120. Take this section, single section, and make it 1 at an angle 120. Or if you have time, you can do A plus B whole cube and equate it, right? Because single section will give 120. All the 3 sections are going to give you 360. So your wish. So small simple method, you do it, right? The hard method of expanding, I will do it, right? Simple method, I'm giving it to you. Take this single section and equate it to 1 at an angle 120. Hard method is we have to apply a plus b whole cube and do for all the 3 sections. Right? All the 3 sections, let me do it. Minus rf by r1 whole cube equal to a plus b whole cube, a cube plus b cube plus 3a square b plus 3a b square, 3a b square. Put s equal to j omega. Put s equal to j omega. Okay, so have you finished single stage 1 at an angle 120? By this time you would have finished the answer, right? What is equate imaginary terms? 0 equal to 3 omega CRF minus omega cube C cube RF cube. Divide the whole equation by omega CRF, omega square C square RF square. So what is omega? It is root 3 by CRF. Omega is root 3 by CRF, or F is root 3 by 2 pi CRF. Equate real parts on both sides. Minus RF by R1 whole cube. Real part 1 minus 3 omega square C square RF square. Omega square C square RF square here is 3. It is 1 minus 3 into 3. 3 3s are 9. 1 minus 9 minus 8. RF by R1 whole cube. How will I write 8, sir? Can I write 8 as 2 cube? That means RF should be 2 times of R1. So this is a lengthy way of doing it, right? What is the simple way? Take this single section minus RF by R1 by 1 plus SCRF and equate it to 1 at an angle 120. What is 120? 2 pi by 3. No? So what is the phase of each stage? You can check. What is the phase of each stage for this transfer function? Phase of each stage. Each stage for minus RF by R1 by 1 plus SCRF. Tell me what is the phase for that? Minus is there, so I will write 180 minus tan inverse omega CRF. It is 180 minus tan inverse. What is omega CRF? Omega CRF, omega CRF. Root 3, no? Omega CRF square is 3. Omega CRF is root 3. Please tell me what is tan inverse root 3? 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 180 minus tan inverse root 3. It is going to be how much? 120 degrees, is it not? So each section is going to give you 120, right? If you go by the length. Or you can take a single section and equate it to 1 at an angle 120, you'll get the same answer. See, the problem is why oscillators are not asked in GATE much. Because it's lengthy, is it not? 2 marks for 2 marks if a person cannot keep on doing. And moreover, oscillators are not designed for GATE exam. Oscillators are designed in electronics. They are not designed because you have to write GATE exam, is it not? So that is why GATE examiner will not choose much oscillators. If a simple oscillator is there, he will give. But RC phase shift oscillator, so many derivation and all, for 2 marks you cannot expect, is it not? Because oscillators are not designed for GATE exam. So oscillators are already there in books even before GATE exam. So and they look like this only. There are only 3 stages. One is the amplifier network will be there, then beta network will be there, then you have to combine them. But sometimes you'll have 3 stage like that. So it is laborious. You have to do it, right? So that is why GATE examiner will not give such lengthy oscillators, right? It's okay because oscillator topic is there. You can always see. See how he has given in the question, right? You would have seen amplifier network is asking a relation between R2 and R1. Beta is already given. Beta is 1 by 6 at an angle 0, he said. RF is R2 is 5 times R1. Last time we have done. That is a gate question. And in oscillators, one more question he has asked where he has given a diode in the feedback and he said what for it is used, amplitude stabilization. So like that, simple questions will be asked, right? Maybe Colpitts is also simple. Someday you can expect. See, in all these circuits, whenever beta network is there, to isolate the beta network with amplifier, so that I can do step 1, step 2 separately, I put a buffer. Don't worry if there is a buffer. What is the gain of a buffer? 1, isn't it? A buffer will always isolate the amplifier with the beta network. See, every op amp, every IC, at least 2 op amps will be there. 1 op amp I am using for this is not a big thing. Is it? I am not wasting my money in this. So any IC you buy, at least 2 op amp, 2 op amps, 4 op amps will be there. 1 op amp you can use it for buffer to isolate the beta network, right? Is my A plus B whole cube correct? It has to be correct, otherwise you will not get 120 here, isn't that? Okay. Now there is one more oscillator called VCO. What is VCO? VCO stands for voltage controlled oscillator. So in communications, you would have studied about what you call a PLL, something called a PLL, phase lock loop. So in a phase lock loop, we will always use a VCO. This is a separate type of oscillator. But by changing voltage, you can change the frequency. By changing voltage, we can change the frequency. So it is a voltage controlled oscillator. In all the previous cases, the frequency is decided by only RC components. But here, it is not just RC. We will change the frequency by changing the voltage. As voltage changes, the frequency also will change, right? It is called a voltage controlled oscillator. So how are you going to build? So many ways, like I said, but I'll draw one popular way of building a VCO. Okay, so this is a very, very popular VCO, a voltage controlled oscillator. Let us calculate the frequency and see how the frequency changes with the input voltage. Okay, we'll go step by step. See here. Suppose I applied V in here. V in, this is V in. What is the current drawn by op amp? 0. The current drawn by an op amp is 0. So what is the voltage across this 10K? This is going to be V in by 2. It is going to be how much? V in by 2 because of voltage division. But according to virtual ground, the voltage at non-inverting is equal to voltage at inverting. So this voltage should also be V in by 2. So V plus equal to V minus equal to V in by 2. V plus equal to V minus equal to V in by 2. Now, the second op amp, you can see this is some kind of a Schmitt trigger. So what is the Schmitt trigger operation? The output will either be at plus Vsat or minus Vsat. The output will either be at plus Vsat or minus Vsat. So what is plus Vsat for this op amp? Plus Vsat is plus 20. Minus Vsat is 0. Minus Vsat is 0. So plus 20 and 0. Right? So let us start. Case 1. Let V0 is at plus Vsat. Plus 20. Let V0 is at plus 20. Then if this is plus 20, what is Vg? Vg here. Vg is going to be 20 into 1K by 1K plus 1K. It is going to be 10 volts. It is going to be 10 volts. Now, if you give 10 volts to gate terminal, 10 volts to gate terminal, the MOSFET, is it going to be on or not? Yes. MOSFET is on. MOSFET is on. If MOSFET is on, then what is I1? I1 is going to be V in by 2 by V in by 2 by R, which is V in by 2R. So once the MOSFET is on, you can imagine a large VGS here. Your VDS is much, much smaller. You can neglect VDS. So I1 is V in by 2R. What is I2? What is I2? I2 equal to, what is I2 here? I2 equal to V in minus V in by 2 by 2R. It is going to be V in by 4R. V in by 4R is I2. I1 is there, I2 is there. Now what is I3? What is I3 by Kirchhoff's current law? The current that are entering is equal to the current leaving. I1 plus I3, let me see, is it? I2 plus I3 is I1. I2 plus I3 is I1. So we know I1 and I2. What is I3? I3 is going to be I1 minus I2 which is V in by 2R minus V in by 4R. This is again going to be V in by 4R. So I3 is V in by 4R. All right. Now what is this VC? What is the voltage across the capacitor VC? VC equal to 1 by C integral I dt. Current is constant, so I by C of t. It is V in by 4 RC into T. This is VC. But we know V01 minus V in by 2 is VC. V01 minus V in by 2 is VC. Therefore, V01 equal to V in by 2 plus VC. What is VC here? VC is V in by 4 RC. V in by 4 RC into T. So this is like Y equal to mx plus c. Mx plus c. What is the slope m? The slope m is going to be V in by 4 RC. The slope m is going to be V in by 4 RC. So what happens as the time progresses? As time progresses, if your output is at how many volt? 20 volt. If your output is at 20 volt, tell me what happens if your output is at 20 volt? Your output is at 20 volt. And your V01, what is V01? V01 is going to have a slope V in by 4 RC. V in by 4 RC is going to have a slope V in by 4 RC. Now what happens if your V01, if this V01 with a positive slope crosses VG? What happens if V01 crosses VG? If V01 crosses 10 volt, if V01 crosses VG, VG is how much? 10 volt, then what happens if this V01 crosses VG? Then your VD is negative, no? VD is negative. Then VD is negative. So V0 switches from where to where? 20 volt to 0 volt. V0 switches from 20 volt to 0 volt. So once it crosses 10, it is going to switch from 20 volt to 0 volt. Now, once V0 switches to 0 volt, what is case 2? This is case 1. You can see V0 is at 20 volt. V0 is at 20 volt. What happens when V0 is at 0 volt? Case 2. Let V0 is at 0 volt now. With 0 volt at output here, what is VG? What is VG if your output is 0? If your output is 0, VG is also equal to 0. Then the MOSFET is off. If the MOSFET is off, your I1 through MOSFET is going to be 0. Your I1 through MOSFET is going to be 0. Now, surprisingly, because I1 is not there, I2 and I3 both are same. Your I3 is exactly minus I2, is it not? Your I3 is exactly minus I2. I1 is 0, so I3 equal to minus I2. What is minus I2? What is I2 already? I2 is V in minus V in by 2 by 2R. It is going to be minus V in by 4R. Minus V in by 4R is I3. So what is your V01? V01 equal to I3 by C of T plus V in by 2. We have already seen this. So now the slope is going to be negative. V in by 4RC of t plus V in by 2. Previously, what was V01? Previous case, if you see V01, there is a positive sign. You can see V01 here. Here, there's a positive sign. Now, the same equation is got negative sign. The slope m equal to minus V in by 4RC. Minus V in by 4RC. So, happily, you're going to get same slope now. See how clever this circuit is. Can you see here, there is a 2R here and R here. Can you see 2R and R? What happens if the upper resistor is 2R and the lower resistor is R? You are having a slope of V in by 2 by R. That is going to be V in by 2R, this side. But once the MOSFET is off, V in minus of V in by 2 by 2R is again V in by 4R. The same I3 is minus I2. So the slope will still be same. The slope is going to be still same, right? But in second case, if your V01, this is 0 now, this is 0. If your V01 is less than 0, then what happens? If V01 goes less than Vg or less than 0, then V01, V0 switches from minus Vsat to plus Vsat, 0 volts to 20 volts. 0 volts to 20 volts. So once this voltage goes less, again you will switch to 20. Once you switch to 20, again you are going to have what ramp? Positive ramp. Once you cross 10, it will fall down. So this is a simple waveform, square or triangular. But what is the slope m here? The slope m, this is the time period t. Half of this is t by 2. So tell me, what is the slope here? Slope formula. Slope is going to be change of y by change of x. Change of y by change of x, that is equal to V in by 4RC. That is going to be, what is the slope here? V in by 4RC or minus V in by 4RC, whatever. So from here, what is t? What is t? T is going to be, what is t? T is going to be 10 2s are 20, 20 into 4, 80. Can I say 80? T is going to be 80 RC by V in. Or frequency is V in by 80 RC. So for the first time, the frequency is dependent on the voltage. That is why it is called a voltage controlled oscillator. It is called a voltage controlled oscillator. So you can take R and C some values. Let R equal to 10 kilo ohm. C is 1.25 nanofarad. C is 1.25, 10 power minus 9, that is 10 power 4. If you multiply with 80, your frequency F is going to be, round figure, I'm just trying to make it round, is going to be 1000 times of V in. Your frequency F is going to be 1000 times of V in for V in by 80 RC. So tell me, if my V in range is from 10 millivolts to 10 volt. So that is possible, is it not? My V in range is from 10 millivolt to 10 volt. Then what is my frequency range? 10 milli into 1000, right? Cancel. It's going to be 10 hertz to 10 kilohertz. So now I can change my frequency not by changing RC values. In the previous case, you keep on changing RC value, gang capacitor, change resistor. But VCO is beautiful. You just change the voltage, you are going to change the frequency. If your voltage is from 10 millivolt, then you get 10 hertz. If your voltage is 10 volt, you get 10 kilohertz. So as the voltage changes, your frequency will also change. So let me repeat this once again. All of you just observe. Can you see the cursor here, right? So first my V naught I assume to be 20. If V naught is 20, Vg is 10. If Vg is 10, Vg is 10 here, the MOSFET is on. If the MOSFET is on, what is the current? The current is V in by 2 by R. What is I2? V in minus V in by 2 by 2R. I3 is going to be I1 minus I2, and your I3 by C is the slope, where which is V in by 4RC. With that slope, your V01 is going to increase. In what direction? Positive slope. But as this voltage is going up and up and up, but here you have 10 volt. So what happens when this crosses 10? If this voltage crosses more than 10, then your VD becomes negative. If VD is negative, your output will switch from 20 volts to 0 volts. If it goes 0, now your VG will also be 0. If your VG is 0, then the MOSFET is going to be off. If MOSFET is off, your I3 and I2 both are same now, a single series circuit. Your I3 is minus I2. But what is the new slope for the capacitor to discharge, right? If the current has to flow in the opposite direction, it is V in minus V in by 2 by 2R. It is again V in by 4R. It is again V in by 4R. So the capacitor, now the slope is not positive. It is going to be negative slope, going to be negative. Once the voltage goes below 0, because this is at 0, if it goes below 0, this voltage, say minus 0.1 like that, then VD will again become positive. Your output will flip to 20 volts, and then the MOSFET is going to get on. So once the MOSFET gets on, you will have a positive slope again, right? So you'll have a positive, negative slope. But the slope is fixed, V in by 4RC. So what is the frequency? What is the frequency? For calculating frequency, we have to use the slope formula. What is the slope? Change of y is 10, change of x is t by 2, or y2 minus y1 by x2 minus x1. So 10 by t by 2 equal to v in by 4RC. So your t is going to be 80 RC by v in, or your frequency is going to be 1000 v. By changing v in, we can now change the frequency. Are you getting? So once the MOSFET is on, you can replace MOSFET with a closed switch. Once the MOSFET is on, you can replace MOSFET with a short circuit, because your VDS is very, very small. This is R, this is V in by 2. So what is the current I1? It is going to be V in by 2R. It's going to be V in by 2R, right? If the MOSFET is on, the switch is on. You can replace MOSFET with a short circuit for on. For off, you can replace MOSFET with open switch. If you replace MOSFET with open switch, then the current will become 0, right? So this is a voltage controlled oscillator, a voltage controlled oscillator. Okay, shall we take a break now? We'll take a break. When we come back, we will see other circuits. Fine. So where is this VCO used? So I was mentioning that this VCO is used for frequency tracking, right? So there are two ways of tracking the signal. One is amplitude tracking. Amplitude tracking is amplifier. The amplifier is going to track the amplitude and accordingly modulate the signal that is coming from the supply, right, with some gain. Amplitude tracking. The other one is frequency tracking. The frequency tracking is done by PLL. So how do you track the amplitudes? To track the amplitudes, we need, like we had an op amp, right? If you apply any signal V in, how the same signal appears at the inverting terminal? To track the same signal VF equal to V in or VS, your VF is equal to Vs by 1 plus 1 by A beta. So if your A beta is large, then your VF tracks Vs. This is called amplitude tracking. And an amplitude tracking is something we called it as virtual ground. What is virtual ground? The signal that is at the inverting terminal, which is coming from the supply, is almost going to be the same signal Vs, right? For this, we need a differential amplifier, a mixer, followed by a gain stage. And here we had resistors. This is beta. So if you apply some signal Vs here, your Vf is going to be Vs by 1 plus 1 by A beta. And how do you know that you have tracked the same amplitude at Vf here? Because your Vd is 0. Your Vd, the moment Vd becomes 0, it is understood that your Vs and Vf both are same, because Vd is Vs by 1 plus A beta. So if you want to build a good amplitude tracker or a good amplifier, your loop gain should be very high. So all this happens if loop gain is high. If loop gain is high, then the tracking will be perfect. Your Vf is almost equal to Vs. So once you track the same signal here, if you give 2 sin t, you're able to get 2 sin t here. This is going to be 4 sin t with some gain, right? Gain is going to be 2 times. 1 plus R2 by R1 times. But to track the amplitude, we need a mixer here, which is built with a difference amplifier and a gain stage, and then some resistors in feedback. So this is how we can track the amplitude. But how do you track the frequency? To track the frequency, you have some signal F1 here, F1. Here also you need something called a mixer, but this mixer happens to be a phase detector. This mixer happens to be what? A phase detector. And the phase detector output, like Vd of almost 0, if the phase detector output is 0, then we can say that for every single sine wave of F1, there is the same sine wave of F feedback here, Fr, right? Fr that is being, your Fr almost matches the F1. For only one cycle of Fin, there will be one and only one cycle of Fr, right? Such that the phase detector output is going to be 0. Here you can have a low pass filter or some gain stage here, gain stage. What happens if the loop gain is high? If the loop gain is high, the error Fr is almost going to become Fin, and Fd, the phase error, right? Phase error is going to become almost 0, right? And what should I put in the feedback? In the feedback, because the output is in voltage form, you can put a VCO. You can put a VCO. So what a VCO will do, whenever the voltage changes here, accordingly the frequency will change. So if loop gain is high, then your FR almost matches your Fin. FR almost matches your Fin. When both match, the phase difference is going to be 0. So what is phase and what is frequency here? What is phase and what is frequency? A simple analogy is, suppose if you would have seen the Grand Prix, the Formula One race, isn't it? In Formula One race, suppose all cars are moving round and round and round. Suddenly, if someone meets with an accident, what they will do? They will put a flag, and the flag shows that one of their friend has met with an accident, and they should all phase lock their speed with the car. The car is called pace car, right? The one which shows the flag. So everybody should lock their speed, phase lock with that car. So everybody will go with a normal speed until they remove, the debris, and they have to. Some medical people will come and they somehow have to save their friend, is it not, who has met with an accident. So how can they all go with the same speed? How every car is going with the same speed? The cars are going with the same speed because the difference between the cars, the phase difference between the cars is same. As long as you maintain same distance between the cars, it is understood that two cars are moving with the same speed. So even in so many movies you would have seen, two cars are going with high speed, but they are maintaining same distance between them. What do you mean by that? If the distance between the two cars are same and they are going with high speed, it is understood that both are going with the same speed. So similarly, for every one cycle, if you say that there is one and only one cycle at FR as compared with Fin, how do we know? The distance between the two, that means the phase error should be 0. That is why the phase detector should be there. Here, difference amplifier should be there. For amplitude tracking, you need a difference amplifier which will take the difference between the two amplitudes, and your VD should almost be 0. But the construction here is saying, in frequency tracking, the moment the phase difference is 0, the moment the distance between two cars, see, even we would have seen friends going on bikes, is it not? How two friends are going on two different bikes will go with the same speed. They know that they are going with the same speed because the distance between them is maintained constant. So similarly, as long as the phase error is 0 between the two, we can conclude that we have phase locked Fin with FR. We have phase locked Fin with FR. But of course, you can even do synthesis also. For example, what if I put a divide by n counter here? If I put a divide by n counter, then after division, you are getting FR equal to Fin. After division, you are getting FR equal to Fin. That means what is the voltage at this point? It is going to be n times of Fin. So once in GATE exam, they have given a PLL for 2 marks. Nothing. They have put a divide by n counter. They said, what is the voltage here? Because PLL design is very wide topic. There are people who spend a lifetime designing PLL, is it not? But general block diagram, you would have studied this even in communications, right? The general block diagram is this. One phase detector will be there, one low pass filter, gain stage. If the loop gain is very high, then you can phase lock these two frequencies, and then the phase error is 0. Here, what is 0 here? VD is 0. Your VS is almost equal to VF. So this is the amplitude tracking, but this is the frequency tracking. In frequency tracking, we will use a VCO. What is VCO? It is a voltage controlled oscillator. A voltage controlled oscillator is a VCO. Okay. So let us take a fresh topic here. The topic is feedback amplifiers. Or negative feedback amplifiers. Negative feedback. Feedback amplifiers or negative feedback. Negative feedback. Negative feedback. So what is the general configuration of negative feedback? General configuration of negative feedback. Just now we have seen, if you want to track the same amplitude at this terminal, you need a mixer, and there is beta here. Who is beta? Beta is designed with resistors. Resistors. Who is A? A can be a basic amplifier. A basic amplifier. And this basic amplifier can be with 1 stage, 2 stage, 3 stage, 4 stage, like that. Basic amplifier using BJT, MOSFET or op-amp. It is a basic amplifier using BJT or MOSFET or op-amp. So this is a mixer. And at this point you sample. This is a sampler. So at input you can give some signal excess. This is either voltage or current. So it is either in voltage form or in current form. And here you are going to get X naught, either voltage or current. So here you are going to have feedback, XF. So what is the gain with feedback? The gain with feedback is given as, in control system, this is G and H. A is G, beta is H. So what is the overall gain in negative feedback? G by 1 plus GH. A by 1 plus A beta. A by 1 plus A beta. A by 1 plus A beta. So in most of the amplifiers, A beta is going to be much greater than 1. In most of the amplifiers, A beta is far greater than 1. Then what is AF? AF is going to be A by A beta. 1 is very small. A is going to get cancelled. And the gain will depend only on beta, resistors. So what is the major advantage of negative feedback? So first class I told you advantage of negative feedback. What is the advantage of negative feedback? If A beta is large, then A is going to get cancelled. So the major advantage of negative feedback is if the loop gain is high, then the overall feedback gain, with feedback depends only on beta. depends only on beta or resistors. The open loop gain A is desensitized. The open loop gain A is desensitized. The overall feedback gain depends only on resistors or beta, right? Therefore, I told you the gain is predictable, stable, and accurate. So you are designing an amplifier which has got MOSFETs, BJTs, and op amps, but the gain is sensitive only to resistors. So what more do you want? Because BJT behavior, I told you, it's very bizarre, right? BJT is highly nonlinear. You cannot trust a BJT or MOSFET. They are nonlinear devices. So if the gain depends on nonlinearity, then finished. You cannot predict the gain. Morning one gain, afternoon another gain will be there. But now the gain is predictable, it is stable, it is accurate, because the gain is no longer going to depend on the forward transfer parameter A. It is going to depend only on the feedback resistance, right? So this is something we know. We have already seen this. I have discussed this so many times. But in this last topic, what we have, that means whatever we studied in the first topic, we are going to revisit in the last topic. In the first topic, I said an amplifier is decided not on the basis of gain, but on the basis of its sensing and driving capability, which is the input resistance and output resistance. Do you remember? An amplifier is decided based on its impedance matching, based on its input resistance and output resistance. If you want a voltage amplifier, then your input resistance should be high, your output resistance should be low. Your input resistance should be high, your output resistance should be low. So if you want high resistance and low resistance, what is the type of topology you are going to use? Type of topology. The type of topology is high means series topology at input, low means shunt topology you have to use. If you use series topology at input and shunt topology at output, then it is a voltage amplifier or voltage controlled voltage source. Controlled voltage source. What is a voltage controlled voltage source? It is voltage form at input and voltage form at output. So who is there? You are mixing voltage and you are sampling also voltage. So it is a voltage mixing and voltage sampling circuit. Voltage sampling circuit. Input side is voltage, output side is also voltage. Voltage control voltage source. If you want to build a current amplifier, high-low voltage amplifier, low-high is current amplifier. How you want to get low? Low means shunt topology you have to use. High means series topology you have to use. But what is the device? Your wish. Device can be BJT or MOSFET or op amp, because we know BJT can be current control current source, right? MOSFET can be voltage control current source, op amp can be voltage control voltage source. But design is going to take over the device. We are least bothered what device you are using. Sir, I am using BJT. Can I make a current amplifier? Yes. Sir, I am using MOSFET. Can I build a current amplifier? Yes. I am using a op amp. Can I build a current amplifier? Yes. How you can build current amplifier with 3 different devices? You have to blindly follow the topology. If you give shunt at input, series at output, the moment you give shunt, whatever input resistance BJT has, MOSFET has, that is going to come down by 1 plus A beta times. If you give shunt, 1 plus A beta times, the input resistance will fall. If you give series, 1 plus A beta times, the resistance is going to increase. then irrespective of any device, you can build a current amplifier. Yes or no? So who is a hero in this topic is not the device, it is the design. It is a design. So who is an amplifier? Is BJT an amplifier, MOSFET an amplifier, op-amp an amplifier? Because examiner will ask, no, for 2 marks, recognize the amplifier. So how will you recognize? Don't see BJT, don't see MOSFET, don't see op-amp, because an amplifier means design. Amplifier means topology. Amplifier means connection. How you connect amplifier and beta, how you connect two things, A and beta, will decide the type of amplifier. So if somebody says recognize the amplifier, it is a current amplifier, but it can be designed with BJT or MOSFET or op-amp, immaterial, as long as you give shunt series feedback. As long as you give series shunt feedback. First one, series shunt feedback. Whatever the device you are using, it doesn't matter. It is high input resistance, low output resistance. It's a voltage amplifier. That's all. If you want to build a transconductance amplifier, transconductance. Tell me, for transconductance, both should be high. Am I right? High input resistance and high output resistance. So this is a current controlled current source. This is a voltage controlled voltage source. Transconductance is what? Voltage controlled current source. Voltage control. What is voltage control? High. What is current source? High. Right? So it's a combination of first two sections. The first two amplifiers, if you combine them, is something like the transconductance. Voltage controlled current source. High and high. So you should give what topology here? What topology you have to give here? High means series. High means series. So the topology is going to be series topology. Series topology. So this is voltage mixing and current sampling. So this is current mixing and current sampling. What is the last amplifier? The last amplifier is trans resistance. In a trans resistance amplifier, what is the last category? High, low, low, high, 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 low, low. Low input resistance and low output resistance. So both low, it should be shunt topology at input and shunt topology at output. So finally, how many circuits we can build? How many circuits? I am having an op-amp BJT. With BJT, I can have 4 types of amplifiers. What are they? VCVS, CCCS, VCCS, and CCVS. All the 4 types. Similarly, MOSFET. I can have all the 4 types. VCVS, CCCS, VCCS, CCVS. Op-amp. I can have again 4 types. So now you'll realize that who is an amplifier now? Because with every device you are building that amplifier. Then what is an amplifier? How can you differentiate what sort of an amplifier it is? It is only by topology. If you give series shunt, then it is voltage amplifier with BJT. If you give shunt series, current amplifier. If you give series, transconductance. If you give shunt, trans resistance. The same with all other cases. So which is important in today's topic? Is it device or design? It is design. If you follow the type of topology, then you can build the type of amplifier irrespective of any device. Sir, what happened to device? Don't worry about device. Device got cancelled here. Can you see? The device is gone. The gain is dependent only to what? Resistors. The gain is not sensitive to the forward transfer parameter amplifier. The gain is sensitive only to the resistors one. So by changing the resistors, we can change the gain of the amplifier. By changing the resistors, we can change the gain of the amplifier, right? It is CCVS, current mixing voltage sampling. CCVS, current control voltage source, current mixing voltage sampling. Okay. So what is the first feedback? The first topology is series shunt. Series shunt, voltage control voltage source. Now, how do you connect two two-port networks in series? I'm having an amplifier and then the beta network. How do you connect two two-port networks in series? Series means whatever current enters, the same should leave. Whatever current enters, the same should leave. That is called a series connection. So, how do you connect two resistors in series? Two resistors in series. How do you connect two resistors in series? Whatever current enters, the same should leave. Whatever current enters, the same should leave, right? So you can connect like this. All right. If you connect like this, these two resistors are in series. So similarly, two-port networks, you can connect like this. How do you connect two resistors in shunt? I'm having a resistor here, another resistor. How do you connect two resistors in parallel? You can connect it like this. Whatever voltage you give, the same voltage is manifested here. So this is how you connect two resistors in parallel or shunt. And this network you will find in any networks book. In any networks book, they call this as H feedback. H feedback. If two two-port networks are connected in series shunt, their H parameters can be added. Shunt series, G parameters can be added. Series Z, shunt Y. So this you will study in networks, but I'm not going to use parameters. I'm just telling you this kind of a topology is also called H topology, H feedback. Series at input and shunt at output. In control systems, the same network is drawn like this, no? Here you will have G or A, and here you will have beta. Am I right? Now tell me, what is the relationship between VD, VS and VF? What is VD? Let me write the relation here. VD equal to VS minus VF. This minus indicates negative feedback. Am I right? This is the forward path. This is the feedback path. What is V naught? V naught is going to be A times of VD. And in this beta is, to the beta network, input is V naught, output is VF. What is beta? VF by V naught. Beta is VF by V naught. Am I right? And what is AF? Overall gain? A by 1 plus A beta. A by 1 plus A beta. Am I right? So all these equations we know. Right? I don't know what topic you call this in controls, block diagram, something like that, right? Fine. But how this connection here, series shunt topology, will also give you the same equations. Let's see. This is VF anyways. You can give me a KVL down the loop. KVL says that this is minus VS plus V in plus VF equal to 0. So what is V in? It is going to be VS minus VF. Can you see we got the same equation? So this minus indicates negative feedback. So if somebody asks you, sir, how do we know whether this is positive feedback or negative feedback? You simply follow the topology, that's all. Two-port will take care. If you follow the topology, if you give this kind of a connection, it will always be negative feedback. There's always a minus sign here. There's always this minus sign. You follow any topology, series, shunt, shunt, you will always get this negative sign. That means these topologies are for negative feedback amplifiers. They are what? Negative feedback amplifiers. Am I right? So let me write this once again. What is A? What is A? A is going to be V naught by VD. And what is VD? It is VS minus VF. What is beta? For beta network, input is V naught, output is VF. Beta is VF by V naught. And what is the overall gain? AF? A by 1 plus A beta. A by 1 plus A beta, right? If A beta is large, your AF is going to be 1 by beta. So this Vn is nothing but Vd here. This Vn is nothing but Vd. Am I right? This Vn is nothing but Vd. Vn. So what is Vn? Vn is going to be Vs minus Vf, right? It's same thing now. Both look same. Now, if you ask me, how are we going to follow this topology? Example, if you have a non-inverting amplifier like this, non-inverting amplifier, we know that a non-inverting amplifier will give you 1 plus R2 by R1, R2 by R1. The same non-inverting amplifier you can draw like this. To the plus terminal, we have to give Vs. To the output terminal, here we can connect RL, which you can short. From minus terminal, can you see from minus terminal to the output here, to the output, there is R2. The output. And here you have R1. So this is all ground. So ground nodes, you can join them. We join the ground nodes like this. So a non-inverting amplifier, what we've been doing till now is nothing but an amplifier with a series shunt topology. It's just an example. We will have so many examples. I'm just telling you, this is where we have to move on, right? If somebody asks you what is a type of amplifier, don't see op-amp, don't see resistors, don't see load, don't see source. What you have to see is how they are connected. Connection is amplifier. Design is amplifier, not a device. So instead of op amp, here if you put a BJT, it is still a voltage amplifier. Series shunt feedback, voltage control voltage source or voltage amplifier. Instead of BJT, if you put MOSFET, it is still a voltage amplifier as long as the feedback is series shunt. As long as the feedback is series shunt, right? Okay. So we'll come back there later, right? First, we'll see all the 4 topologies. Then we will make the connections. What is the second one? Series shunt. We'll change one at a time. Here we have series shunt. What if this shunt, I'll make it series? Shunt, I'm making it series. Series topology. Voltage controlled current source. Transconductance GM. GM is going to be I naught by Vs. GM is going to be I naught by Vs. Am I right? Transconductance. So how do you get transconductance? Both should be series. Both should be series. Input side series. Output side also series. And output is in current form. Whatever current enters, the same current should leave. Whatever current enters, the same should leave. So here you are having V in and Vf. So this is Vf. So this topology, either it is a BJT or MOSFET or op amp, doesn't matter, A. But as long as you follow this topology, it is called a series topology or a transconductance amplifier. Transconductance, right? Input is in voltage form. Input is in voltage form, but output is in current form. It is in current form. Input is in voltage form, but output is in current form. So now tell me, what is V in? V in equal to Vs minus Vf. Am I right? What is A? A is going to be I naught by V in, which is I naught by Vs minus Vf. And what is beta? Beta is Vf by I naught. And what is AF? A by 1 plus A beta. A by 1 plus A beta is AF. So similarly, draw the other 2 topologies. Draw the other 2 topologies. Can you see, if the amplifier is transconductance, beta is trans resistance, because for amplifier, input is voltage, output is current. For beta, input is current and output is voltage. Input is current and output is voltage. So beta is trans resistance. So strictly, this A is actually GM. This is RM. So what is the overall gain AF? It is A by 1 plus A beta. It is understood that it is GM by 1 plus GM into RM. Units and dimensions, yes or no? GM is the transconductance of amplifier, RM is the trans resistance. See, one more logic. Suppose if GM is negative, what should be RM? If GM is negative, inverting amplifier, then RM should also be negative. The negative of negative should be positive. So always A beta should be positive. Then only it is negative feedback amplifier. If the amplifier gives 180 degrees phase shift, the beta network should also give 180 degrees phase shift. Then A beta will always be a real value. No phase shift should be there. A into beta. A into beta, because it is added to a constant. Yes or no? You cannot add horses with donkeys. Constant means no units. That means A beta should also have no units. Then only it is added to one constant. Yes or no? So if amplifier is trans conductance, beta should be trans resistance. If amplifier is trans resistance, beta should be trans conductance. So what are the other two? What are the other two? The other two are shunt series, current amplifier, current control current source. Okay. So input is now in current form. Input is in current form. Your output is also in current form. So what is I in here? I in is Is minus If. Let us apply KCL. KCL tells that entering current equal to leaving current. Therefore, If is Is minus In. Or In is Is minus If. Your In is Is minus If. So what is A? A is I naught by In, which is I naught by Is minus If. Beta. Input to the beta network is I naught, output is If by I naught. And the overall gain AF is A by 1 plus A beta. A by 1 plus A beta. Please draw the last one. What is the last topology we are left with? First is series shunt, then series, then shunt series. What is the last topology we are left with? Last topology we are left with. Shunt. So what is A? V naught by I in. What is I in? IS minus IF. What about beta? Input is V naught, output is IF, IF by V naught. AF is A by 1 plus A beta. So these are the four topologies. So now we did nothing now. Till now what we have done, we know what is a series connection and what is a shunt connection. That's all. What is a series connection and what is a how to draw a series and how to draw two-port networks in shunt. If you recognize the connections, then you can get 2 marks minimum, right? 2 marks. Okay, so what is the first topology? Recognize the type of feedback comma feedback factor beta and the approximate gain V naught by Vs. Recognize the type of feedback factor beta and the approximate gain V naught by Vs. Recognize the type of feedback factor and the approximate gain V naught by Vs. The same thing you can draw with MOSFET also. In MOSFET, you can, just interchange the diode with MOSFET. So who is the amplifier now? Is BJT an amplifier, MOSFET an amplifier, or op-amp an amplifier? Amplifier is not the device, it is a design. All these amplifiers are same. The reason is they all have the same topology. They all have the same beta. They all have the same approximate voltage gain. So any device that you are going to use, these three are going to be same: feedback, feedback factor, and the approximate gain. It is same for all the three circuits. Recognize the type of feedback, feedback factor, and the approximate gain. It is same for all the three circuits. Okay. So how are we going to solve this? How are we going to solve this? If it is a BJT, or if it is a op-amp, to solve negative feedback, apply virtual short. Is it not? Apply virtual short. What is virtual short here? If you give Vs, your Vf is almost equal to Vs. Why it is equal? Because your Vf is going to be Vs by 1 plus 1 by the loop gain A beta. If A beta is large, Vf equal to Vs, right? So in op-amp, you have to assume Vd equal to 0. Vd 0, which means V1 is equal to V2. And IOP equal to 0. Current drawn by an op-amp is 0. Now, why V0 and I0 when you have two voltages which are same? If you have two voltages which are, suppose I am giving you 5 volt. 5 volt at input. Op-amp generates another 5 at the inverting terminal. Then what will happen? I am giving 5, op-amp generates another 5. Then what is the voltage from here to ground? Here to ground, minus 5 plus 5, this voltage Vd is 0. And even if you put a resistor between the two terminals, the current is going to be 0 minus 0 by R, current is going to be 0. So your Vd 0, Id 0, this kind of a circuit is called nullator. So who is a nullator? Any device which you give negative feedback is going to behave as a nullator. Whatever voltage you give at non-inverting is the same voltage at inverting. Similarly, BJT, you are going to make VB almost equal to VE. VB almost equal to VE, and your IB is approximately 0 in BJT. So in all the BJT problems, if you want a quick approximation, quick means what? By seeing a two-stage amplifier, you have to tell the gain. Now you don't have to do DC analysis, you don't have to do AC analysis. Why we should not do DC analysis, AC analysis? What for we have to do? So that we have to calculate. But in the end, when everything is getting cancelled, see, your amplifier is getting cancelled. Where is this? Yeah. Can you see here? A is getting cancelled. When A is getting cancelled, if you do it with small signal model, all the GMs and R naughts and R pi's, everything will come to numerator. Whatever GM R naught R pi has come to numerator, the same GM R naught R pi will come in the denominator also. And what will you do in the final step? All the GM R naughts and R pi's in numerator, all the GMs R pi and R naughts in the denominator get cancelled, and finally the gain will depend only on resistors. So if at all somebody wants you to assess the gain of the amplifier, if you do by AC analysis, replace all the DC sources to zero, capacitor short circuit, replace the transistor with a small signal model, and finally cancel it. Are you getting? So is it really useful? Right? Final step, you will cancel everything which you have calculated. So what if we cancel it in the beginning itself? You will save time. In the beginning itself, I am telling you, just don't care about the amplifier A. Just go and apply virtual short. What is virtual short? Virtual short we are going to apply for BJT. Virtual short we are going to apply for MOSFET. Virtual short we are going to apply for op-amp, because virtual short is not op-amp's birthright. Any amplifier with negative feedback, if the loop gain is high, is going to converge the error, and the voltage at plus is equal to the voltage at minus. The voltage at V1 is equal to the voltage at V2. The voltage at VB is equal to VE. Not 0.7. VBE DC is 0.7. This is AC analysis. This is AC analysis. So VB is almost VE. Your base voltage is almost equal to emitter voltage. And your base current is 0, you have to say. Base current is 0. Your VE is almost equal to VB. If you make this assumption, you will save time. For MOSFET, what is the equation here? Your VG is approximately equal to VS. So if you have a MOSFET, VG is given here. This is VS. VS you have to do approximately VG. And your IG, of course, IG is already 0. So if you do this assumption, then very quickly you will get the answer by inspection. This way we can avoid what analysis? Small signal, right? Do you remember we have done the gate problem where there is a feedback resistor 10K and series resistance 1K. I told you don't even do by Miller. Just by looking at the amplifier minus 10K by 1K. Are you getting? So those type of circuits we are going to do today, where no DC analysis, no AC analysis, just by looking at the resistors, 1 or 2 resistors, you will assess the gain of the amplifier. The whole gain is controlled by RF and R1. Okay? So let us solve it now. Tell me, how will you solve this? V1 equal to V2. This is V1. V2. V2 is almost V1. V2 is almost V1. So this voltage is also Vs. And here you have V0. Now you can apply voltage division rule. What is voltage division rule? Vs equal to V0 into R1 by Rf plus R1. From here, your V0 is 1 plus Rf by R1 times the Vs. Am I right? Similarly, in BJT, how will you solve in BJT? Your VB is almost equal to VE and your IB is 0. VE is almost equal to VE or IB is 0. So who is there at VB here? Vs. So at VE also, you are going to have Vs. VB equal to VE. Here there is V0. You can apply voltage division. So Vs equal to V0 into R1 by Rf plus R1. So your V0 is 1 plus Rf by R1 times the Vs. See, for op-amp, if Rf is 9K, R1 is 1K, Rf is 9K, R1 is 1K, you will get around 10, is it not? But in BJT, you will get around 9.8, 9.9. So by seeing an amplifier, we can tell the gain is 10. If Rf is 9K and R1 is 1K, right? See how simple it is now, right? How will you solve MOSFET now? How will you solve MOSFET? Your VG equal to Vs, right? So this voltage is almost to 0, virtual short. If there is Vs, there is almost Vs here. You can apply voltage division. What is voltage division rule? In all the problems, solution is same. This is Rf, R1. The amplifier is a voltage controlled voltage source. It's a voltage source. So this is how you solve a two-stage amplifier. Somebody gives you a two-stage transistor amplifier. With this you have to solve. See how important voltage division rule is, right? Two-stage amplifier is solved by voltage division rule. So what is the Vs here? Or some current I we can take, right? Let's derive voltage division rule, right? What is I? I equal to V naught by Rf plus R1. Rf plus R. What is Vs? It is I into R1. Vs is I into R1. What is I? It is V naught by Rf plus R1 into R1 is Vs. Can you see? Or what is V naught? 1 plus Rf by R1 times of Vs. 1 plus Rf by R1 times of Vs. Your V naught equal to K times of Vs. This is a voltage amplifier. It is a voltage amplifier. A two-stage voltage amplifier is solved by voltage division rule. What about transistors? Don't care about them. If you replace them by small signal model R pi, R naught, GM, final step everything will get cancelled. The gain will depend only on resistors. So for assessing the gain, don't look at the BJT. Okay, how to recognize the topology? Draw AC equivalent. In AC equivalent, you have R1 here, RF here. Here there is RC1. Please draw AC equivalent for this. For AC equivalent, what will you do to voltage sources? For AC equivalent, the voltage sources are short. So RC1 is connected to ground, RC2 is also connected to ground. So this is a circuit you get. All right. So let me draw the circuit here just to give you a good feeling where the feedback is series shunt. This is Vs. RC1, RC2, output, this is all ground. Now just tell me, where is RF connected? RF from the emitter of the first transistor to collector of the second transistor. Collector of the second. And here you have R1. This is ground, this is ground. So you can join it. It's all ground, 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 ground. So can you see that this is what topology? Series at input and shunt at output. It's a voltage control voltage source. It is what source? Voltage control voltage source. Now, is there any shortcut to know it without drawing all this nonsense? Just by seeing the circuit, can you tell me what is the type of topology? Without drawing anything, can you tell the type of topology? I'll give you a simple shortcut here, right? Recognition of topology, right? Recognition of topology. So if you have an op amp connected to non-inverting, and at inverting, this is from the beta network, then naturally it will open up like this. Yes or no? It will open up like this. Ground. This is from the beta network. This is a series at input. Simple, sir. Same terminal means shunt. The feedback is taken input at point A, feedback also from point A, shunt. Input given at point A, feedback given somewhere else. If it is somewhere else, then it is series. So what is the difference between shunt and series topology? Same point is shunt. Elsewhere, if you give it is series. Voltage is given to plus. Feedback is given somewhere else, minus, somewhere else you have given. So naturally, it opens up like this. It is series at input. But if input is given to one terminal and the feedback is taken from the same terminal, if input is given to one terminal, feedback is taken from the same terminal, it is shunt at input. Shunt at input, right? Input is given to one terminal, feedback is taken from some other terminal. So input is given to one terminal, feedback is taken at some other terminal, then it is series at input. Input is given to one terminal, feedback is also taken from the same terminal, then it is shunt at input. This is shunt. One is a shunt series at input, the other one is shunt at input. In op-amp, if the sampling is taken just after op-amp, then it is across the load, it is shunt at output. It is shunt at output. So similarly, shunt at output, right? It is shunt at output across the load. Now, what is series at output? If you take through the resistor, through the load resistor, then it is series at output. Series at output. If you're not taking across the load, right? Here, if you take it is shunt, but now somewhere else they have taken and tapped here. So naturally it is series at output. It is series at output. After op-amp, if you take, it is shunt. Through the load resistor, if you take, it is series. So now the current is series at output. That means you are sampling current at output. This is current sampling. What is this here? It is voltage mixing. This is current mixing. This is voltage sampling. This is current sampling. So slowly you will understand this, but there is a simple shortcut. Same point if you give, it is shunt. If you give elsewhere, it is series. So if you give to non-inverting and through inverting you are giving the feedback connection, then naturally it will open up like this. It is said to be a series connection. But if you give it to the same point, it is always a shunt current. Of course, I will draw clearly, but I'm just asking you to recognize just by inspection. Yeah. Now, once you get it, what is beta? Feedback factor beta. Feedback factor beta is always 1 by AF, or AF is 1 by beta. AF is 1 by beta. So feedback factor beta is 1 by AF or 1 by gain. What is gain of the amplifier? 1 plus RF by R1. That means feedback factor beta is going to be R1 by Rf plus R1. The feedback factor is going to be R1 by Rf plus R1 because the gain of the amplifier is 1 plus Rf by R1. Are you getting? So if somebody gives you this amplifier for 2 marks, what they will do? Recognize the feedback. How do you recognize? Input is given to some terminal 1. Feedback resistors are connected at some other terminal, some terminal 2, right? Then it is series. The load is connected at collector. The feedback is taken from the same collector, same terminal. Load is connected at terminal A, which is collector. Feedback is also taken from the same terminal A. Same terminal, it will always form shunt. Different terminal, it will always form series. It will always form series. So this is a shortcut to recognize topology, right? This is just by observation, by observation. This is by observation. Yeah. So now you can take screenshot, right? This is the first circuit I've given. 3 circuits. Solution is same. Solution is same. BJT, MOSFET solution is same because all the circuits are solved by voltage division rule. Voltage division rule. So what is the solution of all the circuits? The solution of all the circuits is voltage division rule. This one is the solution. This one is the solution. That's all. The solution for all these circuits is a voltage divider rule. V0 by Vs is 1 plus Rf by R1 times of Vs. This is how we have drawn the AC equivalent. And this one, the second diagram will give you a good feeling that input side is in series and output side is in shunt. Input side is in series and output side is in shunt. So this is how you recognize the topology. Because in feedback amplifiers, mostly recognition of amplifier or recognition of topology is important, right? Recognize topology. Feedback factor and approximate gain. Gain without by inspection. Don't do DC analysis, don't do AC analysis. This is the second amplifier in our class, the inverting amplifier. I told you this is a trans resistance amplifier. Now please, the same transistor, you can have a differential amplifier also, right? Differential amplifier, the moment you find a differential amplifier, the differential amplifier will have two terminals. One is plus terminal, the other one is minus. You can equate it to an op-amp. So whenever you find a differential amplifier, the whole differential amplifier, you can assume it to be an op-amp. One end is plus, the other end is minus, and you can draw the feedback structure. Are you getting? So even if you have a 2-stage, 3-stage differential amplifier, doesn't matter. This whole thing, what is this whole thing here? You can assume this whole thing as a difference amplifier or a differential amplifier. Even for a differential amplifier, voltage at non-inverting is equal to voltage at inverting only, right? All of you see here, I will give you a simple example. In a non-inverting amplifier, what is the gain? The gain is 1 plus RF by R1 times of V. Am I right? Can we get the same thing using op-amp, I'm saying, using differential amplifier? The same structure, can I draw it like this? So here some current mirror will be there, no problem. Okay, this is a BJT, not a MOSFET. So I'll give Vs here. When you give Vs, this is plus terminal, this is minus terminal. To minus terminal, if you want a common collector amplifier stage, you can connect it. Here, this is the output. Can you see from the output to minus, there is RF. Output to minus, there is RF. Here, there is R1. Now, if such a structure is given, and you are asked to find gain, how will you do it in this problem? The effort that you put in this problem is the same effort that you should put here. So this is plus terminal, this is minus, this is your VF. Voltage at non-inverting is equal to voltage at inverting. So this is Vs here. You applied what rule? Voltage division. And you came to know V0 is 1 plus RF by R1 times the Vs. Am I right? Now, this whole block here, this is a plus terminal, this is a minus terminal. This whole block is your op amp now. This whole thing is your op amp. But this is kind of a sleeping op amp, right? It's something like, oh, I need a different color. Yeah. This is something like a sleeping op amp, like this. Here we are giving Vs. Here there is a voltage divider. So dotted line, I'll put like this. Like this. Now, how will you solve whether it's an op amp sleeping or standing? Voltage at non-inverting is equal to voltage at inverting. So similarly, this Vs is this Vs, no? If there is a Vs here, there's a Vs here, entering current equal to leaving, neglect base current. Then V0 minus Vs by Rf is same as Vs by R1. Then what is V0? It is 1 plus Rf by R1 times the Vs. Are you getting? So whenever you find a differential amplifier, because differential amplifier is drawn sideways, no? Think that it can be equated to a sleeping op amp like this. Whether you call it sleeping or standing, whatever. Huh? So this is non-inverting terminal plus terminal of one amplifier minus, and then you are giving feedback. Are you getting? So a differential amplifier also you can visualize like this. Yeah. It has become zigzag. Huh? You can draw it neatly. You draw it neatly. You realize what big block you draw, right? You draw it like this. Oh, I need space for this. You draw it like this. This is an op amp. So who is here? Simply, I connected a common collector here. Now this guy is the minus terminal. This guy is the minus, right? So now how do you solve such a circuit? The voltage at non-inverting is equal to voltage at inverting. Here you have RF, here you have R1. Op amp draws no current. Op amp draws no current, but this happens to be the base current. Previously it was IOP for us. It was IOP. Now it is IB. IOP or IB is what? 0. Op amp draws no current. So entering current equal to leaving. So V0 minus Vs by Rf is Vs by R1. So your V0 is going to be 1 plus Rf by R1 times the Vs. Are you getting? Right? But if there is no feedback, tell me if there is no feedback, what is the gain of open loop gain? No feedback. Then right side if you take, if this is V0 by Vs, it is going to be plus GMRC by 2. Plus GMRC by 2. What happens if you give negative feedback? The moment you give negative feedback, this GMRC by 2 is going to get cancelled. So it is something like this. If you don't give feedback, it is GMRC by 2, right side. But if you give feedback and then the beta, the overall gain is now going to depend only on beta. Your GMRC by 2, right side, is going to get cancelled, right? This is A. A is going to get cancelled because overall gain is A by 1 plus A beta. A is going to get cancelled. The gain will depend only on 1 by beta. Are you getting? Right? So whenever a differential amplifier is given, also you can solve very easily. Right? Draw an op amp like this, differential amplifier. Voltage at plus is equal to voltage at minus. Voltage at non-inverting is equal to voltage at inverting. Op amp draws no current. That is a simple way. Voltage division rule you can How do you solve this? For op amp, V1 is approximately V2. For BJT, VB is approximately VE, virtual ground. For MOSFET, VG is approximately VS. VG is approximately VS. If V1 is approximately V2, then this is 0. Entering current equal to leaving current. IOP is 0. So tell me, if you have RF here, this is 0 volt. You have V0, current is IS. IS equal to 0 minus V0 by RF. So your V0 is going to be minus RF times of IS. So input is in current form, output is in voltage form. See here, all of you, did we do, for the first problem, did we ever do DC analysis and AC analysis of all the 25 transistors inside? Did we ever attempt to do DC analysis and AC analysis of all the 25 transistors inside, even in this problem? Did we do? If I had the non-inverting amplifier, why we didn't do DC analysis and AC analysis of the transistors inside? Because we know it is waste of time. Even if you do A by 1 plus A beta, A is however going to get cancelled. Similarly, when you don't do here, you have no right to do even in the BJT circuit. Because both have the same topology, if you do DC analysis, AC analysis for the BJT, final step, it will get cancelled and you will think that unnecessarily you have wasted time. Wasted. Are you getting? Suppose two students are there. One student who's doing with DC analysis and AC analysis. The other student is not doing, he's just seeing and telling the gain. He's saying gain is 1 plus RF by R1. Which is better, right? By inspection, you have to solve 1 plus RF by R1, even without doing anything, right? Yeah. How do you solve BJT? Your VE is almost 0. Your VB is almost 0. Because your VBE is VB minus VE. If your VE is 0, your VB is equal to VE. And what is the second assumption? Your IB is almost 0. Here IOP is almost 0. IB is neglected. So if this is IS, this current is also IS. This current is also IS. So now tell me, what is V0? What is V0? What is V0 here? Your IB is almost 0. This is 0. Right? It is not 0. There is a small VB here. There is a small VB equal to IB into R pi. IB is 0, VB is almost 0. Right? If VB is 0, your VB is equal to VE. Nullator. Then the current drawn by IB, here IB is also 0. Then this current is IS. So how do you solve this? To solve this, IS equal to 0 minus V0 by RF. IS equal to 0 minus V0 by RF. V0 is minus RF into IS. Minus RF into IS. So this is a simple way. Are you getting? If you want topology, what is the AC equivalent for it? AC equivalent. RC here, current source here, and resistor here, RF. Tell me, what is AC equivalent? Have you recognized the topology? If you have not recognized, then I'll draw like this. This ground. The source also has ground. Am I right? Now, where is your RF? Your RF is from here to here. It is actually from base to collector, but I'm drawing it like this. And this is ground and this is ground. So they are all ground nodes. Just to give you a good feeling that this is shunt at input and shunt at output. Shunt topology. So recognize the type of feedback. The feedback equal to minus RF gain. What is the feedback factor beta? Feedback factor beta equal to 1 by gain. It is minus 1 by RF. The same thing you can do with MOSFET also. With MOSFET. Tell me for MOSFET, how will you solve? This is VG. VS is almost 0. VS is ground 0. Your VG is almost 0. Because VGS is 0. VG equal to VS. IG is 0. So this current is IS. IS equal to 0 minus V0 by RF. 0 minus V0 by RF. So your V0 is minus RF times of IS. Your V0 is minus RF times of IS. So how do you program that signal? Programming current IS with VS and R1. So if you see my first classes, right, op-amp, this is the statement I wrote for an op-amp inverting amplifier like this. Programming current IS with VS and R1. So now tell me, how do you solve this? If this is 0, this voltage is also 0. Entering current equal to leaving. Op-amp draws no current. Am I right? So VS minus 0 by R1 equal to 0 minus V0 by RF. V0 by VS or V0 equal to minus RF by R1 times of VS. Do you remember this inverting amplifier formula? Yes or no? So the same problem is given in GATE exam for 2 marks. I have already told you, but it is given not with op-amp but with BJT, is it not? But with BJT, here there is RC. This problem we have already solved with Miller. This is RF capacitor here. So this was around 10K. This is 1K. I told you. This is a GATE problem. So how to solve this? Examiner unnecessarily has given beta, thermal voltage, VT, this, that. He is forcing you to do DC analysis. He is forcing, because all the negative feedback amplifiers are operating point independent. Irrespective of any operating current, the gain is dependent only on resistors. When they are operating point independent, it is waste of time doing DC analysis. First DC analysis, then AC analysis, then finally your answer will come 9.8. In the option, if you see 10 will be there, then you will think about 10 is there, right? It is all waste of time. But what is a quick way of doing this analysis? If this is 0, this voltage is almost 0. Capacitor is replaced by short circuit. IB is 0. VB is almost VE, virtual short. IB0. This is the new network analysis technique. What is the new network analysis technique? Any time there is feedback, please apply this technique to save time. To save time. It is only to save time. If you are reluctant, you say, no, I don't want to apply this feedback. I will do DC analysis, AC analysis. Then also you can do. Unnecessarily, it will take a lot of time. So this is a new technique we are learning in feedback amplifiers. What is the new technique? Apply virtual ground for any feedback amplifier. Whether it is BJT or MOSFET or op-amp, don't hesitate. Just to do V1 equal to V2 for BJT, sorry, op-amp, VB equal to VE for BJT, VG equal to VS for MOSFET. If you do that, it will save a lot of time. Like how you are not doing DC analysis and AC analysis of the transistors inside an op-amp, you will not do DC analysis and AC analysis of BJT and MOSFET also, right? So if this is the current, this current is equal to this current, IB is 0. So tell me what is this current here? Entering equal to leaving. It is Vs minus 0 by 1K, 0 minus V0 by 10K. This is a get problem for 2 marks. V0 by Vs is minus 10. See how simple it is, yes or no? Right? Very, very simple. Right? So this is given 2 times in GATE exam. Because the trick is virtual short. You have to apply virtual short to BJT. VB is almost equal to VE. IB is 0 in negative feedback, right? Do not apply virtual short if there is no negative feedback. Apply only when there is negative feedback, right? So if your BJT is PNP, please convert it into NPN. Your answer is not going to change. So 2 feedback topologies we have seen. We are left with 2, right? One is a non-inverting series shunt. The other one is inverting amplifier or trans resistance amplifier. This is trans resistance amplifier. We are left with 2 more feedbacks, right? What are they? The third feedback is recognize feedback. So we are going to have series, recognize feedback, beta and gain. Now, if you replace BJT with MOSFET, then you are going to get the same answer. So what is negative feedback and positive feedback we have seen? If the increase in output will further increase, it is called positive feedback. If the increase in output will decrease, it is called what feedback? Negative feedback. So in any amplifier, where there is negative feedback, you tell me if V0 increases, your Vs or Vf will increase here. Vf is Vs. Your Vf will increase. If Vf increases, your Vd will decrease. Your Vd will decrease. If Vd decreases, your V0 will decrease. So if V0 increases, V0 will decrease. If V0 decreases, again Vf will decrease. Your Vd will increase, and your V0 will increase. So you can see that V0 increase and V0 decrease. It is what feedback negative. Similarly here, if V0 increases, your emitter voltage VE will increase. If VE increases, the error calculator here VB, your VB is going to decrease. So whenever VB decreases, naturally IC will decrease, V0 is going to decrease. So if V0 increases, V0 will decrease. So if V0 decreases, again VE will decrease, your VB will increase, and your V0 increases. So all these structures have a mixer here. The error calculator here has VD, here the error calculator has VB, right? It is going to have VB. So the analysis is same. Similarly, you can see here, if I0 increases, what will happen to VF here? I0 increases, VF will increase. If VF increases, VD will decrease. If VD decreases, your I0 will decrease. But the increase of I0 is compensated by decrease. Similarly here, if I0 increases, this VF will increase. VF increases, VB will decrease. Again, if base emitter voltage is less, naturally the output current will also be less, right? So all these structures are having negative feedback, but solving them is very, very simple. Solving them is very simple. You have to simply make an assumption that this voltage is approximately this voltage. This voltage is approximately this voltage, and you can apply current division formula. Is I not? Here there is Vs. Am I right? This is I naught. Your Vf is approximately equal to Vs. So I'm drawing it separately here, current division. Let this current be Ix. So Vs equal to Ix into R3. R3. Ix by current division is I0 into R1 by opposite arm current by sum into R3. So what is the transconductance Gm? The transconductance Gm is I0 by Vs is going to be R1 plus R2 plus R3 by R1 R2. This is the gain of the amplifier, gain AF. What is beta? Beta is 1 by AF, or AF is 1 by beta. It is going to be R1 R3 by R1 plus R2 plus R3. Is the feedback factor. The feedback factor is always going to be inverse of the gain. Inverse of the gain. This is a transconductance amplifier. So the gain is R1 plus R2 plus R3 by R1 R3. Now, what topology is this? Input is given to some terminal 1, feedback is given to terminal 2, some other terminal. Naturally, it is series. The load is connected to some terminal X. The feedback resistors are connected to terminal Y. If they are connected to different terminals, then it is series at input and series at output, right? Different terminal, series, same terminal, it is shunt. So how do we know that? You can draw AC equivalent for this, AC. What is AC equivalent? This is the first transistor, second transistor, third transistor. Now let us go back to the circuit. Tell me, if this is ground, where is the feedback resistor R2 connected? R2. R2 is connected from emitter of the first transistor to emitter of the second transistor. Emitter of the first transistor to emitter of the second transistor. And of course, here you have R1 and R3. R1 and R3. So R1 is here, R3 is here. And join all the ground nodes just to give you that feeling of, box. Upper one box A, lower another box beta. This is ground, this ground. So let's join, put one wire like this. So then you will know that this is what topology? Series. Voltage controlled current source. It is voltage controlled current source. Current source. See, simple. Forget about the series shunt. Tell me logically, if you want to take current, because this is taking, this is giving. If you want to take current lena hai, then you will always take in series. If you want to take voltage, आपको voltage लेना है, then you will always take voltage in shunt, parallel. But when you want to give voltage or give current, there should be current division or voltage division. So I want to give voltage. When I want to give voltage, naturally there should be a voltage division. So you have to give only in series. Voltage giving means series. Current you want to give, current division. How current division will be there? When you give current, naturally current has to divide. So it will be in shunt. That means logic. What is the logic here? Taking current means what? At output, if you are taking current at output, this is output side. Taking current means what topology? Series, right? You take from, right? Taking voltage at output. It has to be shunt. You take voltage only at shunt. But you want to giving voltage. You want to give voltage at input side. We have already seen, right? So you want to give here. Yeah, I want to give VF. There is already VD. There is VS. So when you want to give, you have to give voltage in series. If you want to give current, it has to be in shunt. Are you getting? So input side we are giving, output side we are taking. That is what is called feedback. Right? Taking and giving. Taking, giving. With this also we can have name, no? We can have a name. Topology we know, series. What about feedback name? How will you give feedback name? This feedback is also called current to voltage feedback. What you are taking, you have to mention first. What you are giving, you have to mention later. What you are taking here, current. What you are giving here, voltage. This is also called, this one is also called, what name? Current to voltage. Don't say voltage to current, because feedback always comes from the output to input. Topology name comes from the input to output. Topology, series, shunt, series, like that. If you want to know the type of feedback, you should always mention the parameter of interest at the output and then input. So this is also called current to voltage feedback. It is also called what feedback? Current to voltage feedback. Okay, we'll take a break. Last session, after this last session, we will wind up after doing the last feedback and one or two few questions, recognizing the input and output resistance we have to calculate. And with that, we will wind up, right? So next will be the last session of analog subject, right? We'll take a break now. When we come back, we will see. Okay. So now we have found the transconductance of the amplifier. GM. What is GM? I naught by Vs. But if you are asked to find voltage gain, what you have to do? V naught by Vs can be written as V naught by I naught into I naught by Vs. What is V naught by I naught? V naught by I naught, if this is V naught by I naught is minus RC. It is minus RC gain. I naught by Vs is nothing but GM. So it is going to be minus GM into RC. The voltage gain of this amplifier is going to be minus GM into RC, right? Minus RC is the load. RC is the load. GM is the transconductor. So now, who decides GM here? Who decides GM? In a common emitter, the GM is decided by the BJT. So if there is any change in the BJT parameters, then the gain will change. But here, these are stable because the transconductance itself is decided by the resistors. R1, R2, R3, right? R1 plus R2 plus R3 by R1, R3 is GM. So your voltage gain, AV, is going to be minus GM into RC. Okay, whatever it is, that is not, see, a good amplifier is one where the output parameter should never depend on load. Here it is dependent on load. That is why voltage gain is not the parameter. GM is the parameter. GM is output current by input voltage. If you do output voltage by input voltage, then the load will come into picture. The load is going to come into picture, right? Okay. So what is the last feedback we are left with? The last feedback we are left with is first we have done the voltage amplifier, then we have done the trans resistance. This is the transconductance. So I think we are left with current amplifier. Recognize feedback, find beta and gain. Recognize feedback, find beta and gain. So recognize feedback, beta and gain. This is the current amplifier, right? So what sort of feedback is this? Input is given to some terminal 1. Feedback resistors are also connected to the same terminal 1. So it is shunt. The load is connected to some terminal, feedback is connected to some other terminal. It is series. Same terminal shunt, different terminal, it is series. Shunt series. So high-low voltage amplifier, low-high current amplifier. This is a current control current source. It is a current control current source. The feedback is shunt series. So after the op amp, if you take from here, then it is shunt. Through the load resistor, if you take, it is always series, right? So how are you going to, you draw AC equivalent, then you will realize if you draw AC equivalent, what is AC equivalent? DC sources should be grounded. DC sources should be grounded. So this is ground, you can short it, right? Now, where is RF? Where is RF? Can you see RF is connected from gate of the first transistor to source of the second. Gate of the first transistor to source of the second. And R1 is connected from source to ground. It is connected from source to ground. Now you can join all the ground nodes. This is ground. So input is given to some terminal, feedback resistors. See, how do you know who is a feedback resistor? Here, how do you know who is a feedback resistor? RD or load. If you remove the load, whatever the resistors that are left, they are called feedback resistors. Feedback means the output should be fed back to input. Are you getting the output? A portion of output should be fed back to input. So the feedback topology is shunt series. The feedback topology is shunt at input and series at output. Okay. So let us solve this. How to solve this? Virtual short. V plus equal to V minus and IOP equal to 0. IOP equal to 0. So if this is ground, this voltage is 0. The current drawn is 0. So the same current will travel here. Now the same thing with MOSFET. Here, your VGS is approximately 0. That means if this is ground, this node is 0. And what is the second assumption? The current drawn by the gate terminal is 0. IG is 0. Then the current going through feedback is also IS. The current going through the feedback is also IS. So let me draw this like this. This is I0 coming. Here you have R1. And here this is at virtual 0, RF. And you have IS here. You have IS. Right? So you have IS. So now you can find a relationship between I naught and IS. I naught and IS. How will you find the relation between I naught and IS? If this is IS, the current in opposite is minus IS. So you can apply current division. That is one method. Another method, if you don't remember current division formula, then you can apply KCL. This node we don't know, we'll call it Vx. We'll call it Vx. So tell me, what is entering current equal to leaving current? So I naught equal to Vx by R1 plus Vx minus 0 by Rf. It is Vx into 1 by R1 plus 1 by Rf. Equation 1. But what is IS? But IS is 0 minus Vx by Rf, or Vx is minus Is into Rf. Substitute 2 in 1. Substitute 2 in 1. You get I naught equal to minus Rf Is into 1 by R1 plus 1 by Rf. From here, what is the gain I naught by Is? It is the same gain of non-inverting amplifier, but with some negative sign. With a negative sign, your I naught by Is is going to be minus of 1 plus Rf by R1. Minus of 1 plus Rf by R1. You can take this node as Vx, right? You can take this node as Vx. So I naught by Is is going to be minus of 1 plus Rf by R1. So what is the feedback factor beta? Beta is going to be 1 by gain. 1 by minus of 1 plus Rf by R1. It is going to be minus R1 by Rf plus R1. This beta. So what sort of amplifier is this? This amplifier is also called the current amplifier. Current amplifier or current controlled current source. Current controlled current source. Okay. input and output resistance of a feedback amplifier. Input and output resistance of a feedback amplifier. So let us take the first circuit. So what is input resistance? Input resistance of this basic amplifier is given as V in by I in. Am I right? V in by I in is the input resistance of the basic amplifier. So who is basic amplifier? BJT, MOSFET or op amp, right? This is a basic amplifier. But after giving feedback, the closed loop input resistance with feedback is going to be Vs by Is. It is going to be Vs by Is. So input resistance of the basic amplifier in open loop is V in by I. V in by I. Am I right? What is input resistance with feedback? It is going to be Vs by Is. Am I right? Vs by Is. Then what is the relationship between this input resistance with feedback and input resistance of the basic amplifier? Any relationship? Because we know V in is equal to, or Vs equal to, what is Vs? Vs is equal to V in plus Vf. Am I right? The Vs is equal to V in plus Vf. But if you have V0 here, if you have V0, can I say Vf as beta times of V0? Vf is nothing but beta times of V0. Because what is beta? Beta is Vf by V0. Beta is Vf by V0. What is A? V0 by Vin. A is V0 by Vin. Beta is Vf by V0. This is forward path. This is a feedback path. Feedback path. So V0 can be written as A times of Vin. So from here, what do you get from here? Your Vs is nothing but Vin multiplied by 1 plus A beta. So your Vs is nothing but Vin into 1 plus A beta. And what is Is and In? Is and In. Is is same as In. So this is very, very important. Your Vs is Vin into 1 plus A beta, and your Is is same as In. Is is same as In. So now you tell me, what is Vs? Vs is going to be Vin multiplied by 1 plus A beta. And Is is same as In. So what is Rin of the basic amplifier? Vin by In. So it is Rin of the basic amplifier multiplied by 1 plus A beta is Rin with feedback. So this is a very, very important observation. So whether there is an op amp with some input resistance RID or Rin, this resistance is going to get multiplied by 1 plus A beta times. This resistance is going to get multiplied by 1 plus A beta times after giving feedback. After giving feedback. Similarly, in shunt topology, what will happen? In shunt topology, the input resistance is going to decrease by 1 plus A beta. Similarly, in shunt topology, what about output resistance? How will you calculate output resistance? For calculating output resistance, your voltage sources should be shorted, no? Your voltage sources should be shorted. This is your input resistance. Here you can have output resistance R0. So what will happen to that R0 value of the basic amplifier? This resistance is going to get divided by 1 plus A beta. It is going to get divided by 1 plus A beta because of the shunt topology. With a series topology, the input resistance of the basic amplifier is going to get multiplied by 1 plus A beta.
Is it done?
So what about output resistance? I have an amplifier with some output resistance. For calculating output resistance, the voltage sources should be shorted. Voltage sources should be shorted. You have to open circuit the load. Open circuit the load. Connect 1 volt source as a test voltage. Find current IT. By Ohm's law, output resistance is Vt by It. It is 1 by It. So what happens in if you and what is Vf here? This is Vf, this is Vn. Vf is going to be, how much is Vf? Yeah, we have written here. What is Vf? Vf is beta times of V0. Vf is going to be beta times of V0. Beta times of this Vf. Here I'm having V0. Here you are going to have Vf, which is beta times of V0. Here you can have an open circuit. This is V0. So this V0, Vf is nothing but beta times of V0, right? So some connection. This is A times of Vin or Vd. So what happens if my Vs is shorted? Vs equal to Vn plus Vf. Your Vs is 0. Your Vs is 0. Therefore, your Vf is going to be, how much your Vf is going to be? Or your Vn is going to be minus Vf. Vn is going to be minus Vf. Am I right? So give me Ohm's law. What is It here? It equal to, this voltage is 1 volt. 1 minus AVn by R0. 1 minus AVn by R0, right? And what is Vf? Vf is going to be beta times of V0. So let me substitute here. Vn is nothing but minus beta times of V0, right? Minus beta times of V0. And how much is V0? 1 volt by R0. So it is 1 plus A beta by R0 is It. Now, what is the output resistance? It is 1 by It. It is going to be R0 divided by 1 plus A beta. R0 divided by 1 plus A. Because what is V0 here? V0 is going to be 1 volt. 1 volt. So this is only beta. Beta into 1. Vf is beta into 1. So V0 is 1 volt So your R naught is the R naught of the basic amplifier divided by 1 plus A beta. So whenever there is a series topology, your input resistance of the basic amplifier is going to get multiplied by 1 plus A beta. If there is a shunt topology, if you calculate output resistance, this is calculation of output resistance. How do you calculate output resistance? First class I've given you. You have to remove the load first. You have to open circuit load, short Vs, connect 1 volt source and find current. Connect 1 volt source and find the current. You realize that the R naught is going to be small R naught of the basic amplifier divided by 1 plus A beta. Okay. So please remember, series topology means the resistance will enhance, will increase. Whenever it increases, multiply by 1 plus A beta. For output resistance, it is going to decrease. So naturally, you have to divide by 1 plus A beta. This input resistance is given for 8 marks, I think, in IES. Prove that the input resistance of the basic amplifier is multiplied by 1 plus A beta times with feedback. Now, in the buffer section, do you remember in op amp in the buffer section, I told you input resistance of buffer is very high and output resistance is low. But we didn't calculate. If you see the class notes, I didn't calculate the input resistance and output resistance. I just said buffer is a VCVS. Now I have an opportunity to calculate it because given op amp has RID equal to, you can take RID equal to, say 1 mega ohm, 1 mega ohm input resistance. R naught of op amp is 10 ohms, 10 ohms. Open loop gain, open loop gain is 10 lakhs. Open loop gain is 10 lakhs. Find the input resistance with feedback and output resistance with feedback. With feedback for the buffer. For the buffer. So a buffer will just have a wire like this. Am I right? So now we are asked to find input resistance with feedback and output resistance with feedback. Input resistance with feedback and output resistance with feedback. Okay. So from the non-inverting terminal, we have given Vs, and from here to the output, there is a load where you take V0. All right. This is ground, so this is ground. Now just tell me how this wire is connected here. From the minus terminal to output, beta is 1. From the minus terminal to output, beta is 1. So it is connected from minus terminal to output. Wire means no attenuation. If this is Vf, Vf by V0 is going to be 1 because Vf and V0 both are same. Vf and V0 both are same, right? So this is ground, so you can short it here. And this beta goes all the way to the output. So this is ground node, so you can short it. So now you realize that connecting a wire like this is not a joke. You might think what is their output is fed back to input. No. Just by connecting a wire like this, you have increased the input resistance by 1 plus A beta times. You have decreased the output resistance by 1 plus A beta times. Because of the series topology, what is the input resistance with feedback? This one, Rin of F. What is R naught of F? Rin of F is going to be RID of the basic amplifier multiplied by 1 plus A beta. So what is RID of the basic amplifier? 1 mega ohm, 10 power 6. Gain is also 10 power 6. Beta is 1. So it is going to be 10 power 12 ohms is Rin of F. What is R naught of F with feedback? It is R naught of the basic amplifier divided by 1 plus A beta. So this is not that good of an op-amp. Op-amp output resistance will still be low, but I took 10 ohms here, 10 ohms. But after feedback, gain is 10 power 6. So this is going to be 10 power minus 5 ohm. So 10 power 12, can you imagine 10 power 12 ohms input resistance and 10 power minus 5 ohms output resistance, right? So if somebody asks you why negative feedback, what you will tell him? In a single nutshell, in a single sentence you have to finish. Why negative feedback? If somebody says, you simply tell him a non-ideal device will build an ideal amplifier. A worst device, BJT, a worst device, non-ideal, is going to build an ideal amplifier if you give negative feedback. Because your distortion will reduce, noise will reduce, bandwidth will improve, linearity will improve, input resistance will improve, output resistance. Every factor is going to be by 1 plus A beta times, 1 plus A beta, 1 plus A beta, 1 plus A beta, 1 plus A beta, 1 plus A beta. So your input resistance is improved by 1 plus A beta, your output resistance is divided by 1 plus A beta. So simply, why negative feedback? If somebody asks why negative feedback, so what is the answer for this? A non-ideal device is used to build an ideal amplifier. If you want almost an ideal amplifier, high input resistance, low output resistance, good linearity in the circuit, you simply take a non-ideal device, but give negative feedback. You give negative feedback, finished. The amplifier with that useless device is going to become an ideal amplifier. So if you have a voltage amplifier, input resistance of the basic amplifier is multiplied by 1 plus A beta because of series shunt topology. Series shunt. High input resistance, low output resistance. Your output resistance will divide by 1 plus A beta. Divide by 1 plus A beta. So what is the feedback topology here? The feedback topology is, this is a voltage controlled voltage source. Am I right? So I told you, feedback means you should always come from the load to the source. So what is a type of feedback? Type of feedback. The type of feedback, it is voltage to voltage. Voltage to voltage, or it is voltage mixed in series. So it is called voltage series feedback. So from the output to input you have to talk. You can either say voltage to voltage, or you can say voltage series feedback. So what is the second amplifier? Second amplifier is current amplifier. Current amplifier is shunt series topology. Current control current source. Shunt, input resistance will decrease by 1 plus A beta. Output resistance will increase by 1 plus A beta. So what sort of topology is this? Or the type of feedback it is? The topology is shunt series. Type of feedback is current to current. Or current shunt. The current at output is mixed in shunt at input, current shunt. So the third one is the transconductance amplifier. Transconductance. Series. Voltage control current source. Series transconductance, voltage control current source. So whenever input is in series, input resistance will be multiplied by 1 plus A beta. Output resistance also multiplied by 1 plus A beta. Right? So what is the type of feedback? Feedback. It is current to voltage. Current to voltage feedback. Or current series feedback. Current series. Similarly, what is the last one? Trans resistance. The last one is trans resistance amplifier. It is shunt topology. Current control voltage source. So what will happen to the, for shunt, input resistance of the basic amplifier is going to get divided by 1 plus A beta. This is Rin with feedback. What is R naught with feedback? It is the output resistance of the basic amplifier, again divided by 1 plus A beta. The output resistance of the basic amplifier is again divided by 1 plus A beta. So what is the type of feedback? You can call it voltage to current feedback, or voltage shunt feedback. Voltage shunt feedback. So voltage series, current shunt, current series, voltage shunt. Now, I'm going to give you two special cases. Special case of single discrete feedback system. So all these amplifiers we have seen, but two amplifiers are special cases. What are special cases is, within a device there is a feedback going on. Within the device there is a feedback going on, right, in amplifier. One is common collector amplifier. Common collector amplifier has high input resistance and low output resistance. CC amplifier has high Rin and low R0. Low R0. So high low, it should have series shunt feedback. It should have series shunt feedback, or what is the other name for series shunt feedback I have given you? Series shunt is also called voltage series. It is also called voltage series. So what is the special case here? You can see input is given to one terminal. The feedback VF is taken at other terminal here, right? Input is given here, but you are taking VF here. But it so happens that your V0 and VF both are same. V0 and VF both are same. Output is taken at this point and the feedback also at the same point. So there are no separate resistors. The load itself is giving you a feedback here. Can you see? This is V. This is ground for AC analysis. But your VF, this is your VB. So what is VB? If current increases, if I0 increases, what will increase? V0. If V0 increases, VF will increase. If VF increases, VB will decrease. If VB decreases, your I0 will decrease and your V0 will decrease. So there is some sort of negative feedback. But how to show that this is series shunt? Because what is VF and V0? VF by V0 is 1. Beta is 1. Beta is 1. So it's kind of little difficult to show. But instead I will try, right? I'm having a transistor here. This is Vs. And here you have Vb. What is Vb here? Vs minus Vf. VF. Beta is 1. So VF and V naught both are same. This is VF and this is V naught. Both are same with respect to ground. And here we have connected this to ground node here. Ground node. Right. This is ground node. This is RE. No. Collector is connected to ground. Collector is connected to ground. But where is RE here? Where is RE? RE is connected from emitter to ground. So I can take this as ground. Let me remove this whole section. Collector is ground. Where is RE? RE is connected from emitter to ground here. RE. So this is ground. No? This is ground. So I can short it here. This is ground. So I can go like this. Okay, I'm just trying to do it, but intuitively you can say that VF, VB or Vin, this is Vin, VB or Vin is going to be Vs minus Vf. This minus indicates what feedback? Negative feedback. This minus indicates negative feedback. This is a special case of a single discrete feedback system. So if somebody asks you, what feedback is there in common collector? You have to say series at input and shunt at output. So series, that means it is a good example of a voltage amplifier or a voltage controlled voltage source. It has high input resistance and low output. Similarly, common base amplifier. What is a special case? Common base amplifier has low input resistance and high output resistance. So common base CB amplifier has low Rin and high R naught. It is a current control current source or current amplifier, shunt series topology. Shunt series topology. But how to prove it? What is common base? In a common base, where is input given? This is a common base amplifier. Input is given at emitter, output is taken at collector. This is a common base amplifier. But in this common base amplifier, there is shunt series feedback. How to show shunt series here? So let me draw it like this. Input is given at emitter. Collector is connected to load RL. And this load is connected to base like this. Okay, right, it can't be better than this. So generally, what is current mixing here? Current mixing, your IS will always be a summation of, what is IS? IS, this is IF, this is IN, right? So your IN is IS minus IF, or IS is equal to IN plus IF, am I right? Then we say it is negative feedback. So this is IS, but this is IF, and this is IN. So by superposition, by KCL, current entering equal to current leaving, IF plus IN is IS, or IN is IS minus IF. This minus indicates negative feedback. Minus indicates negative feedback. So just keep in mind, these two are special cases. Common collector amplifier, emitter follower is a special case of voltage amplifier. It has high input resistance and low output. Common base amplifier is a special case of what amplifier? Current amplifier. It is a special case of a current amplifier or current controlled current source. It has low input resistance and high output resistance. So low high, it is going to be current amplifier. High low, it is going to be voltage amplifier. It is going to be voltage amplifier, right? Keep that in mind. Now I remember I had a friend. We used to buy components, right? Now my friend is definitely a better engineer than me, because if suppose a transistor goes or a sensor goes, I used to replace the same type of sensor, but that fellow will always have a substitute in mind. For example, if op amp is there, if suppose we are using Motorola op amp, if Motorola op amp goes, I used to order for only Motorola op amp, but he used to replace with normal, National Semiconductor LM series, and still the customer is happy with him. So after becoming a lecturer, I realized that if you replace an op amp with any op amp of any make, the gain output is not going to change much. So what he was doing, because the design is important, device is desensitized. Even if you replace a device with another device, the gain is not going to change much, right? So that is something called sensitivity analysis. In fact, you can prove that with calculus. Calculus is so great. You can remove a transistor and put another transistor, but your gain is not going to change. So if you look at the sensitivity analysis, so what happens if I replace a BJT with another BJT, or I replace an op amp with another op amp? Because with negative feedback, AF is A by 1 plus A beta. Am I right? So what happens if I do DAF by DA? What do you mean by this? DAF by DA? The change in the overall gain when the op amp is replaced with another op amp. When A is replaced, when A is changed, when a transistor is replaced with another transistor, when a MOSFET is replaced with another MOSFET, when the gain A changes, what will be the gain in the closed loop feedback system? DAF by DA. Will there be any change in the overall gain? So this is like U by V. You can do 1 plus A beta whole square. So V U dash minus, yeah. So what will happen now? DAF by DA, you can write this as, tell me, 1 plus A beta minus A times of beta, is it not? So what is DAF? It is going to be DA by 1 plus A beta whole square. 1 plus A beta whole square. Now let us divide numerator and denominator by AF. What do you get? DAF by AF equal to DA by AF by 1 plus A beta whole square. But AF is A by 1 plus A beta. It is A by 1 plus A beta divided by 1 plus A beta whole square. So tell me, now we end up getting a very important relation. DAF by DAF equal to DA by A by 1 plus A beta. So what do you mean by this? What do you mean by this? It tells that the percentage change in the overall gain is equal to percentage change in the open loop gain divided by 1 plus A beta. Divided by 1. So what do you mean by that? If there is 50% reduction in the gain, imagine I'm replacing an op-amp from 10 lakhs gain to 5 lakhs gain. From 10 lakhs to 5 lakhs, there is 50% reduction in the gain. The overall change is not going to be 50. It is 50 divided by 1 plus 10 lakhs. What is 50 divided by 1 plus 10 lakhs? 0.00005% change will be there. So that is why op-amp or BJT or MOSFET, the basic amplifier, is completely desensitized. The gain will depend only on the feedback resistors. So that is why it is very important. DAF by AF equal to, tell me, DA by A by 1 plus A beta. Therefore, 1 plus A beta is called the desensitivity factor. Desensitivity. Any improvement in feedback amplifier is by what factor? 1 plus A beta, 1 plus A beta, 1 plus A beta, 1 plus A beta times. So 1 plus A beta is called what factor? Desensitivity factor. Desensitivity. So still if you want with a graph, how we can prove this? Suppose he has an amplifier whose gain is say 10,000, right? 10,000. So the customer is using a gain of 10,000 and suddenly op-amp goes. Somebody like me who go to the customer's place, he want to replace the op-amp with the same op-amp. But my friend, he will replace 10,000 op-amp gain with 5,000. Still the machine will work. Some other day this op-amp also will go. He will replace another with 1,000. Now somebody like me will get worried. Previously it was 10,000. Now you replace op-amp with 5,000 gain. Now again you replace op-amp with 1,000 gain. How is that the amplifier is still working fine, right? How is that the amplifier is still working fine? The amplifier gain AF is A by 1 plus A beta. A by 1 plus A beta. So if for that amplifier the beta resistors is 9K and 1K, then what is the feedback factor beta? 1K by 9K plus 1K. This is going to be 1 by 10. 1 by 10. So what will happen with feedback? With feedback, AF1 equal to 10,000 by 1 plus 10,000 into 1 by 10. Next time AF2 5,000 by 1 plus 5,000 into 1 by 10. What is AF3? 1,000 by 1 plus 1,000 into 1 by 10. Tell me, what is the value here? With feedback, once you give feedback, op-amp, that fellow kept on replacing with some op-amp, from Motorola op-amp to National Semiconductor op-amp, TI, whatever comes to his mind, whatever is there in his tool bag, he has replaced it. But after feedback, is there any change in the performance of the amplifier? What is 10,000 by 1 plus 10,000 into 1 by 10? This is going to be probably 0.999. So you are going to get 0.999 gain. But after that, it is going to be 0.998. It is going to be 0.9975 like that. So I don't know the values. You just calculate the values and tell me. It is again going to be the same 0.998, 0.997. So you can see that the linearity has improved. Linearity has improved by 1 plus A beta. So the distortion has decreased. There is no harmonic distortion here, right? So the linearity has improved 0.998, 0.9975 like that. So the line is almost there only, right? The line is almost there. But the open loop gain is changed. The open loop gain from 10,000 went to 5,000 to 1,000, but the closed loop gain is almost 0.99, 0.99, 0.99, 0.99, right? So linearity is improved. So if you ask me, with negative feedback, what are the advantages? Negative feedback. There is also bandwidth improvement. Yesterday we have done this bandwidth extension. By what factor your bandwidth is getting extended? Tell me. The open loop op amp, yesterday I have given you, do you remember? Open loop op amp had a gain 10 lakhs. Its bandwidth is 10 radians per second. Am I right? 10 radians per second. Now what happened to the closed loop bandwidth? This is bandwidth. What is happening to the closed loop bandwidth here? The closed loop bandwidth, the gain bandwidth product is, gain into bandwidth is 10 power 6 into 10. It is 10 power 7. What is happening if this amplifier is given negative feedback? Is given negative feedback. So the bandwidth with feedback is going to be the bandwidth of the open loop multiplied by 1 plus A beta. If you want, you can check here. Bandwidth of the open loop is how much? 10. DC gain is 10 power 6. Beta you can take 3K, 1K. Beta is 1 by 4. So this is going to be 10 power 7 by 4. Did I not tell you this? After feedback, if the gain reduces to 4, then the bandwidth will increase to 10 power 7 by 4. Yesterday I told you that 10 power 7 by 4 is nothing but a factor 1 plus A beta times. So if the gain falls down to 4, the bandwidth will increase to 10 power 7 by 4, because 10 power 6 into 10 is nothing but 4 into 10 power 7 by 4. So the bandwidth with feedback is going to be the bandwidth of the open loop amplifier multiplied by 1 plus A beta time, because what is beta? 1K by 3K plus 1K. It is going to be 1 by 4. So any improvement in feedback amplifier is by what factor? 1 plus A beta, 1 plus A beta, 1 plus A beta, 1 plus A beta. This factor is called the desensitivity factor. It is called desensitivity factor. It is called desensitivity factor. Okay. So I was told that this is 9.99999. Okay. So the linearity is excellently improved, is it not? The linearity is excellently improved even with feedback. This open loop, this with feedback, the gain is almost going to be constant, right?
Hello, sir.
Yeah.
Hello.
Yes.
Hello. Can you tell me yesterday's doubt? Yesterday's in that I missed in starting.
Yeah, I have not finished here.
Okay.
Sir,
Everyone's here. Is input resistance of the basic amplifier multiplied by 1 plus A beta. This is in series connection. Output resistance of the basic amplifier divided by 1 plus A beta, if it is what connection? Shunt connection. The gain with feedback is going to get divided by 1 plus A beta with negative feedback. Bandwidth with feedback is going to be the bandwidth of the open loop multiplied by 1 plus A beta, such that AF BWF is going to be A into BW. The gain bandwidth product is constant. Because linearity is improved, the distortion with feedback is going to be the distortion divided by 1 plus A beta. Noise with feedback is going to be the noise divided by 1 plus A beta. Percentage change in AF is going to be percentage change in AF divided by 1 plus A beta. So every improvement in feedback amplifier is by what factor? 1 plus A beta, 1 plus A beta, 1 plus A beta, 1 plus A beta times, right? Yeah. Already doubt session is started. Huh? Okay, tell me. So we have come to an end of today's session. Thank you very much for being so patient. And some students are asking in the comment section, sir, what topics we should study?
Hello?
Yeah. See, I told you any subject, 4 or 5 bits will come, right? So only 4 or 5 bits. So if you study DC analysis, if there is a question on DC analysis of BJT, AC analysis he will not give. AC analysis of MOSFET he will give. So device wise you study, that is better. Are you getting? Op amp, right? 1 or 2 bits. Diode, one question will be there. MOSFET, 1 or 2. BJT they might give, they may not give. But if you see the AC analysis of BJT and MOSFET, both look same. Are you getting? So my aim was to see that the student learns the subject. But otherwise 4 bits, honestly speaking, even if you solve my notes, class notes, right? Class notes thoroughly and analyze it. And after that, if you see previous gate questions and our material, that is more than enough for analog, right? Okay, all the best. My best wishes for a bright future, right? You have been so patient all these days. Thank you so much. Thank you so much. I hear so many people, okay, writing good things. Thank you so much. Thank you, Harsha. Thank you so much. I don't know. Harsha was the guy. Whenever I say good morning, he'll say yes. Yes, sir. Right? Very quickly. Harsha, Durgesh, Sai Kumar, Shweta, Sandeep. Yeah, Sandeep, Ranjit, Janapati, Mohit, Devi Kumar. Thank you so much. Thank you. Kartikeya. Yeah.
Hello, sir.
Yes. Aditya. Thank you. Thank
Hello,
you so
sir.
much.
Hello,
You're
sir.
being Thank
Hello,
you.
sir.
Thank you. Yeah.
Hello, sir.
Yes. Tell me.
Yesterday's class, I didn't listen starting, sir. 1 to 4 pages. Starting.
You didn't
Yesterday's.
listen 1 to 4 pages.
1 to.
What is
Yesterday's.
that? What topic is that? You can listen again in the
yesterday.
video, no?
No, sir. I have doubts. I have some doubts, sir. Yesterday.
You doubt, you ask me. What doubt
Okay,
you have?
sir.
Because
Yes.
videos, anyhow, they are uploading. You can watch.
Yes, sir. I'll tell you, sir. Find the CMRR of differential amplifier given.
Yeah.
CMRR.
CMRR
That
is
first problem.
A1 minus A2 by 2 times of A1 plus A2 you have to find.
Yes.
A1 is the gain due to V1 alone when V2 is shorted.
Yes.
A2 is gain due to V2 alone when V1 is shorted.
Once you can open, no, sir, I'll tell which pages I have missed. Due to internet problem, I have missed.
Okay, no problem.
Once you can open.
Yeah, this one.
Yes, sir. This one.
Yeah. What doubt you have?
Yeah, in CMRR, if we don't take if we doesn't have any if we don't take VP and V1, only VP, we can calculate only V0 and V1, no, sir. Without taking
We can
VP.
calculate V0 and V1. Yes, but this voltage division is there, no? You have to draw some Thevenin equivalent for this. Then it will be V1 into 10K by 1K plus 10. There is voltage division, no?
Okay.
Otherwise you do like this. This is V1.
Okay.
There is 1K here. There is 10K here. And there is VP here.
We can take series and we can do it.
They are in series. So same current will flow. You can apply voltage division.
Okay,
If this is R1, this is R2, then this voltage is going to be R2 by R1 plus R2 times of V1.
V1. Yes.
Have you understood now?
Yes, sir. Next page, can you go, sir? Next page. Yes.
Yeah.
Next page.
Yes.
Sir, why we are taking VF, sir? VF directly instead of not taking V2 like that. Why we are taking VF in
It
that?
is VF here. V2 is there. No? V2.
Uh,
V0 by V2 is minus 9K by 1K.
like we are taking series or parallel. This one. These
Which
are
one is series parallel here?
This
Yeah,
one.
you
This
can take this as series, but there is virtual ground here, 0 volts.
okay. You are directly taking to virtual ground.
Then entering current equal to leaving. This is your
Okay.
second class, no?
Yes, sir.
Yeah,
The
yeah.
third class.
Third class. Okay. See, in op-amp section, you solve some questions regarding virtual ground.
Okay.
First 2-3 classes.
Okay,
For
sir.
every day we have done around 30 problems on this.
Okay. Okay, sir.
Okay, if you practice, you will get an idea.
I understood, sir. I'm understanding, but I missed it yesterday due to some
No
internet. I
problem.
missed
No
also.
problem. Yeah, yeah.
Third. Can you do for third page? Third page. Sir, if in gate questions, which topic will come in now? We are in the CMRR fluid. Which questions will come? Today's topic and yesterday's topic.
See, we cannot say, but generally, sometimes he may not give in any of these topic. He will ask you
Okay.
just to calculate voltage and current. What is the output voltage? What is the output current? What is the input resistance? So it must be much simpler. But all these topics are
Okay.
there. In op-amp, only one bit will come, no, yeah? 1 or 2, 1.5 bit. 2 marks, one mark he might give. So there are so many topics,
Okay.
but we cannot say.
Yes, yes, that's why we can only if we know the formula or the knowledge we take, we can let them know, sir.
Yes,
Only
yes,
to
yes, yes.
check every.
No, first you have to practice what has been taught in the class.
Practice
2-3 times.
Okay, sir. Yes, I'll practice. That's what I'm asking.
That is more than enough.
Gate.
If you practice what has been taught in class, then that is more than enough.
Okay. Go to page number 4, sir. Go to page number 4. Sorry for interrupting you.
No problem. Yeah, tell me.
Sir, here it is. Here the resistance are in a series now, sir.
Yes, but with different voltages.
Parallel, if it is in parallel, how we have to take them?
Parallel, they are not in parallel, no, they are in series.
If it is parallel,
Whether it is series or parallel, you can apply KCL. Entering current equal to leaving current, you can apply.
Leaving current.
For adder circuit, subtractor circuit, you can apply KCL. Their resistors will be in parallel. Okay. If you see initial classes, you will understand.
Okay, sir.
Yeah. Okay.
Thank you, sir. Thank you.
Okay, all the best.
Today's class 49.
Hello, sir.
49 F, sir. Today's class.
Yeah.
We have 49 F. Yes, sir. In these MOSFETs and BJT circuits, how are we identifying whether it's a negative feedback system or not?
All the feedback topologies, 4 topologies are for negative feedback only. Positive feedback circuits are different. In positive feedback, 2 transistors should be cross coupled. They are called multivibrators. A transistor like this will be there. The output here has to be fed back to input, and the output is fed back to input here. Such circuits are positive feedback. So we didn't discuss these type of circuits. These are multivibrators. All the feedback topologies, series, shunt series, they are all negative feedback only. How do we know that they are negative feedback? Negative feedback means the increase of output should decrease in the next iteration. I told you many times.
Yes, sir. That I know using this method, but by just looking at the circuits, that's what I want.
By looking at the circuit, suppose this is a transistor circuit.
Yes, sir.
This is V0. Here I have connected like this. First circuit. If V0 increases, your VF will increase. No?
Yes, sir.
If VF increases, your VB will decrease. If VB decreases, V0 will decrease. That's all. Any
So-
circuit is like that. First start from V0. Assume V0 increases. Next iteration, V0 should decrease. All these circuits which we have done today, they are like that.
So all the circuits that we have done till now.
They are negative feedback.
mostly-
One example I have already given you.
Yes, sir.
I'll show you one more. Yeah, can you see here? V0 has increased.
Yes, sir.
VF has increased. VD has decreased. V0 will decrease. Similarly, V0 increases. VF will increase here. VB will decrease. Yeah, V0 will decrease.
Correct. So 58F.
Yeah.
Yes, so in here, what is RID actually? I didn't.
RID is the input resistance of the op amp. Op amp's input resistance.
So what is it called? Why is it written RID there? I don't.
It is RID stands for the differential input resistance. A resistance between the two terminals V1 and V2 is called
Okay.
differential input resistance.
Because it's taken between the two terminals. That's why.
Yeah. Otherwise, generally it is RID only. It is RID. But because it is between the two terminals, we call it RID.
हाँ
Okay. And sir, if it's
क्या हुआ?
if a
वो
resistor is
फोटो ले लो
attached,
पूछ भी क्या क्या कैसा रहता
Huh?
पहले
sir, if a
मेरे को
resistor
लाके
is attached in parallel, so this noise is coming from somewhere.
हाँ
Yeah. We'll wait.
So
Yeah.
if a resistor is attached in parallel or series with it, then we'll calculate it by using this old method that we have already.
Yeah,
No.
this simple input resistance you can multiply by 1 plus A beta or divide by 1 plus. Yeah, it's an old method. Connect a voltage source, find current, no? That is enough.
Okay.
You just connect one voltage source, find current. That is input resistance only. But this the topic is feedback amplifier, no? That is why I have bought every calculation under one ground. What is that common ground? 1 plus A beta times. Any improvement in feedback amplifier is by 1 plus A beta, 1 plus A beta times.
So what I'm asking is, if a series resistance was connected in before RID, in
Yeah.
this, yeah. So
Still input resistance is same. Because
See-
input resistance is always removing RS. Output resistance is always removing RL.
okay, I got
Input
it.
resistance, always you should remove RS. Output resistance, always you should remove RL.
Okay, and so 59F. So 60F, sorry. Yes, sir. So how are we doing this type of feedback?
The feedback means you are feeding it back. The feedback name comes from the output to input. Topology name comes from the input to output.
Okay, so the type of output we are taking on that.
What your output is in voltage, input is in voltage, voltage to voltage.
Okay.
Here output is in current, input is in voltage. So it is current to voltage.
Current too. Okay. And so in that special cases that we took, why are they special cases?
Because common collector amplifier is a special case of single discrete feedback system within the device. Generally, in all the feedback system, we had one big amplifier and few resistors. Yes or no? But in common collector, only device is there. That's all. Device load, but still it is
Okay.
giving you series shunt.
Okay.
Common base, device load. Still there is a feedback going on within the device.
Okay.
Within the device. Can you see what is
Yes,
beta
sir.
here? Only wire is there. Only wire. Beta is 1.
Yes, sir. Okay.
Yeah.
And sir, I wanted to ask, is there any study plan that we should follow for analog? What should we study first and then?
You should practice questions in op amp, few diode problems, MOSFET, little BJT. Device wise you study 4 devices.
Okay.
BJT problems you can practice. What you will study in op amp? Calculation of output voltage, input resistance calculations, And the last thing is tau and bandwidth. I told you amplifier has
Yes, sir.
only 3 things.
4.
Yeah, 4 rather. Calculation of gains, calculation of R in R naught, calculation of tau and bandwidth.
Tau and bandwidth. Yeah.
Only these calculations you have to do in what you call
Op-amp.
op-amp. Then you come to BJT, same thing. DC analysis. In AC analysis, calculation of gain, calculation of input-output resistance, and tau and bandwidth.
Yes, sir.
MOSFET also same.
Okay.
Diode circuits, topics are clippers, clampers, peak detectors, rectifiers.
Okay.
And then you can combine op-amp with them. This is more than enough.
Okay.
This tau
First,
bandwidth
this
calculation and the
Yes, sir.
diode problems, if you do, is more than enough.
Okay. Okay. Thank you so much, sir. I really enjoyed your classes. You have been very.
Thank you, thank you, thank you. Pleasure.
Thank
Sir,
you.
39F,
Yeah.
sir.
What?
Sir, 39F. Sir, while determining the type of the topologies, we were told about some short tricks, no, sir?
Yeah, recognition. Same
sir.
terminal, shunt. Different terminal,
Sir,
it is
could you
series.
explain that trick in this problem, sir? Once I couldn't get it, that implementation of that short trick. In the problem, sir. Yeah. This one only is 39F.
This one only, no?
Yeah,
Recognition
39F.
of topology.
No, sir. I'm saying implementation of this in the problem, sir.
See,
problem.
the first problem was this. Okay. The second problem was this. The second one. Which one? Which problem do you want? First or
39.
second?
39F.
Yeah, this is the first problem.
Yes,
So
sir.
in first problem, input is given here. Feedback is taken here. Different. Then naturally it is series. Or you can take a line like this. Can you see a dotted line?
Yes, sir.
No, this is series only, no?
Okay.
Yes or no?
Okay. Sir, in the next problem. Okay.
In the next, input is given to one terminal, feedback also from the same terminal. Same terminal.
Sir, feedback means resistors other than loads.
Yes, feedback means a resistor other than the load.
Okay.
You're right.
Okay. Thank you very much, sir.
Yeah.
Thank you very much.
Good luck.
52F, sir.
So,
Thank you very much, sir.
Yeah.
sir,
Hello, sir. 52F. Sir, here I didn't understand, sir, taking current.
Taking?
This logic I didn't get, sir.
Yeah, see, if I want to give current, no, I cannot take current in shunt. I have to take current in series because same current is flowing, no? I have to
Yes, sir.
redirect this current here. This is taking current. But when you are giving in series, it has to be voltage because this is VF, this is VB, and this is VS. So VN equal to VS minus VF. See, it's simple. Try giving a voltage division in shunt. In shunt, can you give voltage? Already voltage will be same, no? What is that you will give?
Yes, sir. Yes, sir.
You cannot give. Similarly, current, I want to give in current division. What if you give in series current? Same current will already flow. Where is that you are giving? For voltage division to happen, they should be in series, no?
Yes,
For
sir.
current division, it should be in shunt. So while giving current, voltage means series, current means shunt.
Shunt.
Why?
Opposite.
Why? Because if it's the other way around, you cannot give.
Yes,
You
sir.
cannot give voltage in shunt at the input side because already in shunt all voltages will be same.
Same. Yes, sir.
Yeah. Are you getting?
Thanks for teaching, sir. Thank you so much.
Yeah. Good luck. All the best.
Thank you,
we are
sir.
considering, sir,
Yes.
so we're considering A to be large, no? Like
Yeah.
the
A
gate.
is very large.
So if we take A as one, like the gate examiner is very smart. Sometimes he will give A equal to small value like 5. Then will
Yes,
this
yes, yes.
all will work?
Yes, A
So,
is small.
in that
If
case,
A
what
is
should we do?
small, virtual short you cannot apply.
Yes, sir.
You cannot apply these
Then if we
negative
can,
feedback tricks. Same voltage at non-inverting is equal to voltage at inverting, you cannot apply. Then if at all you want to calculate input resistance, use Ohm's law directly, V by I. Apply voltage, find
that
current.
KCL,
Switch off.
KVL.
KCL, KVL.
Okay, sir. Thank you so much, sir.
Yeah,
It
yeah,
was
yeah.
really great understanding everything.
Thank
so
you,
much.
thank you. Pleasure.
Sir,
Just a
Yes.
small doubt. In yesterday's class, while we are solving some problems starting of oscillators, when LC circuits are LNC are in parallel, we are considering it as open, and LC are in series, we are
That is
considering.
resonance condition, because an oscillator will select only one frequency. That frequency is the resonant frequency. So in networks class, you will study that whenever you have a parallel LC circuit, it is going to offer high impedance at resonance. Whenever there is a series LC circuit, it is going to offer low impedance at resonance. That is a condition you will study in networks. That condition I applied here.
It is not the same in RC or RL.
No, RC or RL, no.
Okay.
For RC, there have to be two RC networks, no? Two
Yes.
RC networks should be there, not one LC, two RC.
Okay,
Here
sir.
it
Thank
is only one LC network, that risk you can take.
Yes, sir.
Yeah.
Thank you, sir.
Yeah.
hello, sir. Sir, 14 up, sir. Hello,
Yeah.
14 up. Not this, sir, actually. 13, I think. We are giving stabilization, man.
Yeah.
Sir, actually, we should use stabilization to positive feedback, no, sir.
Stabilization to?
Positive
This is
feedback.
positive feedback only. No, V0 increases, VF will increase. VF increases, V0 increases. This positive feedback oscillator. But to amplitude, to stabilize the amplitude, these resistors somehow they are giving a negative feedback only for V0, only for V0 amplitude. See, if suppose the Zenars are off, it is as good as any oscillator, no? If the Zenars are off, why the Zenars will come into picture? If V0 increases more than 7 volts, then the Zenar will come into picture. Are you getting?
Yes, sir. Actually, here in positive terminal, we are given ground, no, sir. That's
Positive
why
terminal we are given ground. Yes.
positive feedback means we have to give from positive terminal, no, sir.
Acha, see, there are two feedbacks. One is you are talking about VD. If this increases, this will increase, this will decrease. With respect to VD, if you talk, it is negative feedback only. But with respect to V0 and VF, if you talk, it is positive feedback. Oscillator is with respect to V0 and VF, not with respect to V0 and VD.
Okay.
You are talking about this one, no? This op-amp feedback. This is not oscillator. This is oscillator.
Yes, sir. If in oscillator, how we can tell that negative feedback and positive feedback difference, sir?
Only positive feedback is there in oscillator. V0 increases, VF increase. VF increase, V0 increase. Positive feedback.
Okay.
Every oscillator is like that, yeah. It's not only this. You take any RC phase shift, any oscillator, in this loop, if V0 increases, this will increase, again V0 will increase. In any loop, it is positive feedback only.
Are
Are you getting?
Yes, sir.
See, a logic, anything implemented in a loop, anything implemented just in a loop is positive feedback.
Okay, sir.
There is a loop, lot of components in that loop means it is positive feedback only. But if you have a mixer, that Arey yaar, disturbance is coming.
Yes, sir. No disturbance.
So much of disturbance, sir.
Hello.
Sir, can you tell again, sir?
See, if you draw one circle, that is called a loop. In
Yes,
that
sir.
loop, if you put components, it is positive
Arey ruka
feedback.
me.
But if you have a mixer like an op amp or a BJT, To base terminal you are giving, feedback you are giving to
Look,
emitting
cut में तो तू है ना
terminal is changing. Then it is negative feedback. Directly in all oscillators, what we are doing, one amplifier again give it to when output is fed to input and output is again fed to another input, output is fed back to another input, back to, then it is positive. Are you getting?
Can you tell once again, sir? I got confused.
See, last circuit, I will tell you, last circuit we have done. Do you remember?
Sir.
Last circuit, can you see here?
Yes, sir.
What? See, here Vy is there, Vx is there, Vz is there, V0 is there. This is like this: A1, A2, A3, and then feedback. That means if this increases Vx, Vy will increase. If Vy, then Vz. Vz again Vx. So if one increases, the other will increase, no? But what you are doing in your mind is, you are opening this dabba A1, and inside you are finding one op-amp with negative feedback. So oscillator is a positive feedback system implemented with many linear negative feedback amplifiers. Your negative feedback is with respect to Vd inside that op-amp. Why are you focusing on Vd when my loop is so big? See, there are 3 small loops here. One loop for here, one loop here, one loop here, one loop here. This is not oscillator. Oscillator is this, no? From here to here you have to come. Within that op-amp, if you see, it is negative feedback only. That means if you remove only one op-amp section and put in your pocket, then it is an amplifier. It is not an oscillator. It is having negative feedback. 3 amplifiers you have to connect in a loop. That loop is said to be positive feedback. Because when something increases, Vx increase, then your Vy will increase. Vy increases, Vz will increase. Are you getting? So how many control systems are here? One big control system with Vx, Vy, Vz, and 3 small control systems within the Vd, within Vd, Vy, within Vz, Vd here. There are 3. This is not that is why amplifier itself you have to take it as a block. When you take it as a block, can you see negative feedback in this?
No, sir.
You should not. Inside it will be linear amplifier. Why are you worried about inside? This is oscillator, no? Outer loop.
Sir, and yesterday you told the feedback amplifier is the worst, no, sir? Actually.
Before compensation. Yes, op-amp, if you don't compensate, it is worst only, no?
Yes, sir.
Now an op-amp is ready. It is been compensated. Now you can use it for amplifier, oscillator, switch, anything you want, Schmitt trigger, triangular wave generator, RAM generator, anything you want, you can implement.
Okay.
The IC
Sir,
is ready. IC itself is not going to oscillate. Oscillation is only by external RC components.
Okay, sir.
By external RC, you can make amplifier, you can make oscillator, you can make switch, but op-amp is stable now. You are using a stable IC. Are you getting?
Yes, sir. Sir, and you have stopped suddenly, no, sir, last topic. Is there any continuation or we are asking doubts, so you stopped?
Which one today?
Yes, sir.
No. I was summarizing, but after summarizing, what is there? Suddenly people started talking. I don't know. I have written the summary, no? That is in fact the end of the class.
Okay. Sir, you teacher wonderfully, sir. Thank you very much.
Yeah. Thank you. It's my pleasure. My best wishes for your future.
Thank you, sir.
Hello,
Yeah.
sir.
Yes.
Hello, sir. Good evening, sir. Can you go to 53F, sir?
Yeah.
Sir, it should be series shunt, na, sir.
Shunt. Same terminal if you connect, it is shunt.
No,
Output
sir,
is in series.
logic, na, sir.
Logic says that at whatever terminal you give input, same terminal if you connect, it is shunt.
No, sir. You told one logic 52 page number.
Which page number?
52.
Sir,
you're taking current in series and giving current in shunt, na, sir.
Yes.
So
So you can, yes, you can call this as current series also.
we need to write first giving and then taking, sir.
No. Taking to giving if it is voltage and currents. Topology you can write series shunt, series from input to output. I have given you both conditions, no? Both I have given. See. Yeah, this one. Can you see here?
Sir.
This is the topology from input to output. Feedback is from taking to giving. Here, can you see here?
Sir.
This is voltage series from output to input. Current shunt, output to input. Current series, output to input. Topology is series, shunt series here, shunt here.
We can blindly input.
Topology is from input to output. Feedback is from output to input.
Sir, another dot, sir, 12.
Yeah.
12 F.
Yeah.
Sir, you said here -9 is decreasing, sir, but it is increasing now, sir. -10 to -9 means. So gain increasing now, sir.
No. Magnitude of gain, slope. -9 because input is given to inverting terminal. Gain is 9 only, no?
Okay, sir.
9. Gain is 9.
Sir, why Zener in breakdown acts as a voltage regulator, sir? Why not a diode, sir?
See, that is internal construction we have to see.
Okay, sir.
In EDC, you would have studied, no?
Sir.
Yeah.
Sir, thank you very much, sir.
Yeah. Good luck. My best wishes.
Sir, can you give your mail ID, sir?
Yeah. EU_Kiran.
Sir?
EU_Kiran. KIRAN @yahoo.com.
EU?
EU_Kiran.
One second, sir.
Once you written, sir.
EU_Kiran.
I'll better write.
Yes, sir.
Yes, sir. Right up.
Yeah, this is my phone number.
Appropriate time for contacting you, sir.
Sir.
Yeah.
51 it.
51.
Yes, sir.
रुक रहे एक सेकंड सर वन सर हेलो
Yes.
Sir, it
Hello,
means
hello.
GM equal to how
Hello,
you
hello.
calculate, not understand. I not by views.
GM is the ratio between current and voltage, no? Output current to input voltage. You can apply current division formula there.
I not equal to.
IX equal to I naught into R1 by R1 plus R2 plus R3.
Sir, this circuit only, sir. I not R1 plus R2 plus R3.
What is the relation between IX and I naught? IX is I naught into R1 by R1 plus R2 plus R3. Current division formula.
Okay. Sir, last VO by VS equal to minus RCGM also.
What?
VO by VS minus RCGM.
Yeah, some student in the comment section, he asked, sir, what if they ask voltage gain? Voltage gain, if they ask, means you have to include resistor, no? There is a resistor here, RC. Can you see RC here?
I see.
So if this is ground, this is V0. What is I naught? V0 is going to be 0 minus V0 by RC. Or I naught by V0 is minus RC. V0 by I naught is minus RC.
Okay.
That RC we have included.
తర్వాత మళ్ళీ కాల్ అందరికి యాడ్ చేస్తూ పోయింది అలా. సరే అందరూ చెప్తున్నా.
Okay.
29. Sir, 59. 59.
Yeah.
Sir, in this Rn equal to Rd.
Rn equal to?
Rd 10.1046.
Into 1 plus A beta, yes. Input resistance, wherever there is series topology, input resistance should be multiplied by 1 plus A beta, I told you, no? Output resistance should be divided by 1 plus A beta. Can you see this formula here? Star?
Yes, sir.
This formula we are applying here.
ROF equal to R0 by 1 plus A beta.
Wherever there is shunt resistance, can you see this table? For series, input resistance should increase. For shunt, resistance should decrease. That's all.
Okay. Thanks.
Yeah. All the best.
29. 29.
Yeah.
Sir, could you explain the VCO function, sir? I lost my connection.
See, VCO, I was just, I didn't explain much because VCO is a very big concept. I was just explaining them the analogy of a Formula 1 race, or even if two friends are there who are going on a bike. Two friends who are going on a bike on two different bikes. They are going at the same speed. How do they know they are going at the same speed? Because the distance between them is same, no? So that analogy I applied here. I said two frequencies are same. Two signals have the same frequency. Number of cycles per second of two signals is same, Fin and Fr, only when the phase difference between them is 0. So for a PLL to track frequency, the phase error, what is there? The phase detector you need, and you have to make the phase detector output 0. But when you are doing amplitude tracking, which is amplifier, your VD should be 0, I told you. If your VD is 0, you will have virtual ground, no? Vs equal to Vf. Yes, or no? So here, Fin should be equal to Fr. For every 1 and 1 cycle of Fin, there should be one and only one cycle of Fr. That will happen only when the phase error, the distance between the two are 0. The phase error is 0. So we need a phase detector. Low pass filter purpose is to eliminate noise. Gain state should be there, and a VCO. VCO, what VCO will do? It will convert the voltage into frequency.
Sir, 49. Yes, sir. 40 FC.
Yeah, 40.
40 F.
Yeah.
Sir, we have to assume while solving the op-amp BJT MOS for this. These are the conditions, sir.
Yeah. Virtual ground conditions you are applying even for BJT and MOSFET now. Because wherever the loop gain is high, the voltage at non-inverting will appear as voltage at inverting, right? The errors between the two terminals will converge. The same thing with BJT also. If you give negative feedback, like how in op-amp VD is 0, here VB will be 0.
Sir, virtual ground is applied only when there is a infinite
feedback. When there is negative feedback and there is high gain.
Okay, sir. Thank you, sir.
Yeah, all the best. Yeah.
Sir? Hello?
Yes.
Sir, appropriate times of when we can call for the doubts, sir?
Yeah, you can give me a WhatsApp. I will respond, or you can give me a call anytime. No problem.
Hello, sir.
Yes.
Sir, actually, you have explained a positive and negative feedback, right, sir? Hello?
Yes.
Sir, in only differential amplifier, we will get positive feedback, sir.
No. Positive feedback circuits in BJT, you have to take two transistors cross coupled. Then you will get multi vibrators, square wave generators, and all that. We have not done positive feedback with BJT and MOSFET. All the 4 topologies are for negative feedback only.
Okay. Sir.
Yeah.
And op-amps are basically negative feedback only, right, sir?
All are negative feedback structures, but positive feedback means only Schmitt trigger circuit.
Okay, sir.
Yeah.
Sir, and sir, I'm getting confused between mixing and sampling, sir. Can you please explain once again?
Mixing is input side, sampling is at the output side. Same terminal means it is shunt topology. Different terminal, it is series topology.
Okay, those names
topology, you should not see the BJT or MOSFET. You should only see the feedback resistor and the source. If the source is given to some terminal and the feedback resistor is also taken from the same terminal, it is shunt. Don't see BJT MOSFET, not the device. Only the source and the feedback resistor. Similarly, at load, if the load is connected to some place and the feedback is taken from the same place. For example, in this circuit, the load is connected at this point A. Am I right?
Yes, sir.
Feedback is taken from the same point. It is shunt only. Input side. Source is given to some point. Feedback resistor R1 is at some other point. Some other means series. Don't see MOSFET. Just see source and the feedback. Load and the feedback.
Okay.
Are you getting? If you see BJT MOSFET, you will get confused. Don't see BJT. The feedback is only between source and the resistors, load and the resistors.
Okay, sir. Got it, sir.
Yeah.
And 53, sir, page 1.
Yes.
53. Hello, sir.
Yes.
Page number 53, sir.
53.
Yes, sir.
Yeah.
Sir, here in the right side diagram, sir, how we will get to know that current is flowing, sir?
We don't know, but you can apply KCL, entering equal to leaving.
Okay.
Now, the entering current has to leave into 2 parts, no?
Yes, sir.
But IG is 0. Where it will go?
It will go towards the load.
That's all.
Okay. Sir.
Apply KCL. KCL will tell you.
Okay, sir. And sir, in some problems, we will short VP and VN, sir, and connect to voltage source.
VP and VN?
We will short and we will connect the voltage source. Hello, sir.
Disturbance is there. VP, VN?
Yes, sir. Sir, for inverting and non-inverting terminal, we short and connect the voltage source, sir. For that same thing, sir, this series and shunt, same thing we need to apply.
Yes.
It was where we are shorting, right, sir? Then how we will find the input, sir, there?
Where we are shorting, I'm not understanding.
Inverting and non-inverting terminal, we will short, sir.
Don't short. They are virtually at the same potential.
Okay.
Why do you want to short?
Okay, sir. And 56, sir. Sir, here Rin basic amplifier formula is Vin by In, right, sir?
Vin by In, yes.
And if we are substituting Vin in that formula, sir, then Vin is Vs by 1 plus A beta, sir.
Vin is Vs by 1 plus A beta. Okay.
Then here in formula, you have substituted Vin into 1 plus A beta.
Vin into
1 plus A beta.
అదే అదే
You are saying V in is Vs by 1 plus A beta.
Yes, sir.
దాన్ని బట్టి మనం ఏమైనా మాట్లాడాలన్నా ఆలోచించి మాట్లాడాల్సి వస్తుంది.
Not getting one. Acha, you are saying that Vs. What is Vs? The relationship between Vs and Vin is Vs is Vin into 1 plus A beta. Vs. Vs is large, no? Vin is small. You are right.
Yes, sir.
Vs is large. Vs is Vin into 1 plus A beta. And Vin is Vs by 1 plus A beta. Correct only?
Yes, sir. In Rin basic amplifier formula, sir, we need to substitute V.
Not R in basic amplifier formula. R in with feedback we want.
Okay.
We want R in with feedback. No, why you want to substitute at the R in basic amplifier? I am giving you. R in with feedback you have to find.
Okay, sir. Okay, sir. Got it, sir.
Okay.
Hello, good evening, sir.
Sir, and last doubt, sir. Last doubt, 66, sir.
మనం మళ్ళీ కనెక్ట్ అవుదాం, అడుగుదాం.
There is disturbance backgrounds.
Yeah.
Sir, can you please explain this?
See, even if the gain changes, open loop gain changes, closed loop gain is not changing. That is only the difference. Because 1000 by 1 plus 1000 into 1 by 10, 5000 by 1 plus 5000 into 1 by 10 is almost 10 only. It is almost 10. It's not 0.99, it is 9.99.
Okay, sir.
It's almost 10.
Sir, the sensitivity, what we will study in control system, same thing, right, sir? Here.
Same thing.
Okay. For transfer function and all, same thing.
Yes. Same thing.
And sir, in analog, basically the starting, whatever the main concept, that only they last, right, sir?
Only those things, yes.
Gain and frequency range.
Yes. Input and output resistance, tau and pi.
Sir, your teaching is very awesome, sir. Thank you, sir.
Thank you so much, yeah. It's really a pleasure to know.
Hello, sir. Thank you.
Hello, good evening, sir.
Yes.
Sir, I had a doubt. Like, was there? Like you told for an oscillator, it is a phase compensating circuit, no, sir?
Yeah.
And in all pass filter, we studied that it is a phase compensation filter. So there can be any connection, means like all pass filter can be used in feedback or something for phase compensation.
Yeah. See, there in all pass filter there is no feedback, no. Only input and output. And you already know how much you have to compensate in all pass filter. Suppose accordingly you will adjust the value of R and C.
Yes,
all pass filter phase compensation when you are designing, suppose you want 152 degrees compensation, accordingly you will adjust the value of R and C, no? Okay, but in oscillator there is no adjustment. Anything that the basic amplifier gives a phase lag, the compensation should automatically come from the beta network.
Okay.
So it is self-correcting. Oscillator is self-correcting. But in all pass filter you have to adjust R and C for phase.
Okay. Yes, sir. Here no input, nothing output is there.
It is advanced oscillator. You switch on, it will do on its own.
Okay, sir. Sir, second part is the 39F. Could you open, sir, once?
39F.
Yes, sir.
Yeah.
Sir, it's like means like a minor thing. Like here you have mentioned the type of feedback we need to check and approximately you have given V0 by Vs. So this signifies that it is a voltage amplifier. So sir, means like in exam it is given like this, then do we need to find or direct we can say that V0 by Vs it is asked, then it will be voltage amplifier on PCBS. Sir, lot of noise is there, sir. Sir, now
who are these people shouting here?
Sir, they have unmuted and they are not muting themselves, sir.
Acha, after unmuting, they are not muting.
That only, sir. That is the issue. Means from their side the sound is coming. That is the issue.
Acha, after class is over, they are just they are not switching it off.
No, sir. That is the issue.
Acha. So okay. some special effects.
Yes, sir.
Hello,
Yeah.
sir. Sir, I just wanted to say
Hello,
this,
sir.
like,
खुला नहीं लगती है,
exam
सीधा अंदर बंद कर दो। कैसा खुलता है वहाँ? अब खोली नहीं तो क्या है तभी? कितना बार डालता हूँ?
Are you on a video? Then we can know who is shouting, sir.
Sir, अभी
Yes,
you can first में unmute से sir
we
कर
will know, sir. We
ask
will know who
student
is shouting, sir. You can say his name.
Yeah, who is that person?
Sir, you
Sir,
turn on your video,
turn
you
on
will
the
get to see
video,
his
sir.
name, sir.
Yes, sir.
Sir, please turn on your video, sir.
My video.
Yes, sir. Then you can.
Yes, sir. Then you can see her name.
Sir, it is H.G. Giri Pravan someone, sir.
Yes, sir.
Yes, sir.
Hey, it's not mine. Just now I turned on my
Some
microphone.
educated
Someone it is, sir.
Okay, last class we are having fun, no problem.
Sir, just a minor doubt, sir. You hear, sir. Sir, means like in this question you mentioned approximate gain is V0 by Vs we need to find, and you asked the type of feedback. So
Yeah.
here by seeing the circuit only means V0 by Vs is asked, then we can directly tell that is it a VCVS, sir. Means
Yes,
like
yes.
voltage amplifier.
Yes.
Sir, then we don't need to solve in exam if like this it comes.
No. Don't. The examiner generally in these type of questions, he is asking only topology. He is not even asking gain.
Okay.
Feedback amplifier means topology. If you recognize means enough.
Okay,
But,
sir. Okay.
yeah.
Thank you, sir. Sir, your teaching helped my fear to vanish, sir, in analog electronics. Thank you, sir.
Good luck.
Thank you, sir. Thank you.
Yeah, yeah.
Sir, 12 left.
Can you say Nabi
Hello?
talking to
Sir, 12 left.
Yeah. 12F. Tell me.
Sir, can you explain Zener diode? When Zener diode is on, what is the how we
Yeah,
go?
see, if V0 rises above 7 volts, if it rises above 7 volts, then the diode is going to get on now.
Yes.
Excuse me.
Okay.
You have two diodes here.
Yes,
So what
sir.
happens if two diodes are connected back to back? If the current flows like this, upper diode will give 0.7, lower diode will give 6.3. Total is going
Yes,
to be
sir.
7 volts. Yes, sir? So once this
Yes,
output touches 7 volt, the Zener gets on. But when the Zener gets
Yes.
on, the next iteration, the gain is less. Otherwise, V0 was always experiencing a gain of 10. Now it will experience a gain of 9. So in this loop, this signal at the input goes here. So in next iteration, when V0 appears, the gain is going to be less. So your signal once it touches 7, next it is going to go 6.9.
Yes, sir. Yes, sir.
Once it decreases, again the Zener becomes off. If the Zener becomes off, again the gain is 10. So loop gain is 1. So a nicely stable oscillation you will get.
Yes, sir. Sir,
See, something like
Please say them to unmute. Don't talk, sir. Very noisy, sir.
Yeah.
Thank you. Hello, sir. Good evening, sir.
hello.
Good evening.
సార్ ఈ
Hello.
సార్ గుడ్ ఈవినింగ్ సార్. ఈ మనము ఇప్పుడు ఈ ఫీడ్బ్యాక్ టోపాలజీ ఐడెంటిఫై చేసేటప్పుడు ఒకవేళ అక్కడ కరెంట్ అవుట్పుట్ దగ్గర అయినట్టు అలా చూసుకోకుండా డైరెక్ట్ మనం ఇట్లా ఈ గీయాల్సిందేనా సార్ ఈ బొమ్మ అంటే ఇట్లా ఫీడ్బ్యాక్
గీయడం ఒక పద్ధతి, ఇంకో పద్ధతి చూసి చెప్పడం ఏంటంటే యాంప్లిఫైర్ డివైస్ ని చూడకూడదు, మీరు సోర్స్ ని ఫీడ్బ్యాక్ రెసిస్టర్ చూడాలి. సోర్స్ ఏ టెర్మినల్ కి అయితే కనెక్ట్ అయిందో ఫీడ్బ్యాక్ అదే టెర్మినల్. See, terminal means there are only two terminals, base and emitter. No?
Yes, sir.
If source is given to base, feedback is taken from base. It is shunt.
Shunt.
If source is given at base, feedback is taken at emitter, series. If
Sir,
source is given at emitter, feedback is taken from emitter, shunt. If source is given at emitter, feedback is taken from base, series.
సార్ ఈ మనం మిక్సింగ్ అండ్ శాంప్లింగ్ మనం ఎక్కడ వాడలేదు సార్. జస్ట్ ఈ టర్మ్స్ మనకు అంత అవసరం లేదా సార్. మామూలుగా మిక్సింగ్ అంటే ఇన్పుట్ సైడ్, శాంప్లింగ్ అంటే అవుట్ సైడ్.
మిక్సింగ్ అంటే ఇన్పుట్ సైడ్, అవుట్ శాంప్లింగ్ అంటే అవుట్పుట్ సైడ్.
ఒకవేళ మనం వాటిలో రాయాలంటే ఎలా సార్? కరెంట్ మిక్సింగ్, వోల్టేజ్ అంటే అలా ఏమి ఉండదా సార్?
మీకు లిస్ట్ ఇచ్చా కదా నేను. మీకు సిరీస్ షంట్ అంటే వోల్టేజ్ కంట్రోల్ వోల్టేజ్ సోర్స్, అప్పుడు రివర్స్ లో రాయాలి అంటే మీరు ఏం రాస్తారు? వోల్టేజ్ టు వోల్టేజ్ అన్నా వోల్టేజ్ సిరీస్ అన్నా రాయాలని చెప్పాను.
లేదు సార్, మనం శాంప్లింగ్ మిక్సింగ్ అని వాడలేదు కదా సార్ టర్మ్స్. అందుకని
ఇన్పుట్ లో ఉన్నది వోల్టేజ్. ఇప్పుడు వోల్టేజ్ కంట్రోల్ వోల్టేజ్ సోర్స్ బదులు వోల్టేజ్ మిక్సింగ్ వోల్టేజ్ శాంప్లింగ్ అని చెప్పి అయిపోయింది కదా.
ఓకే సార్, ఓకే సార్. సార్ ఇంకొకటి సార్, మనము ఈ ఇన్పుట్ ఇంపిడెన్స్ కనుక్కునేటప్పుడు మనం ఎక్కడ ఆర్ఎస్ అనేది కనుక్కోలేదు సార్. ఈ ఆర్ఎస్ ఇన్వాల్వ్ చేయలేదు సార్. అంటే ఇన్పుట్ ఇంపిడెన్స్
ఆర్ఎస్ ఎప్పుడు ఇన్పుట్ రెసిస్టెన్స్ కి ఇన్వాల్వ్ అవ్వదు. ఆర్ఎల్ ఎప్పుడు అవుట్పుట్ రెసిస్టెన్స్ కి ఇన్వాల్వ్ అవ్వదు.
కానీ వోల్టేజ్ అయినప్పుడు మాత్రం మనం ఆర్ఎస్ కన్సిడర్ చేసుకోవాలి.
అంటే V0 అంటే వాడు ఏమి ఇస్తాడు? V0 బై Vin ఇస్తే V0 బై Vs ఇస్తే Vs, అప్పుడు సోర్స్ కూడా వస్తుంది.
ఓకే సార్. సో అంటే మనం అక్కడ యారో మెన్షన్ చేస్తూ దాని ప్రకారం మనం
దాన్ని బట్టే కదా ఇన్పుట్. ఇప్పుడు ఇన్పుట్ రెసిస్టెన్స్ ఆఫ్ యాంప్లిఫైర్ అంటాడు. యాంప్లిఫైర్ అన్నప్పుడు ఈ సోర్స్ పని ఏముంది?
ఓకే ఓకే. ఇన్పుట్ రెసిస్టెన్స్ ఆఫ్ యాంప్లిఫైర్ అన్నప్పుడు ఓన్లీ మనం యాంప్లిఫైర్ ఈ సోర్స్ పార్ట్ ని తీసేసి మనం ఓన్లీ యాంప్లిఫైర్.
అవుట్పుట్ రెసిస్టెన్స్ ఆఫ్ యాంప్లిఫైర్ అంటే లోడ్ ని తీసేసి చూడాలి.
మరి ఇప్పుడు మనం ఎప్పుడు లోడ్ ఈ కన్సెప్ట్ ఓకే ఓకే ఎప్పుడైనా సరే అవుట్పుట్ రెసిస్టెన్స్ అంటే లోడ్ అనేది మనకి
లోడ్ తీసేయాలి, ఆర్ఎల్ తీసేయాలి. నేను అన్ని ఆర్సీలు ఇచ్చాను కాబట్టి ఇంక్లూడ్ చేసాం మనము. కానీ ఆర్ఎల్ అనేది నెక్స్ట్ లోడ్ ఇస్తే అప్పుడు ఆ లోడ్ తీసేసి చూడాలి.
సార్ ఇంకొకటి సార్, ఈ మనకి ఆసిలేటర్స్ ఈ ఫార్ములాస్ ఏమి గుర్తు పెట్టుకోవాల్సిన అవసరం లేదు కదా సార్. మనకి ఏది
ఏం లేదు, వాడు ఏదో ఒక చిన్న ఆసిలేటర్ ఇస్తాడు, R2 R1 రిలేషన్ అట్లా ఒకవేళ ఇస్తే
జస్ట్ VCO అన్ని కూడా మనకి జస్ట్ అనాలిసిస్ పర్పస్ కానీ మనం ఇక్కడ
ఎందుకంటే టాపిక్ లో ఉన్నాయి కాబట్టి చెప్పాము.
ఓకే సార్.
మనకి జనరల్ గా ఎగ్జామ్ లో ఆ వోల్టేజ్ కట్టు, గెయిన్ కట్టు, ఇన్పుట్ రెసిస్టెన్స్ కట్టు ఇవే ఉంటాయి.
ఈ బీజేటీ సార్, ఈ బీజేటీ లో కూడా మనకి గేట్ ప్రీవియస్ లో కూడా ఎక్కడ కూడా మనకి చేసి అడగలేదు సార్. అంటే
అంత సీనే లేదు. అవును, కానీ మనం భయంకరంగా చేసాము, చాలా ఎక్కువ.
లేదు సార్, దానివల్ల చాలా హెల్ప్ఫుల్ అయింది సార్ మాకు. సర్క్యూట్ చూడడం అప్పుడు భయపడేవాళ్ళం సార్. ఇప్పుడు చాలా
నాకే ఏంటంటే అప్పుడప్పుడు కొద్దిగా ఓవర్ యాక్షన్ చేసామా మనం.
లేదు సార్, మీరు చెప్పినట్లు ఇప్పుడు మేము మామూలుగా మనకి మీరు మెటీరియల్ లో కూడా ఇచ్చిన క్వశ్చన్ లో మీరు చేసిన క్వశ్చన్ ఒకలా ఉన్నాయి సార్. కానీ మనం ఎప్పుడైతే గేట్ మెటీరియల్ ఓపెన్ చేసామో చాలా ఈజీగా అనిపించింది సార్ అక్కడ.
వెరీ గుడ్, వెరీ గుడ్
సార్. థ్యాంక్ యూ వెరీ మచ్ సార్. యువర్ టీచింగ్ ఇస్ ఎక్సలెంట్ సార్. థ్యాంక్
యూ నాన్న. ఆల్ ది బెస్ట్. మై బెస్ట్ విషెస్ ఫర్ యువర్ బ్రైట్ ఫ్యూచర్.
థ్యాంక్ యూ వెరీ మచ్. థ్యాంక్ యూ సార్.
Hello sir.
Yes.
Sir, could you please explain
the
offset voltage?
हेलो बस गया कौन पे आते नहीं रहे 7 बजे से दिन में तुम दोनों को टाइम मई उसे भी बोले मई क्या हुआ? हेलो सर कौन टीका को जरा खाने के
హలో వెంకట్, నాయిస్ వస్తుంది, కొంచెం చూడవా?
సరే, నదీమ్ అబ్దుల్ అనే అతన్ని మ్యూట్ చేయండి సార్.
ఓకే సార్, ఓకే సార్, చూస్తాను.
వెంకట్ సినిమా చూపిస్తున్నారు.
ఓకే సార్, ఓకే.
हाँ वो चाय बना रखी है, रख देती नहीं है हमारे लिए.
Hello sir.
Yes.
Sir, I understood how to identify topology.
Yeah.
For a given circuit, how do we identify whether it's an amplifier or not?
Examiner will say given an amplifier, that means it is amplifier only. Why do you worry?
Whether if it's not given, sir. Like in general, I'm asking, sir.
In general, in the sense?
For any transistor, there are two transistors in series and there are some resistors connected for
See,
them.
amplifier means some signal they have to give. Only DC, the amplifier will not be there. All our circuits are amplifiers only. Why do you worry? If there is feedback, then we have to think. Negative feedback means amplifier, positive feedback is switch.
Sir, I was trying to say all amplifiers can be converted to BJT circuits, but reverse we can't, right, sir?
Reverse in the sense?
Like there are oscillators, different circuits made with transistors.
Okay.
So my point is how to identify amplifiers.
That we can easily recognize, because in amplifier there will be an input port and output. We are taking it back.
मजाक ला रहा तुमरे महफिल में.
Hello.
Hello. Yes, sir.
Yeah. Tell me.
My point was how to identify an amplifier from the given circuit.
How to identify an amplifier?
Yes, from any BJT circuits.
Okay. See, if it is a standard amplifier like common base, common emitter, and common collector, you will be able to identify. Yes or no?
Yes, sir.
If it is cascode, common base, these are the only popular amplifiers available. Why do you have a problem identifying them?
Like
We have
if
seen
there
no,
are
if input is given at base, output at collector, input is given at base, output at emitter.
yeah, sir.
These are the standard amplifiers available.
Yes, sir. We solved for all possible amplifiers, but what if they are different circuits and if it's not mentioned an amplifier? How can we? I was just looking.
So
at
that I have to see. You know, you are speculating something. But if something is there, we can have an approach towards it, no? Because the moment you find, it will be one among this amplifier only.
Okay.
A signal should be there. Input should be given either at base or at emitter. You cannot give input at collector. So then that way you can also, go through the process of elimination. Input should either be given at base or emitter. You cannot give at collector, no?
Yes, sir.
So that way we can isolate. If somebody is given at collector and then the input, then we can simply say it is not an amplifier. Supply should also be there. Swing limits you should know. Lot of factors are there.
Okay, sir. So I have another doubt. When in oscillator, sir, when signal is like we take input from microphones, no, sir. So when signal is sinusoidal or single wave, but noise is multi-wave, right, sir?
Yes.
How does op-amp process this, or it gives us only single sinusoidal wave?
See, first of all, noise is just a disturbance, that's all. A sinusoidal waveform is also a disturbance, but a proper disturbance with a specific frequency and period.
Okay, sir.
So, noise means what? Noise means a circuit is subjected to noise when you switch on the supply. When you switch on the supply, you are giving a step input. The sudden step input when you are giving, the frequency domain analysis of step function is sinc function. So when you suddenly switch on the supply, you are giving all sine waves in the circuit. And the circuit has to pick only one disturbance, no?
Yes, sir.
Where the travel time and the period both should match. When the signal goes one loop round, suppose if it takes 1 millisecond, a sine wave of 1 millisecond time period only will be selected. Because only that signal after completing will come to the original point. A sine wave is there, no, it will start. And again it has to come back to zero.
Yes, sir.
Only that signal it will pick.
Okay.
Because the travel period and its period should match 360 degrees phase shift. That is what is called 360 degrees phase shift. See, simple here. Suppose I am designing an amplifier with a frequency of 1 kilohertz. What do you mean by 1 kilohertz?
1 kilo cycles per second.
1,000 times that signal will go around that oscillator.
Yes, sir.
That signal will go around that oscillator 1,000 times in 1 second. V0 will increase, VF will increase, we have told, no? That circle
Yes,
it will do 1,000 times. Okay. So only that signal has to get selected, obviously. Yes or no?
Yes, sir.
All other sine waves, they are not doing this. That the delay offered by them and the delay offered by the system should match. That is why it is called a frequency selective circuit.
Okay. What if there are multiple signals, sir? Can it handle?
Yeah, the multiple signals will be there. Oscillator will take all the multiple signals. Those signals will be added as harmonics to this fundamental.
Okay.
All the harmonics, they are cancelling within each other. So it's, I don't know how to speak an analogy. If suppose there are 10 people here,
Yes,
10
sir.
people are there, you are selecting one. If you ask me what happened to the 9, I have to say the 9 people killed each other.
Okay.
All the other frequencies you are worried, no?
Yes,
All the
sir.
other frequencies, they don't follow Barkhausen criteria. There is only one sine wave which will complete 360 degrees phase shift. The other sine waves, they are going to cancel each other, and they are the harmonics to this fundamental.
Okay, it's like tuning. FM.
Yeah, it's like, yeah, now you getting. Tuning is that,
Yes.
right? What happened to other frequency? Frequency will be there, but to this fundamental, they will be there as harmonics. Little information of other frequencies also will be there.
Okay. Yes.
The spectral purity is 80 dB below, I'm saying. If you are
It's an
fundamental
ideal
is
one, sir.
Huh?
Okay. Is a 80 dB an ideal one?
80 dB is high, very high, no? 1 by 1000, 10,000. If your fundamental is 1 by 10,000 will be all the harmonics put together. So it's like 0.00001. 0.0001 will be the strength of all other frequencies on this fundamental.
Okay, sir. Sir, one more question is that when we call a circuit as detector, what does it do, sir? We call Smith
Detector means
peak,
what? What you are detecting, that is more important. No?
peak detector. Does it detect?
Once peak comes, it will charge to peak and show you that voltage. That's all.
The circuit shows us a voltage, sir.
If it is a peak detector, it will charge to peak and show that voltage. That's it. No?
The Smith trigger is like square wave detector, no, sir.
Yeah.
So, how does it detect? I didn't understand that.
Detect in the sense when it crosses the threshold, the output will flip, no? There is a threshold which you want to cross. Once
Yes,
it
sir.
crosses the threshold, it's an indication. Or you can do one thing. At the output, you can put one LED bulb.
Okay.
Whenever the output increases, you show me with a light indication. It's called detection.
But in circuits like detection, I didn't
Detection means
understand
that when it is at logic 1, rest else it should be logic 0. So it is detecting. Suppose zero crossing detector is there. Whenever it crosses zero line, the output is high. So you put an LED there. That LED will, whenever it glows, it is giving you a feeling that the signal has crossed zero. Is it not detecting that point?
Yes, sir.
That's all.
Yes, understood. Thank you, sir.
Yeah,
You
yeah.
really structured this syllabus in perfect way, sir. I really liked it. Thank you so much.
Thank you.
Hello, sir.
Yes.
Hello, sir.
Yes.
Sir, in amplifiers, we are considering the topology, right, sir?
Yeah.
But when we are seeing Rin and R0, we are considering type of feedback, sir. Is there any reason? Or both
When
are,
we are considering
we can take
Rin and R0, that is also topology only, no?
the type of feedback we
Topology
are
and feedback both are same. Rin and R0, series and shunt, that is topology only. Series shunt,
okay, sir.
topology, high input resistance, low output.
Okay, sir. Sir, and actually, sir, your teaching is very nice, sir, and I understood all the concepts.
Yeah.
Hello.
Yes, tell me.
Sir, only tough thing I felt is diodes, sir. Like.
Very good. Yeah, I think you are 100% correct. Because diode demands a strong background of KVL and KCL. So
Yes.
every diode circuit needs more practice. You are right.
Okay, sir. And other than diode, everything is easy only, sir. MOSFET and all are very easy, sir.
Very good.
Sir, for approaching to diode problems, the only thing is practice.
Only thing is practice. See, let me tell you honestly, even I still have fear on diodes. So now you can imagine, fear on the diode in the sense, 2 diodes, 3 diodes I can manage. If somebody gives me multiple diodes at different, but
Yes,
multiple transistors I can solve. For
Yes,
example,
yes.
multiple MOSFETs are there, 8 MOSFETs. We were able to do it comfortably. But
Actually,
if 3 diodes are given, yeah.
Multiple MOSFETs are more easy than single MOSFET thing.
Okay,
After listening to the classes, I felt like that, sir.
Very good.
But in the case of diodes, that only, sir, I am practicing the more diodes.
Yeah. Diodes, there is it needs practice, more practice. In the sense, after doing network classes, right?
Okay.
After solving more questions, then you come back. Is network over for you?
No, sir.
Then after networks, you will find diodes very easy.
Okay, but now we will feel network very easy, sir, because you have explained KCL and KVL very nicely, sir.
Thank you.
Hello, sir.
Thank you, sir. Thank you very much.
Sir, for
Okay. All the best.
calculation of
Thank you.
input resistance, you said that we need to remove RN and RL, na, sir.
Yeah, input resistance is a function of RL. RL should be there for input resistance.
Yes, sir.
Output resistance is a function of RS. Output resistance will change when RS changes. Input resistance will change when RL changes. But input resistance has got nothing to do with RS.
Yes, sir.
Output resistance has got nothing to do with RL.
Sir, but in resistance reflection rule, we are considering RN and R0, na, sir.
Yeah.
Why, sir?
In resistance reflection rule, we are considering Rn and R0. Yes.
Why, sir?
But I didn't give you source resistance there, no?
Okay, sir, but here one problem, na, sir. There is RS and one voltage divider, R1 and R2, and you are considering RS, sir, here.
It depends on where I give the arrow. If the arrow is at the source, then RS you have to include. It all depends on where you provide the arrow. I am telling amplifier. What do you mean by an amplifier? Amplifier does not include source, no?
Yes, sir.
Input resistance of amplifier means source we have to remove. If I say I want input resistance seen by the source, then okay, RS you can include.
If the arrow is
all depends on where he gives the arrow.
Okay, sir. If he includes RS, then we need to consider, sir.
Obviously, see, suppose I am giving a circuit like this. Suppose my circuit is like this. This is an amplifier, right?
Yes, sir.
For this amplifier, this is my RS. If my arrow is here, then RS is excluded, no?
We need to neglect.
If RS is here, then RS is included.
Okay, sir. Sir, another doubt, sir. In BJT, what is the value of alpha, sir? We are simply calculating RC by
Beta by beta plus 1. 100 by 101. 0.99.
Beta by beta plus 1. Okay, sir. In MOSFET, it is 1.
MOSFET beta is infinite.
No,
IV
sir.
is 0. Alpha is 1.
Okay, sir. Okay, sir. Thank you, sir.
Okay.
Hello, sir.
Hello, sir.
Yes.
Good evening, sir. Hello.
Yes.
Sir, are power amplifiers included in the syllabus, sir?
No, not included. But you can solve any power amplifier thinking it is a normal BJT.
Okay, sir.
Are you getting?
Yes, sir. Yes, sir.
Yeah. See,
Yes,
complementary symmetry pair is there. That is one NPN and PNP combination. That is the popular power amplifier. That problem we have already solved in class, no? But I didn't mention it as power amplifier.
Okay. Got it, sir.
Yeah.
And sir, thank you, sir. It was very.
Thank you. Good luck.
Sir,
It's a
in one
pleasure.
of the hello, sir.
Yes.
So in one of the Zener questions, we will find RS minimum. Do you remember, sir?
Yes.
In denominator, we have IL and INE. I mean, IZ. For RS to be minimum, we should take IZ maximum, no, sir. Why we took IZ knee, sir?
No. Always remember, when VS is VS minimum, IZ is IZ knee. For a minimum input voltage, the current that flows in the Zener is knee current only. For minimum voltage, maximum current will not flow. Always remember, minimum voltage, minimum current, Zener. If you give maximum voltage, then it is different.
But that across the Zener, voltage will remain constant, no, sir?
Voltage will remain constant. I am talking about current. Current is knee current. If somebody asks you when knee current will flow, what you will say? My input is going from 5 volt to 50 volt. When minimum knee current should flow? For 5 volt only, no?
Yes, sir.
So when VS is VS minimum, IZ is IZ knee. But if you want RS minimum, your IL should be IL maximum.
Okay, then when we increase VS, we will be getting more IZ.
At least for that VS minimum, if IZ is there, if your VS increases, your IZ will be more than knee. So the Zener will not go to off state. If you make maximum current at that point, what happens? If you increase more than VS, Zener will go, no smoke will come from Zener. Zener cannot handle more than IZ max. For minimum voltage itself, if maximum current flows, then what will happen for maximum voltage at input? Zener is gone, no?
Yes, sir. But just some little current less than IZ max if you will go, then RS will be still minimum.
That little current is knee current should flow for a small input voltage, minimum input voltage.
Okay.
Yeah, such that after you keep on increasing the current will be more than knee current. And Zener will never go to off state.
Okay, sir. Thank you, sir. Those analogies which you give were really easy, sir. They were handy to understand things.
Thank you so much.
Thank you, sir.
Yeah, all the
We need
best.
to prepare 25 timer, sir.
No, not needed.
Okay, sir. Sir, how to book actually? Sir?
555 timer not needed.
Okay, sir. Thank you, sir. But sir, is notebook and that workbook is enough for preparation?
Yes. Volume 2 you prepare, my notes you prepare, and then you go for previous questions.
But sir, diode questions are easy in notes for me, but workbook also. But when I see previous book now, that 2021 book, I felt very tough, sir. I'm not able to
You need
even
practice,
understand.
that's all. Is networks over for you?
No, sir. Tomorrow it is starting.
Then after networks you will find diodes easy.
Means first, as per notes, first you taught us op amp, no, sir. Then we have to follow like that, no, because in that book, first diode is there. That is why I'm asking.
First you solve op amps. Then after that you can go for diode.
Yes, sir. Thank you, sir. Good night, sir.
Okay, thank you so much. Good luck.
Thank you, sir.
Yeah.
Hello, sir.
Yes.
Hello, sir.
Yeah.
Sir, could you please explain me about integrator doesn't work after offset voltage?
Yeah, see, if offset voltage is, even if you don't give any input, if there is a small offset voltage at non-inverting, the capacitor will keep on charging, no? Because of that. There will always be a current of VOS by R. So even without input, the capacitor will charge to the maximum and it will saturate. So you have to throw that, design. Because even without input, if it saturates, after giving input, it will still be in saturation only.
Okay.
So it is not an integrator anymore.
Oh.
When do you say that a circuit is good? When no input is there, your output should be 0, not plus VSAT.
Yes, sir. I understand.
So with no input, you are getting plus VSAT means it is a dead circuit.
Okay, sir. I understood, sir.
Yeah.
And thank you so much, sir, because after your teaching, I love to solve problems in analog circuit. Earlier, I was
Very good.
afraid of
It is
analog
so
circuit.
nice to hear. Keep in touch. Best wishes. Best wishes.
Thank you, sir. Thank you so much.
హలో సార్
Yes.
సార్ అది నిన్న ఆసిలేటర్ సర్క్యూట్ లోని మీరు చెప్పినప్పుడు సార్ చెప్పారు బఫర్ అంటే ఫస్ట్ ఏదైనా ఆసిలేటర్ సర్క్యూట్ ఉంటే ఫస్ట్ బఫర్ కి టెస్ట్ చేస్తాం, అది బఫర్ కి వర్క్ అయితే ఇంకా దేనికన్నా వర్క్ అవుతుంది అన్నట్టు చెప్పారు సార్.
అంటే ఎప్పుడైనా కంట్రోల్ సిస్టమ్ విల్ రన్ అండ్ యూనిటీ గెయిన్ ఫీడ్బ్యాక్. ఎందుకంటే యూనిటీ గెయిన్ ఫీడ్బ్యాక్ సిస్టమ్ హ్యావ్ ద మాక్సిమం లూప్ గెయిన్.
అదే సార్
అదే నాన్న, ఏ బీటా ఈక్వల్ టు ఏ కదా. మొత్తం ఉన్న సిగ్నల్ మొత్తం తీసుకొచ్చి ఇన్పుట్ దగ్గరికి ఇస్తున్నాం. అవుట్పుట్ ని అటెన్యూయేట్ చేసి ఇవ్వడము మామూలుగా మనకు పద్ధతి. బఫర్ ఏం చేస్తుంది, అవుట్పుట్ లో ఉన్నది మొత్తం తీసుకొచ్చి ఇన్పుట్ కి ఇస్తుంది. సో బఫర్ కి మీరు పెద్ద కెపాసిటర్ పెట్టి మీరు కాంపన్సేట్ చేయగలిగితే అది బఫర్ నే పనిచేసింది అనుకోండి, ఏ సర్క్యూట్ కన్నా పనిచేస్తుంది అంటాడు వాడు.
అంటే ఇంకా దేనికన్నా సరే ఆ ఫీడ్బ్యాక్
స్టేబుల్ అయిపోతుంది. మీరు బఫర్ కి స్టేబుల్ చేయగలిగితే పెద్ద కెపాసిటీ పెట్టి మీరు ఏ సర్క్యూట్, మీరు యాడర్ కాదు సబ్ట్రాక్టర్, మీరు ఏమి ఇచ్చుకున్నా అది ఆసిలేట్ కాదు. కానీ మీరు స్టెబిలైజేషన్ చేసేటప్పుడు మీరు ఏ ఒక యాడర్ సర్క్యూట్ కో ఇంటిగ్రేటర్ కో పెట్టి చేశారనుకోండి, దాని తర్వాత మీరు లూప్ గెయిన్ పెంచారనుకోండి, లేకపోతే దాని తర్వాత బఫర్ కనెక్ట్ చేశారనుకోండి, మేబీ అది ఆసిలేట్ అయ్యే ఛాన్స్ ఉంటుంది. అప్పుడు మీరు ఏమంటారు, ఈ ఆప్ యాంప్ అయితే ఈ సర్క్యూట్ కొన్ని సర్క్యూట్లకు పనిచేస్తుంది, కొన్ని సర్క్యూట్లకు పనిచేయదు అంటారుగా. డిజైన్ కొనుక్కుంటాడు వాడు, షాప్ వేరే షాప్కి వెళ్ళి కొనుక్కుంటాడు. అప్పుడు ఈ షాప్ లో కొనుక్కుంటే వాడికి తెలియదు ఆ డిజైన్ లో ప్రాబ్లం ఉందని.
Yes, sir.
సో మనం
అంటే
ఎట్లా
buffer-
డిజైన్ చేయాలి? మీరు ఏ సర్క్యూట్ ఇచ్చి కనెక్ట్ చేసుకున్నా మీకు అది ఆసిలేట్ అవ్వకూడదు. అంటే వాడు మ్యానుఫ్యాక్చరింగ్ చేసేటప్పుడు ఏ సర్క్యూట్ గురించి థింక్ చేస్తాడు చెప్పండి? ఏ అవుట్పుట్ అయితే మొత్తం తీసుకొచ్చి వాడు ఇన్పుట్ కి ఇస్తాడో ఆ సర్క్యూటే. ఎవడు వాడు? బఫరే.
అంటే బఫర్ ఫస్ట్ కేస్ సినారియో లాగా.
అంతే కదా మరి. బఫర్ ఉన్న మొత్తం గెయిన్ ఏ బీటా ఇస్ ఏ. అందుకే ఏ క్లోజ్డ్ లూప్ ఫీడ్బ్యాక్ సిస్టమ్ స్టెబిలిటీ ఈస్ ఆల్వేస్ అండర్స్టూడ్ బై అన్ ఓపెన్ లూప్ ఫీడ్బ్యాక్ సిస్టమ్. ఓపెన్ లూప్ సిస్టమ్ చూసే మీరు క్లోజ్ లూప్ సిస్టమ్ డిజైన్ చేస్తారు. ఓపెన్ లూప్ సిస్టమ్ ఏంటి? ఏ బీటా ఈక్వల్ టు ఏ తీసుకోవాలి. తీసుకొని 180 రాకుండా చూసుకుంటే మీరు ఫీడ్బ్యాక్ ఇచ్చినప్పుడు ఎలాగో 180 వస్తుందిగా, అప్పుడు 360 అవుతుంది. ఆ 360 అవ్వకుండా ఫేజ్ మార్జిన్ మెయింటైన్ చేయాలి అంటాడు వాడు. అర్థమైందా?
సార్ ఇంకోటి సార్, ఇది ఫీడ్బ్యాక్ యాంప్లిఫైర్స్ లో అంటే ఎటువంటి క్వశ్చన్స్ ఎక్స్పెక్ట్ చేయవచ్చు సార్? అంటే
ఈ ఫీడ్బ్యాక్ యాంప్లిఫైర్ లో వాడు ఇప్పటి వరకు టోపాలజీని రికగ్నైజ్ చేయడం ఒక్కటే అడిగాడు.
అంటే ఒక బీజేటీ గానీ మాస్ఫెట్ నెట్వర్క్ లాంటిది
మాస్ఫెట్ ఇచ్చి ఇది ఏ టోపాలజీ అంటాడు వాడు. అంతే, ఇంకా అంతకన్నా ఏం లేవు. ఆ RF R1 రెండు ఇచ్చి 10 గెయిన్ ఒకటి వచ్చింది చూడండి, అది ఒక 2 సార్లు అడిగాడు. ఇంకంతే, ఇంకంతకన్నా ఏం అడగలేదు.
థ్యాంక్ యూ వెరీ మచ్ సార్, చాలా మీరు చాలా హెల్ప్ చేశారు సార్.
రైట్. ఆల్ ది బెస్ట్ నన్ను.
ఎస్, థ్యాంక్ యూ సార్.
Hello?
Yes.
Audible? Hello?
Yes.
Is it audible? Sir, is it audible?
Yeah, now it's audible. Tell me.
Yes, sir, I was trying so long.
Yeah, tell me.
Sir, I want to ask about that precision diode, that ideal diode.
Yeah.
Sir, in diode means it allows current when it is in forward bias.
What?
So, when a diode is connected, when it allows current, but when ideal diode will be connected, then how op-amp will allow current to flow?
See, it is the op-amp who is driving that diode, no?
Yes, sir.
See, this is an op-amp circuit, and you have connected a diode here. It is the op-amp who is driving that diode whenever VOP is positive.
So then, whatever current will enter, that current will flow from the back, depending on the
You want to know the
resistors.
loop? Okay. See, this is a loop, no? This ground. So here we are giving signal. So if you want a loop, it is going like this. Through op-amp.
Okay. Sir, can you explain a level shifter once?
Level shifter. Level shifter is just if you give any voltage here, 5 volt. If you take output at emitter, it has level shifted the DC by 0.7, 4.3 volt. Suppose I am having a sine wave with 5 volt. There is a sine wave. If you give such a sine wave here, what will happen? The diode will take a drop of 0.7. No? Then this voltage is going to be at 4.3 DC. If you put one more transistor, another 0.7. If you put one more, another 0.7. So for 7 volts, you have to put 10 times. Instead, what they have done is, they have connected a current mirror here. Current mirror. So if this is 7 volt, we have done a problem. The output should be level shifted to 0. So this drop we have to maintain 7 volts. That's all. 7 minus 7 is 0. That is the level shifter.
So how we need to maintain that drop?
Because of by the designing R value. Suppose if your current here is 1 milliampere, this current is also 1 milli. Already 0.7 is there. This is 6.3 volt. 6.3 by 1 milli means 6.3K you have to connect. The design of R is 6.3K so that the drop here will be 7. The resistor you have to adjust to value. For different values of resistor, different drops will be there. No? Ohm's law. V equal to IR.
Okay, but the level shifter job is just to
one drop it will create such that this 7, see, I want 0 here, I want 0 here, 0 here, I am giving 7. What is your job of level shifter? To see that from here to here there is 7 volts drop, such that 7 minus 7 becomes 0. Now we will say that, oh, level shifter is doing the job of capacitor, because capacitor will completely charge to 7 no? If you give 7 volt. And it is going to give you 0 capacitor. Capacitor job is what? To block the DC. If I give some DC voltage here, capacitor is going to charge to that DC and output is going to be 0. This job is done by that level shifter. What level shifter will do? How much capacitor is charging, that much drop it will create. That's all.
That only that part is level shifter where we are giving V1 and V12 resistor.
Yeah.
And so today you explained that only op-amp does not have that virtual short property. Every like BJT and MOSFET also have.
Op-amp does not have.
So you said that today that VB can be 0.
VB can be 0.
Yes, sir. So means is there any condition that gain should be infinity or like that? One condition you said that there should be negative feedback.
Yes.
And is there any other condition for VB to be 0 and or VD to be 0 VDS?
No. You have to apply that VB0, IB0 only when there is negative feedback. Only see why we are doing it is, tell me if there are 3-stage, 4-stage amplifier, how you will do? It will take time, no? Doing AC analysis. Instead, this is the method we are using, VB0, IB0, only when there is negative feedback. See, the point is when you are applying virtual ground for op-amp, which has got 25 transistors inside, why not apply for a 2-stage, 3-stage amplifier?
So means like op-amp here, just we have to see if there is negative feedback, then we can directly.
Yes. Then we can apply virtual short, even to BJT circuit.
In any type of question.
Any type. Yes. Let me give you a simple example. What is common collector amplifier gain? 1, no? Common collector CC amplifier, what is the gain? It is 1. Yes or no? But common collector also has negative feedback, I told you. Yes or no? So if this is Vin, common collector VB 0. That means VB equal to VE. So this is VB. It is equal to VE. VE equal to VB equal to Vin. So the gain is 1. No? For this we have done DC analysis, AC analysis. Are you getting what I am saying?
In previous question, we have considered that IC is equal to IB. Then in that case also we are considering virtual short.
IC equal to?
We are most of the questions we are considering that we have got
IB we are neglecting in negative feedback.
Yes, sir.
Yeah.
Okay,
Whenever there is negative feedback, you can apply this technique.
Okay, sir.
Yeah.
Sir, and last doubt that topology feedback you named now. You sometimes you said from front you will make
Topology is from input to output. Feedback is from output to input. 2 names you can give. Topology if it is series or series shunt topology, it is a voltage control voltage source. Feedback you can talk like this: voltage to voltage or voltage series.
But topologies and feedback are same thing now.
Topology means what? Connection. Feedback means what you are feeding back. What you are taking and what you are giving is called feedback.
So sometimes you write voltage series. That also I didn't understand.
Yeah, that's what I'm saying. Suppose I'm having shunt series amplifier. This is current control, current source. What is the topology? Shunt series. Like this you have to see. What is the feedback? back, current to current or current shunt, like that. Shunt, if it comes in the beginning, it is topology. If shunt comes in the end, it is feedback. Because you are coming from output to input, no? You see that list, you will understand, no? You see that list carefully, okay?
Everything was so clear earlier, but yesterday, day before yesterday, I was unwell, and from that day, I cannot track you, and I got so disturbed.
Day before yesterday?
So from CMRR, before that, everything was going right, and from CMRR after oscillator.
After CMRR, what is their frequency compensation we have done?
Yes, sir. So, after that, before that, I was so confident, and that after here.
What is the last topic? Generally, we teach last topics because questions will not come from there. The topics in the beginning are important, no? Last topics and all, if you see previous questions, oscillator, 2010 years back, one question they have asked. In some batches, we don't even teach oscillators. Are you getting what to do? Because questions will not come, is waste. So in the end, we will teach. Similarly, feedback amplifiers also. Very rare they will ask.
And non-ideality?
Non-ideality is what is their slew rate, CMRR, offset. That's all, no? Last is frequency compensation.
Thank you so much, sir. Analog was such a difficult subject for me.
See, the point is, if you treat analog as a subject, controls as a subject, networks as a subject, then it's okay. Because we are treating it as subject. The point is, analog, digital communication, these are your own core, no?
Yes, sir.
Hardcore. An electronics student should not think analog is one subject. Because that is core. If 5 subjects he will study, pulse digital circuits, linear IC applications, so many. Is it not? It is your core. In this core, the biggest headache when you teach core is control systems will come into picture, networks will come into picture, little signals will come into picture. Because that's when you can understand the plots and all that. Are you getting circuits? Yeah. All the best.
Thank you, sir. I am facing little problem in multi-stage amplifier. So I will WhatsApp you, please.
Sure.
Thank you so much.
Okay.
సార్ గుడ్ ఈవినింగ్ సార్ చిన్న డౌట్ సార్. సార్ మన ఈ ఓప్యాంప్ ఇప్పుడు మనం బీజేటీ తీసుకుంటే ఇన్పుట్ కరెంట్ ఇస్తే మనకు అవుట్పుట్ కొంచెం కరెంట్ పెద్ద, కానీ ఈ ఓపీఎంప్ ఎప్పుడు మనం ఎక్స్టర్నల్ రెజిస్టర్ నుంచి అవుట్పుట్ వస్తుంది కదా సార్. ఓపీఎంప్ వల్ల ఉపయోగం అంటే ఎట్లా సార్? నాకు అది
సప్లై నుంచి వస్తుంది, అది వోల్టేజ్ సెన్స్ చేస్తుంది. ఇప్పుడు ఒక యాంప్లిఫైర్ కరెంట్ తీసుకుంది అనుకో, అప్పుడు అది వేస్ట్ యాంప్లిఫైర్. ఎందుకంటే ఆ సిరీస్ రెసిస్టెన్సే మొత్తం చప్పరిచ్చేస్తుంది ఉన్న సిగ్నల్ అంతా.
ఓకే అంటే మనకి
సిగ్నల్ ఉంది, నా దగ్గర ఒక మైక్రోఫోన్ ఉంది. ఆ మైక్రోఫోన్ కి సిరీస్ రెసిస్టెన్స్ 9K ఉంది అనుకో,
మనం మాట్లాడిన బయటకి
ఆప్ యాంప్ కరెంట్ తీసుకుంటే గానీ అవుట్పుట్ ఇవ్వకూడదని నీ ఇన్పుట్ రెసిస్టెన్స్ 1K ఉంది అనుకో, ఉన్నది మొత్తం సోర్స్ అని చప్పరిస్తుంది. ఇంకా ఆప్ యాంప్ ఎక్కడి నుంచి సెన్స్ చేస్తుంది?
సరే సార్ అంటే నాకు ఆ డౌట్ వచ్చింది సార్. ఎప్పుడు చూసినా మనం
ఇన్పుట్ రెసిస్టెన్స్ ఎక్కువ ఉండాలి, అప్పుడే సిగ్నల్, ఆ చిన్న సిగ్నల్ చచ్చిపోయి ఉంటది ఆల్రెడీ. మైక్రోఫోన్ లో వచ్చిన అవుట్పుట్ ఆల్రెడీ చచ్చిపోయింది, దాన్ని యాంప్లిఫై చేయాలి. యాంప్లిఫై చేయాలని నువ్వు కనెక్ట్ చేసి సోర్స్ ఏ మింగేస్తున్నాడు అనుకో, ఇంకా యాంప్లిఫైర్ ఎక్కడి నుంచి, యాంప్లిఫైర్ కనపడదు, ఎతుకుతుంటది ఎక్కడ ఉందిరా బాబు సిగ్నల్ అని. అప్పుడు సోర్స్ చెప్తుంది, బాబు నీ ఇన్పుట్ రెసిస్టెన్స్ కొద్దిగా ఎక్కువ ఉంటే నేను మాట్లాడేది ఏమన్నా నీకు వినిపిస్తుందా నాయన, లేదంటే ఉన్నదంతా నా దగ్గరే ఉంది అంటది.
సార్ ఇంకొకటి సార్, ఈ ఈఎస్సి లో డయోడ్ టాపిక్ నుంచి మొత్తం ఈ రెక్టిఫైర్స్, టిల్టింగ్ ఇవన్నీ అడిగాడు. మనకి గేట్ కి అవసరం లేదా సార్? ఈ రెక్టిఫైర్
గేట్ కి అవసరం లేదు, గేట్ కి అదే మనం రెక్టిఫైర్స్ చేసాంగా, సరిపోద్ది.
అంటే ఈ మన ఫుల్ వేవ్ రెక్టిఫైర్, హాఫ్ వేవ్ రెక్టిఫైర్ లో ఈ సరిపోతుంది కదా సార్? అంతే
గేట్ కి అసలు రెక్టిఫైర్ అనేదే ఉండదు. ఓ ప్రాబ్లం ఇస్తాడు, అది అవుట్పుట్ ఏంటి అని అడుగుతాడు. క్లాంపరా, క్లిప్పరా, పీక్ డిటెక్షన్, ఆ వోల్టేజ్ ఎంత, కరెంట్ ఎంత, ఇవే ఉంటాయి. గేట్ ఆ కరెంట్ ఎంత, ఈ వోల్టేజ్ ఎంత, వోల్టేజ్ ఎంత, కరెంట్ ఎంత, ఫ్రీక్వెన్సీ ఎంత, బ్యాండ్ విడ్త్ ఎంత, ఇలా ఉంటది.
సార్ గేట్ లో ఒక క్వశ్చన్ సార్, అది కెపాసిటెన్స్ గురించి, డయోడ్ మీద కెపాసిటెన్స్ గురించి అడిగిండు. అది దీనికి
ఆల్రెడీ చేసాగా,
అవుట్పుట్ కనుక్కోవడం కదా సార్ మనం ఇట్లా. ఏది మన ట్రైనింగ్ స్విచ్చింగ్ ఒక క్వశ్చన్. ఓకే సార్, నేను ఒకవేళ అది అర్థం కాకపోతే మీకు
పంపించు, చూస్తా.
ఓకే సార్. సార్ ఒకసారి మేము ఆల్రెడీ ఒక క్వశ్చన్ పంపించి సార్, కొంచెం రిప్లై ఇవ్వండి సార్.
చూస్తా ఎందుకంటే రోజు క్లాసులు అన్ని ఉన్నాయి కదా.
ఎస్ సార్.
ఇప్పుడు రేపటి నుంచి ఫ్రీ, నాకు ఇదే పని.
ఓకే సార్.
ఓకే రైట్.
థ్యాంక్ యూ సార్.
ఎందుకంటే స్టూడెంట్స్ కూడా ఎక్కువ ఉంటారు కదా నాన్న.
లేదు సార్, నేను ఫీల్ అవ్వను సార్, అది చేస్తాను. థ్యాంక్ యూ వెరీ మచ్ సార్.
రైట్ నాన్న.
గుడ్ నైట్ సార్.
ఓకే.
సో ఈ కేసులు తొలితే మనం తెలుసుకోవాల్సినవి చాలా విషయాలు. మనం ఒక్కోసారి అక్కర్లేదనుకునే ఒక చిన్న విషయం ఆ కేసుకే ఎంతో ముఖ్యమైన ఎవిడెన్స్ కావచ్చు. చాలా చాలా చిన్న విషయం, అది ఏముందిలే అని అనుకోండి.